So many thanks, first of all, good morning. Second, many thanks, Antonio and other conference organizer for invitation. I'm really very pleased to be here again because 7 years ago it was also online presentation, maybe the first online in Hydride. So again, Antonio was very flexible for this new format of presentation at the conference. And so here I introduce very shortly some main results, and afterwards I try to concentrate on our new results on magnetic properties of superconductors, and at last part just show some what possible development of this activity, hydrides. So let's start. So we will talk about this so-called superhydride, which shows very high critical temperature, nearly at room temperature. No, that's very clear. That's of course important. How it started? In fact, it's some kind of complex development. One of the main point was suggestion of Neil Ashcroft that superconductivity, high temperature superconductivity could be high not in metallic hydrogen, which he studied, and he predicted that metallic hydrogen should be high temperature superconductor, but also in hydrogen dominant materials. He proposed methane, xylene, and so on. In fact, it's not the best proposition, but the idea 10 hours was very fruitful. I want also to mention, even before it was suggestions that hydrides could be useful for study of superconductivity, but that time it was modest thorium hydride with modest critical temperature 8 kelvins. What else? So it's again, at the beginning it was general suggestion, which in fact particular material did not work well. Second, what really worked much better, these crystal predictions, this development of crystal predictions. And now theoreticians can really predict, it's really amazing that crystal materials can be predicted from ab initio such. So as soon as crystal structure is known, it's not a big problem to estimate superconductivity. In this way, it was suggested a lot of superconductors. In fact, this list now, I don't know, 200, 300, maybe more of materials. And it was really impressive predictions, like already 10 years ago with calcium hydride with critical temperature 200 Kelvin. But during these 10 years, it was not realized until now. So recently it was really realized. But other materials, it's very difficult sometimes. Also predicted very high critical temperature, but it's difficult to realize experimentally. But experimentally, it's another set point for this development, because these all predictions should be verified, should be checked, and give some feedback, and so on. So one of the most important development here is electrical measurements. What you see here for electrical leads in diamond angle cell, here sample, in this case lanthanum hydride, which formed when we heated lanthanum sample in atmosphere of hydrogen. Hydrogen also clumped in this hole. And afterwards we measure superconductive steps in different combination of electrical leads. So it means that real sample is normally not very uniform. So in one combination, good step, another not as good step, but anyway, critical temperature is the same. And also important here, not only, of course, electrical measurement, but still pressure is high, so around 200 GPa. And fortunately, at that time, we already had this method and pressure in hand. And just few results. One of most important result is isotope effect, which we found. I skipped a lot. So first material which we found and studied is H3S. We form it from H2S, which in fact decompose to H3S. So H3S shows superconductivity around 200 kelvins. What is important is that when we replace hydrogen for the deuterium, so this superconductive step shifts a lot. So isotope effect really huge. It's in comparison with classical, for instance, mercury isotope effect, which is invisible here, 0.1 Kelvin or much less. And we studied carefully isotope effect with pressure. So in different structures, critical temperature is different. As for isotope coefficient, it was, in this particular compound, it was a little bit less than classical 0.5. Again, I skip a lot. So one important thing was just to confirm that it's real. I mean, this superconductivity is real. One is crucial was confirmation in other laboratories, and it was confirmed some time ago in Japan, in Osaka University, and recently it was in Bristol University. Superconductive steps was very well confirmed. But in fact, besides this, it was a lot of experiments in different laboratories with H3S, with various measurements. So of course, no doubts that this is real superconductivity. Even more important than reproduction is development. So development, it was, because sometimes superconductivity discovered, for instance, classical example, magnesium boride, but afterwards, in spite of many attempts, no progress with critical temperature, and no material was found similar to magnesium boride. Here, fortunately, is not the case. It was found lanthanum hydride. In fact, in this particular case, it was first predicted theoretical. And experiment shows superconductivity which is close to predicted. It's really amazing. And structures also. Again, we studied carefully, and isotope effect you see here, huge. By the way, here isotope effect was difficult to find because what is important, what is essential for superhydride, also quantum effects. I will not stop too much, but quantum effects play here a significant role. For instance, even for structure, it was difficult. This structure for deuterium, in fact, was metastable. It was difficult to find the structure. So, and another essential point here, you see just clearly, it's a lot of hydrogen. So all this activity with hydride, in fact, some kind of model of metallic hydrogen. What you see here, basically metallic hydrogen, heavily doped with lanthanum, 10% of lanthanum. So if one day we will see superconductivity in atomic hydrogen, it will be no wonder that superconductivity will be close to this. And next step, major step. The next step, major step is yttrium hydride. It was a lot of hopes for yttrium hydride because predictions was that critical temperature will be above room temperature. And so we spent a lot of efforts for this system. And And you see, we studied in this system many hydrides, starting from element on yttrium. You see how volume of hydride expands here. So 2.5 times expansion. And no wonder that critical properties also change. And for yttrium, what highest hydride which achieve yttrium H9 shows, of course, a high critical temperature, but not room temperature, as was predicted and expected. And as, in fact, most expectations were for yttrium H10, but unfortunately we could not reach it because even in prediction it's in metastable, and experimentally we could not synthesize it. In spite of we reached really very high pressures and temperature, around 400 GPa. Just to mention, so there is another group, group DS, which also measured yttrium hydride, but their result different from ours. So they showed high critical temperature and simply different. Okay. So when we have 250 GPa, so it's very, we can think about simple experiment. So in fact, I wanted to demonstrate this experiment just online, but it takes also time for preparation, even for this very simple experiment, but arrangement you can imagine easily. So here, box, I can show you this box. Here, I hope you see it, this box. And here, just device for measurements. Nowadays, it's very compact here. So, and we just cool with dry ice and see here superconductive transition. In fact, it's quick. This experiment can be done in 5 minutes, and we're done in 5 minutes. But still, 5 minutes is valuable. In American standard, it's millions. And so let's start now in more particular things like recent development of magnetic properties of our superconductors. So first of all, thanks for talk of yesterday talk of Fyodor Balakirev. I don't need to talk about measurements in strong magnetic field. He presented very clearly and many sense for this, and also introduction was very good. So let's start for susceptibility measurements. So first measurements was published here, and just I reproduce here. So we found very good step in zero field cooling at 200 Kelvin in very good correspondence with electrical measurements, which is in red line. Also, in fact, it's in many respects forgotten. We have done a lot also other measurements like this step in different magnetic field, and also very important also for the deuterium we have done the same. So susceptibility measurements which correspond to electrical measurements. So in fact, it's good measurements. Less good measurements were magnetic moment against magnetic field. And here we had very good big hysteresis, you see here, because of our pressure cell, of course not perfect. And in fact, it's very good. I want to say that it's really a good development because it's very small. Go to squid, go to pulse magnetic field, and go to more than 200 GPa. Now we have 220 GPa. I believe even higher pressure, it's not big problem. So it's really, and also simplicity, amazing. So it's just 4 parts. But here still it's magnetic, liquid magnetic, and therefore we have background. And with this background, still we have a good confirmation that critical temperature, the superconductivity disappears in 200 kelvins. Only later we managed to have more or less good magnetic measurements when we extracted from this raw data background. But still, it was not satisfactory in many respects because it's with ultimate measurements. We have done it only in a few samples which are relatively big. So it should be developed. And we could not do it in years. It's difficult. In fact, it's difficult. What happened recently, it was an interesting development that in our first experiment, it was also difficult because the starting materials, we use H2S. It's nasty material, difficult to experiment and decompose, and finally H3S. So a little bit complicated process. Here, everything started to be much simpler. We put sulfur, we put ammonium borate, and between envelopes, and heat sulfur with laser, and in this way conform lanthanum hydride. In here, we put lanthanum hydride as a sample, or sulfur, and heat it. And obtain H3S, or here lanthanum H3S, after laser heating. And why it's so important? First of all, it's much simpler preparation. Second, in this case, background extracted very clearly. So you will have background in this composition and then laser heat. So nothing changes except of sample. And here we have signal. So black curve, you see signal from this arrangement before laser heating. And after laser heating, signal changes. So here you see changes. And when subtract it, so signal is blue. So quite good strong symbols. The same for lanthanum hydride. And with this technique, we measured much better all this superconductive transition. And what is most important, finally, we managed to determine first critical field from this virgin curves at different temperature. So we have field penetration, and afterwards we transform to first critical field. And finally, we have London penetration depth. That's, of course, very important to know. Because in the first experiment, we just very roughly estimated this value. And next development, very recent, this trapped field. In fact, this idea was proposed by Jörg Hirsch as ultimate test for superconductivity. In fact, it was too much because we have so much evidence for superconductivity, but idea turned out to be useful and fruitful. So idea is the following. So if we say in Meissner effect here, and I mean, not only in Meissner, in this part of phase diagram. So when we in Meissner effect here, and so protocol is the following for this experiment. So we zero field cooling, and then apply magnetic field, different magnetic field in here. So 1, 2, 3, so a lot of magnetic field, switch off field, and there are vortex in the sample. So signal will remain after switching off of magnetic field. So trapped flux. And of course, it's not always observed because it should be pinning of vortexes. So magnetic moments should stay with time. In fact, it's known for many superconductors. For instance, for magnesium borate, pinning is strong, and trapped fields, trapped flux is used for compact, very strong magnets. So here in our experiment, we observe the following. At lower magnetic fields, when we switch off magnet, we see no increase of signal through temperature. So if in this case, when we go above to, in this case, 45 milliliters, some signal appeared, and its signal increase and then saturate. So it's around 4 Tesla. When we increase more than 4 Tesla, 6 Tesla, and so on, and switch off magnetic field. So in this case, signal not increase anymore. So we have what also useful you see here. So in fact we obtained a lot of information from this simple experiment, a lot of conclusions. One is this very obvious: we have critical temperature from these measurements too, of course, which is coincide with other measurements. So we have critical temperature. Second, we have phase critical field. Third, also, what is very useful that we have signal. In fact, we can go to high magnetic fields, because in this case, what is important, our cell does not give background, because no magnetic field, and therefore signal could be reached quite high. So it's very important for measurements at high pressures. So we can go to smaller samples in this case, and can do high pressure measurements, we believe, routinely. So it's a really big step for high pressure measurements. And maybe not only, because of course this method is known, but I believe that it's underestimated for routine measurements when you have small fraction, for instance, of superconductive phase. Okay, so
you should go to your conclusion if possible, because
okay,
25 minutes
so
are
I
over.
will accelerate, in fact. So very good demonstration of creep, so with time. So here, today's sample signal nearly unchanged, similar to magnesium borate. Also, another demonstration for lanthanum hydride. This is good demonstration that during experiment, diamond broken. And in this case, you see here that signal disappeared, and also you see the background from this cell is very small, in spite that it was after 4 tests. And for conclusions, what we measured coherent length with London penetration depth, and which is unusually smaller than for high temperature superconductors, and Ginsburg-Landau parameters shows that we have moderate type 2 superconductors. Just few words about futures usually. So future is room temperature superconductivity, which is allowed basically from theory, no limited within some approximations. And for hydrogen, particular calculations shows that for megawatts, it could be above room temperature. And recent calculations also propose binary system for cerium, also about room temperature, lutetium also, and lanthanum, even lanthanum. And more perspective is for ternary. For ternary, it was predicted some time ago, even 400 kelvins, and recently predicted a lot of compounds, number of compounds above room temperature. Just very shortly summarize what we have. We have 2 types of superhydride, H3s with strong covalent bonding of hydrogen with sulfur, and very different compound, lanthanum hydride, which is very similar to metallic hydrogen, and here also where hydrogen atoms form covalent bonding, weak covalent bonding. And what is interesting also, of course, future predictions and expectations. So first of all, now calculations and experiments shift to lower pressures, so more available pressures and ultimate ambient pressure. So here are some interesting examples when this compound, which can be considered as tetrahedron of boron, and here tetrahedron of methane, and here xylane. And these basically molecular systems, when they doped with magnesium or potassium and so on, they also showed pretty high critical temperature, and sometimes at very low pressures, like metastable to 3 GPa. And just a few words about ambient pressure superconductors. Of course, ultimate case in this case, it's difficult to expect with hydride, because with hydride you see it could be, but still hydrogen is have strong propensity to make molecules at low ambient pressures, so it's difficult. But on the other hand, all this physics, simple physics, shows that in fact, in BCS theory, very important parameter is phonon spectrum, the Debye temperature, for instance. So the Debye temperature for hydrides is very close to diamond. So it's possible to expect high temperature superconductivity in diamonds. Some calculations shows already 75 kelvins, and experiments show 56 Kelvin. It's already very good development. And not only quite complex class right system, also recently predicted to be 75 Kelvin. So many thanks for your attention, many thanks for my group and collaborator, and for you again for your attention. Unfortunately, I don't see you, but I hope I see, to listen to your questions.
Thank you. So maybe there is time for quick question. We are off schedule, so are there any questions from home or from the public here? If not, we can thank the speaker again and then move to the next talk. Next talk is from Ryotaro Arita, Tokyo University. So please, you can unshare your screen and Ryotaro can share his screen.
Okay.
I beg all of the speakers to stay within 20 minutes because otherwise we go off schedule dramatically. Please, I beg you. Thank you.
Okay. Can you hear me? Okay. Okay. Thank you very much. And first of all, I would like to thank the organizers, especially Antonio, for giving me a very nice opportunity to present our recent study on hydride, lanthanum H10. Especially in this talk, I'm going to tell you about its pressure temperature phase diagram studied by path integral molecular dynamics simulations. So my name is Ryotaro Arita from Research Center for Advanced Science and Technology, University of Tokyo, and the Riken Center for Emergent Matter Science. And this work was done in collaboration with many people from University of Tokyo, Rome, Riken or Okayama, Saitama, Tohoku universities, but the main player is Yuta Watanabe and Jiajun Wan, graduate students of my group, and Jose Flores Rivas from Rome. And these are references of my talk today, and this is our recent review paper. Okay. So, as was nicely reviewed by Professor Eremets in the previous talk, a few years ago, high TC superconductivity was discovered in lanthanum H10. So this is a paper from the group of Professor Eremets and Professor Emre. And so they reported that maximum TC is about 250 Kelvin. But theoretically and experimentally, it is not yet fully understood in the phase diagram in the plane of temperature and pressure, in which region this high temperature superconductivity appears. So this is the question problem which I'm going to discuss in this talk. Okay, and regarding the convex hull of lanthanum H10, several groups calculated the enthalpy as a function of hydrogen content. So here I'm showing the result of our paper in 2020. And so in this plot, so the enthalpy is calculated by the standard DFT calculation. So the effect of final temperature is neglected, and also we did not include the effect of zero-point motion of hydrogen atoms. And then in this plot, we have one problem, namely, so for example, if we look at the results of 100 gigapascal, and so this is the result of lanthanum H10. And we see that the point of lanthanum H10 reside higher than the line connecting lanthanum H7 and lanthanum H11. That means lanthanum H10 is not thermodynamically stable in that it will decompose into lanthanum H7 and lanthanum 11. And the situation is very similar to the situation of the 150 gigapascal is similar to that of 100 gigapascal, namely the point of lanthanum H10 is higher than line connecting lanthanum H5 and lanthanum H11. So at 200 gigapascal, the lanthanum H10 becomes thermodynamically stable, but this result is not consistent with experimental observation because high TC superconductivity in lanthanum H10 is observed at the pressure down to 130 gigapascal. And also the conventional DFT calculation has a problem, namely, even we focus on the lanthanum H10, and if we look at the crystal structure, and if we compare the enthalpy of the various crystal structures, we see that this very symmetric structure, FM3 by M, does not have the lowest enthalpy, even above the pressure above the 200 gigapascal. So namely, the structure, a distorted structure has lower enthalpy. And this is not good for superconductivity because if we calculate the density of states of distorted crystal structure and symmetric crystal structure, we see that in the case of symmetric crystal structure, FM3 by M, so there is a sharp peak in the density of states due to the Van Hove singularity. But when the crystal structure is distorted, then this peak disappears. So density of states at the Fermi level becomes very small. And so this is not good for phonon-mediated superconductivity. So we can expect high TC only for this symmetric structure, but this structure is stable only at pressure higher than 300 gigapascal. This is the second problem. And indeed, if we calculate phonon dispersions for this symmetric lanthanum H10, we see that so both in the case of 150 and 200 gigapascal. So if we employ the harmonic approximation in the phonon calculation, we see many imaginary modes. That means So Ransom H10 is not only thermodynamically unstable, but also dynamically unstable. And to overcome this problem, we recently performed the calculation taking account of the phonon anharmonicity and quantum effect zero-point motions in the framework of self-consistent phonon theory, SCPT, which is nicely reviewed by Tadano and Tsuneyuki in this paper, Journal of Physical Society of Japan, 2018. So in this framework, so we start with the anharmonic Hamiltonian. So this is the harmonic Hamiltonian, and these are this is a harmonic Hamiltonian, and these are higher order terms, harmonic terms. And to study this original Hamiltonian, so we introduce fictitious Hamiltonian, harmonic Hamiltonian. So this is the addressed phonon frequencies, including the effects of harmonicity. And for the free energy for this fictitious system and original system, so there is a Gibbs-Bogoliubov inequality. So we can think about minimizing the left-hand side, F prime. And by minimizing this F prime, we can determine the value of addressed, the dispersion of addressed phonons. And so this can be done analytically if we forget about the contribution of higher order terms, the terms higher than the fifth order. And by taking derivatives of F prime with respect to this large omega q, we can derive these equations. And by solving numerically these equations self-consistently, we can determine the dispersion of addressed phonons. And we can also think about formulate stochastic implementation of this SCPT as was proposed by Area in 2014. And so we confirmed that these two approaches gives almost identical results for Ransom H10. So let's show the results. So this is the results of harmonic approximation. And as I have mentioned, there are many imaginary modes. But if we consider the effect of anharmonicity, and if we plot the dispersion of addressed phonons, including effect of anharmonicity, then we see that they are all positive definite, so well-defined modes. So by considering harmonicity, we can say that so Ransom H10 is dynamically stable. And also, so now we have the well-defined phonon frequency, so we can consider the effect of zero-point motions. And by including the quantum effects on the harmonic effect, if we plot the convex Hall again, then we see that Ransom H10 becomes thermodynamically stable. So we can say that by including the effect of zero-point motions of hydrogen atoms, so this symmetric structure, which is good for phonon-mediated superconductivity, becomes thermodynamically or dynamically stable. So this is a calculation for zero temperature. But it is also interesting to see the effect of finite temperature. And to investigate the effect of quantum effect and both the temperature effect and the quantum effect, we performed the calculations based on the path integral molecular dynamics. So PIMD. So in the calculation PIMD, we start with the Hamiltonian for n particle systems and consider the partition functions and do a Suzuki-Torotta decompositions. And here PB, so we introduce the PB copies of each atoms and perform a molecular dynamics simulations. And this PB represents how quantum the problem is. And in the limit of a very large PB, the mapping converges to give the exact quantum mechanical result. And so we perform this PIMD calculation for Ransom H10. And so this is a plot of Gibbs free energy as a function of PB. B means beats. And so we see that when the PB is larger than 20, then the result is almost converged. So in the present calculation, we employed the PB equals 36. And the PB, on the other hand, PB equal 1 corresponds to the calculation of classical MD, which doesn't consider the 0-point motion. Only the effect of finite temperature is considered. And but yeah, and the calculation for PB equals 36 here. Both finite temperature and the quantum effect are considered. And in this MD simulations, we look at the crystal structure and we examine whether the crystal structure is distorted or not. So this is the crystal structure of FM3 by M, and this is the crystal structure of C2, so it's distorted. And we see the effect of the temperature and the quantum effect on the symmetry of the crystal structure. Okay, so let us move on to the results. So first, I'm showing the results of classical conventional MD, molecular dynamics. And I'm showing a very representative results. One is the results for distorted crystal structure, the results for 125 gigapascal and 200 Kelvin. And the other is a result for symmetric FM3 by M structure. The result for 150 gigapascal and 300 Kelvin. And this is the X-ray diffraction pattern. And so we see that in the case of this 125 gigapascal and 200 Kelvin, we have several satellite peaks. But when the system is symmetric, then these satellite peaks disappears and the pattern becomes very simple, just 2 peaks. And so we perform this calculation for these 5 points. And we found that at 300 Kelvin, the crystal structure becomes symmetric, and the symmetry space group is FM3 by M. And on the other hand, other 3 points, there are many satellite peaks. So at these points, the symmetry is lower than the FM3 by M, namely the cage of hydrogen is distorted. So there is a phase boundary between these points. And so this result suggests that at 300 Kelvin, the finite temperature effect can stabilize this FM3 by M structure. So this is the effect of finite temperature. And then we move to the results of PIMD. So we include the effect of quantum effect. And then, so in contrast with the results of classical MD, we see that at these points, the crystal structure becomes FM3 by M. So namely, at 200 Kelvin, because of the synergy effect of finite temperature and the quantum effect, the most stable structure becomes FM3 by M. So the phase boundary becomes here. And this is XRD pattern. And we see that in all cases, there are no satellite peaks. But we also performed space group analysis using some package which we call the PyMatGen. And then we found that in the case of 100 gigapascal and 300 Kelvin, so this parameter this parameter is the threshold, and which measures the deviation from the ideal FM3 bus M structure. And if this threshold becomes smaller, then the PyMatGen detects the small deviation from FM3 by M structure. And we see that in the case of 100 gigapascal, 300 Kelvin, the structure is slightly distorted. So we can say that this point is close to the boundary between the FM3 by M and lower symmetry structures like C2. So these results suggest that so at 200 Kelvin, finite temperature effect alone cannot stabilize FM3 by M, but as a synergy effect with the quantum effect, the FM3 bus M structure becomes stable. And this is actually consistent with experimental observation, I think. Okay, so let us finally briefly discuss whether we can calculate TC as high as 250 Kelvin from first principles. And concerning the ab initio calculation of transition temperatures from mediated superconductivity, there is one problem. Namely, it has been very difficult to treat the retardation effect in the ab initio calculation. So when we calculate the transition temperature of phonon-mediated superconductivity, we solve this the so-called Eliashberg linearized Eliashberg equations. So this is delta is a gap equation, and this V is a phonon-mediated attractive interaction, and VC is a screen-Coulomb repulsive interaction. G is a Green's function. And if we look at the omega dependence of this attractive interaction and the repulsive interaction, there is a big difference. Namely, the phono-attractive interaction is finite only for low energy region. The energy phonon, the window determined by the energy scales of phonons. But on the other hand, the screen-Coulomb repulsion, it is finite up to the energy scales of Fermi energy, in this case 20 or 30 electron volt. So much larger. And so numerically, it's a very hard task to cover this large energy window. So we have to introduce many numbers of mass bar frequencies. That makes the numericals very expensive. So usually we follow the argument by Moreo and Anderson, and we derive an effective equations. And then, so here we introduce a Coulomb pseudo potential. So the screen-Coulomb interaction is renormalized, and so mu becomes mu star. But this the ab initio estimate of this renormalization factor is a big challenge, and in fact, it usually introduces substantial uncertainty. And so in the case of hydrides, this becomes as large as 30 Kelvin. So that makes that is the problems in the initial calculation of DC of hydrides. But recently, we developed a very efficient method to solve this Eliashberg equation using intermediate representation of the Green's function. This is based on the singular value decomposition of the Green's function. And if we use this basis, then we can solve this Eliashberg equation, and the numerical cost becomes 30 or 40 times cheaper. And then, so if we solve the Eliashberg equation, then we can obtain a TC as high as 250 Kelvin. And this is quite consistent with experiment. Okay, so let me conclude my talk. So in this study, so we discussed the crystal structure of lanthanum H10 using path integral molecular dynamics. And we discussed the effect of quantum effect and finite temperature. And we have shown that both effects are important to stabilize the symmetric FM3/M structure at 125 gigapascal and 200 Kelvin. And we also have shown that transition temperature of hydrides can be calculated without introducing any adjustable or empirical parameters. And estimated DC is quite agree well with the experiment. Okay, thank you very much for your attention.
Thank you. So maybe there is time for one or two quick questions, if any. Antonio, please.
I'm sorry, I cannot hear you.
Maybe, Antonio, you should come here by the microphone. Come here.
There is a very important, in cuprates, there is a very important aspect in the electron-phonon interaction due to the fact that you have a mixing between tilting modes and stretching modes, the high energy phonons and the low energy phonons. Did you consider that is mixing?
In this calculation?
Yeah.
What do you mean mixing? Mixing means phonon-phonon interaction? Maybe I'm missing a point. Sorry, I cannot hear you.
High energy optical phonons are very flat, and then you have a stretching modes to 1,500 centimeter. And on the contrary, you have a very low tilting modes at 500 centimeters, very strong softening at the critical point in the K space. So in cuprates, the mixing between the two is very important. It takes 30 years of work to understand.
Mixing between, in the case of hydrides, mixing between this mode and this mode? What did...
So I guess that our time is over, so we can thank the speaker
sorry.
again and
I'm
move to the
sorry.
next speaker. So Ryotaro, please unshare your screen, and the next speaker is Hideo Aoki from Tokyo University. please, you can share your screen. And please try to stay within 20 minutes for your presentation. Thank you. We can see your presentation, but we cannot hear you.
Just a second.
Please, could you check your microphone?
Okay. Can you hear me?
Okay, now we can hear you. Thank you.
Okay. Okay. So I'd like to first thank Antonio. It's always a pleasure to attend this series of conference. So today I'm going to talk about engineering topological superconductivity in and out of equilibrium. Okay. Okay, so this is the plan of my talk. So I'll start with superconductivity in equilibrium from repulsive interactions. So I'll focus on incipient band superconductivity, and examples are new Q plate and flat band superconductivity. Then I move on to the non-equilibrium, namely I remind you of the Floquet topological insulator for dispersive and flat bands. Then finally, I move on to the Floquet topological D plus ID topological superconductivity. Okay, so my keywords are incipient band superconductivity and Floquet engineered superconductivity. Here, my definition of topological superconductivity is first, time reversal broken superconductivity as in Floquet D plus ID. And I also include superconductivity accompanied by topological bands, as in flat band superconductivity. Okay, so let's start with this. Let me start with mentioning an incipient band can favor superconductivity even for Q plates. Okay, so we know good Q plates are one band. My question here is, it is always the case. And I'm going to show that even for Q plate, an incipient band can favor superconductivity. Okay, this has to do with a newly discovered high TC in single layer barium-2 copper O3 plus delta, with delta around 4.2, as discovered experimentally in this fabrication. So this is the usual barium-2 copper O4 with tetrahedra. But when you oxygen depletion, then we've got this barium-2 copper O4 minus 1 or 3 plus delta with copper plane. And the point is, there are a lot of in-plane oxygen vacancies. And namely, this system is heavily hole-doped and heavily oxygen deficient copper plane. Still, we've got TC of 73 Kelvin. And there are several theoretical proposals for the electron structure, but we noticed that experimentally a tetragonal structure is suggested. So this is our model for the mother undoped compound barium-2 copper O3. And so this is a top view of our model for the copper plane. Purple balls are copper, red ones are in-plane oxygen, and pink is apex oxygen. And since this copper atom is chemically inert, we are left with this one. And this is the bird-eye view of our structure with tetrahedra and copper O3 squares. Okay. This is the band structure in 6-orbital model. And the essential bands are just two arising from the x squared minus y squared orbital and the z squared orbital. And this is the TC dome against band filling. So the pairing is intra-orbital S and inter-orbital D wave. But we have shifted the band offset like this to look for the optimum situation. And we found that the optimum situation comes from an incipient band situation, even in this case. So the incipient bands, namely bands close to but away from Fermi energy, is important even in this case. And incipient bands are usually discussed in the context of ion-based superconductivity. For instance, even when your whole band is below the Fermi energy, we still have this kind of pair scattering, and we end up with incipient S plus minus wave pairing. But originally, the concept of incipient bands was introduced by Kazuhiko Kuroki many years ago in a more general context like this. Okay, so let's look at the superconductivity in incipient flat bands. That can occur both in two-band system like this, or one-band system with flat portions like this. And in both cases, pair scattering occurs between the flat and dispersive parts of the dispersion, which enhances TC. Okay, so let's first look at a two-band case. This is the simplest possible two-band flat band model. This is the diamond chain, three-band system. This is flat, and this is a relevant pair scattering process between dispersive and flat bands. This is a real space, and this is a relevant pairing. And we want to move a pair. But you may think that, you might have difficulty because in moving the pair, two electrons have to come to this side, which should cause a very large on-site repulsion. But no, you don't have to worry about that, because since this is a flat band, we got non-orthogonalizable linear functions with overlap like this. So each pair can quite easily move across adjacent unit cells. Okay, and indeed, for this incipient flat band superconductivity, superconducting phase sits just next to a topological phase, topological insulator phase. Okay. How about the one band case with flat portions? For that, Shalavis Hayat and ourselves considered T prime square lattice with second neighbor hopping T prime around minus 0.5 T. So this is a kind of frustrated system, which causes this kind of flat portion in the dispersion. This is a relevant pair scattering processes. So electrons are packed into the flat part, which can produce interesting things, as in this case. Okay, this is a TC dome. For the system, actually, we have a double dome. Why is that? Because on the right, we got the usual D-wave pairing. On the left, we got something more exotic with a lot of nodal lines. Each pair is unusually extended in real space. Okay, so why does this occur in frustrated T prime model? I think a hint comes from the following. In this paper, they talked about half-field Hubbard model, and they did 1/U expansion up to the third order. And the effective Hamiltonian is usual Heisenberg term plus four-side ring exchange terms. And they show that inclusion of T prime makes it even more complicated. So my guess is ring exchange interactions may be enhanced in flat band systems. Okay. Another observation I can make is usually superconductivity from electron-electron repulsion works much better in two-dimensional layer-type materials than in three-dimensional materials. These orange regions mark large spin fluctuation needed, pairing interaction, and the volume fraction is much greater for the two-dimensional case for this kind of pair scattering, as shown by the previous speaker and also by Gil Gonzalez. Okay. And I can point out that flat band superconductivity has a totally different dimensional dependence. In one-dimensional flat band system, the final gap function is a kind of S plus minus pairing between flat band and dispersing band, which occurs rather uniformly in the Boolean zone. In 2D partial flat band, then we again have broad spin structure in phase space, and gap function again has a large amplitude in a very large area. So I think this is a specialty of the flat band superconductivity, namely beyond the nesting physics. So a three-dimensional system in this case should be as good as two-dimensional systems, evading Arita's and Gonzalez's theorem. Another comment I can make is group velocity vanishes at a point, namely one for singularity, and many authors proposed topological superconductivity such as D plus ID pairing. For instance, for the honeycomb lattice with Fermi energy close to 1/4 energy, or twisted by the Guehne. And in this context, maybe this is transition discussed by Antonio for many years may be relevant because they are talking about some singular point like this. Okay, but group velocity vanishes in finite areas in flat bands. So I think the effect should be much stronger. And we can even go from square lattice to triangular lattice. And actually we found something interesting, namely electron nematicity enhanced superconductivity. But this is a different story. Okay. So in the remaining minutes, let's talk about a non-equilibrium. So let me start from the locate topological insulator proposed by Takashi, Oka, and myself several years ago. This is a honeycomb lattice illuminated by circularly polarized light in zero magnetic field, and we can show that we can induce DC Hall current. So we have a quantum anomalous Hall effect because we are opening topological gap dynamically, and experimental detection of the float-plate topological insulator in graphene was achieved 2020 by James McIver in Hamburg. So I may point out that it took a decade from the theoretical prediction to the experimental detection. Okay. Locate topological insulator in flat bands occurs. Locate topological insulator occurs in flat bands as well. For instance, in this leap model. And if you switch on the Hubbard interaction, we can have non-equilibrium many-body phase diagram. There are many quantum phases because by shining the light, we have 2 photon assisted complex hopping and 1, 2, 3 photon assisted complex hopping. And they have different functional form against laser intensity. And every time we have this kind of crossing, we have a phase boundary. Okay, so let me finally come to the Floquet topological D plus ID superconductivity. Okay, time reversal broken superconductivity is usually considered for coexisting pairing symmetries in equilibrium. For instance, as proposed for ion-based superconductivity, if we have two different pairing symmetries, then there's a chance to have a T-broken superconductivity in between. Okay, but here I'm going to propose an entirely different dynamical way, which is a Floquet physics. So this is the perspective of the Floquet physics. So if you start from the one-body problem for the Dirac field, then we have this Floquet topology translator. If you move over to strongly correlated systems, then we can show that if you shine a Mott insulator with circularly polarized light, we induce chiral speed coupling like this. And this gives you a chiral spin states, as shown by Sota, Kitamura, and company. Today, I'm going to shine a circularly polarized light to a D-wave superconductor. And this induces chiral superpairing interaction, and we end up with D plus ID wave superconductivity. Okay. This is the Floquet topological dx squared minus y squared plus I dxy superconductivity. We start from a repulsive Hubbard model under circularly polarized light on a square like this. And we assume that Hubbard is much stronger than the Hawking energy T. In equilibrium, we know that we end up with TJ model as an effective Hamiltonian. But under circularly polarized light, we can extend this to Floquet physics. And this is a final effective Hamiltonian containing several terms, Floquet renormalized Hawking, photon-modified kinetic exchange, photon-induced correlated Hawking, and photon-induced chiral spin coupling. And this can apply to square like this. Why is that? Because if we start from the one-body problem for honeycomb lattice, this is a two photon-assisted process, 1 and 2, and the end result is a complex Hawking, giving a Holden's model. If you do the same calculation for the square lattice, then there are two paths going from here to here, red one and blue one, and we can show that these two cancel each other exactly. So that's why we require graphene or honeycomb for Floquet topology insulator. But if you move over to strongly correlated case, the situation is totally different because there's no cancellation and square lattice already accommodates a topological phase. So to look into that, we can start from the Floquet Hamiltonian in Bogoliubov-Dujan form, 2x2 matrix. And if you look at the matrix element, we can see that we have a dxy component proportional to sine kx, sine ky, involving two-step correlated Hawking, I just mentioned, and the chiral spin coupling I just mentioned. And then we end up with D plus ID. This is the color coding of the magnitude of the two-step correlated Hawking against laser field intensity, laser frequency, and the similar plot for the chiral spin coupling. And we can immediately see that there is a series of omega U resonances in which every time the ratio of omega and Hubbard U is simple fractions, then we have a resonance. Okay.
You should go, please, to your conclusion, if possible.
I'm going to conclude. So this is the gap function, its amplitude, phase, and we end up with this one. And parameters behave with some notable features. I'm not going into detail, but for two-step correlated Hawking, this is significant even in low frequency regime, which helps because the required electric field is proportional to omega. For the chiral spin coupling, this coupling diverges for up to omega U resonance. And T prime is also involved here. So for an optical electric field, IDXI component is I times 0.3t sine kx sine ky, which is remarkably significant as compared with the undriven dx squared minus here, which is 0.7 something. So I think this is realistic, even though the effect is force order in electric field. And this is the TC dome against laser intensity, against laser heating intensity and temperature, about the absolute value of the back function and imaginary part. The white dashed line is a T effective temperature in K Hamiltonian. So if you start from here and increase the laser field intensity, then we have a circularly polarized light induced superconductivity. And quench dynamics confirm this. I switch on the laser and look at the time evolution for this quench and for that quench. And in both cases, we confirm this TC dome. And you may have noticed that there's a funny oscillation. This is actually a Higgs oscillation, okay? As in the high TC plate. Bill Shimano and the company discovered Higgs mode in the D-wave superconductor. So, but the present topological superconductivity is intimately related to Higgs mode excitation. So an interesting possibility is topological superconductivity enhanced by resonantly exciting the Higgs. Okay, I'll skip this one. So when we talk about design for correlated systems, usually people talk about the material design, but we can move on to the design on time axis. In other words, design in 4 dimensions, the fourth dimension being time. And we can also show that the required intensity of the laser is within the experimental accomplishment. This is the point where James McIver used to detect blockade topological insulator in graphene. And the present proposal requires around here, which is more relaxed. Okay, so let me summarize. I talked about this, and these indeed have unique opportunities giving a prospect of quantum phases. And these are my collaborators. Thank you.
Thank you. Thank you very much.
In this short talk, I will remind a short story of the multi-gap superconductivity at the Fano-Feshbach pair transfer resonance and its application to high pressure hydride materials, showing that in order to get, for the theoretical point of view, the room temperature superconductivity, this is a very clear and founded roadmap. The sulfur hydrides have shown near to temperature superconductivity, as has been shown this morning, and has been interpreted in terms of conventional BCS theory. But we think that BCS theory predicts only low TC, and on the contrary, the multi-gap superconductivity is a clear physical paradigm to going beyond the one-band superconductivity that predict room temperature superconductivity in quantum mechanics. The paper has been published in Journal of Applied Physics in 2021, and you can find it in the literature. The breakthrough of ITC superconductivity started in 1965. We discovered it in heavy fermion niobium germanium materials, then cuprates, MgB2, and H3S and lanthanum H10. These are not the single elements. They are two binary, ternary, quaternary compounds, and complexity is going beyond the BCS theory for simple metals. The Cuprates depend not only on doping, but depend only on lattice parameter. And you have a huge dome in TC as function of the lattice parameter. Lattice parameter don't exist in the BCS theory because it's not, that is not for a, BCS theory is for a quasi-particle Fermi liquid. And if you plot TC not only on doping, but also on strain, means you do a phase diagram in temperature, doping, and pressure, and you have a dome. A dome is not predicted by BCS theory. The main point in the history was the point out of Elia Lipschitz in 1960 of a metal insulator transition for appearing of new Fermi surface. And they are determined by strain. What was demonstrated in 2000 is that when you are users of strain, you can have charge ordering, and there is a critical point where you can have paddles of stripes phase, and this stripes was called the phase superstripe phase. Google in 2008 demonstrated that the striped phase at the Lipschitz transition is actually made of a complex pattern of nanoscale phase separation. The idea of superstripes comes from a discovery that disorder was a strongly correlated disorder, was promoting quantum superconductivity, entanglement between condensates. So the conventional BCS theory started with the hypothesis of a single Fermi surface, consider attractive Cooper pair, and does not consider the possibility of charge density waves, spin density waves, polarons, and phase separation, which competed for superconductivity. On the contrary, if you consider a two Fermi surface and two with unconventional Cooper pair, where in one of the Fermi surfaces the phonon is like EF, then you have charge density waves, spin density waves, polaron, phase separation, which coexist with superconductivity. The story of the idea of this new scheme start from 1929, so 93 years ago, when Ettore Majorana in Rome presented his PhD thesis on resonant nuclear scattering. Fano continued this work in 1935 and then go on and shape resonance. Fano, so it's a 93 story. But what concerned us was the idea in 93 of that cuprate superconductor realization of a Fano resonance, and the theory of two-gap resonance superconductivity in superlattice of stripes was presented by Perali at the first 96 Stripes conference. So you see, it's a very long story. It's a beautiful story of quantum mechanics, but now we are realizing in this day how quantum mechanics is promising. So multi-gap superconductivity consider the case where you have two Fermi surface, and you have a shallow band with Bose-Einstein condensation near Beck's crossover, and the other one in the BCS regime. The simple schema of two-gap superconductivity that has been object also of discussion of the presentation of Aoki this morning was that you have a coexistence of a flat band and a very steep band. So you have pairs that are BCS pairs and nearly Beck BCS crossover pairs. The mixing between the two, according with the Fano resonance, is an exchange term that is not in BCS theory, is a contact interaction between the pairs that produce the enhancement of TC. So you have a very complex regime where you have not a BCS multi-gap superconductivity, but you have not a Beck BCS crossover BCS, but you have a Beck BCS crossover regime and the BCS and the Cooper pairs. And the Fano-Feshbach resonance between the two can produce with quantum mechanics ITC superconductivity. So you have this scenario where you have pairs in the shallow band that can be exchanged with pairs in the single band. Clearly, if you have not this one, you have only this one, you cannot have the exchange interaction. So the points that I want to discuss with you today is the fact that hydrogen H3S is essentially a network of quantum wires. You can have different networks of quantum dots, quantum wires, quantum wells. And in this case, you can realize material engineering of room temperature superconductors. This was pointed out in the patent in 93, and then in the paper by Perali that developed the thesis in 96, 98, for a particular case where you have a large Fermi surface and they have a shallow Fermi surface that make a transition from 2D to a closed Fermi surface to open Fermi surface. And then you have a Lipschitz transition around this point. This gives the dome. So the dome that we started discussing comes from quantum mechanics, three very well-founded quantum mechanics that is not appeared in BCS. In the BCS, changing the chemical potential, nothing changed. So you have a flat. And this morning, Arita shown like the BCS prediction in hydrides is a flat. So on the contrary, in the resonance, Fano resonance, you have a huge resonance. You have variation from 1 TC, 1 Kelvin to 100 Kelvin. So you have a huge variations of TC that is not at all predicted by BCS theory. Going now to the results of recent results. So we take a pressurized sulfuride, as you have understood this morning, is a very clear case of high temperature superconductivity with 200 Kelvin. And if you look to TC as function of pressure, you found a dome in a region between 120 and 170 Kelvin. You have a clear dome going from 120 Kelvin up to 200. If you take a pressure, you translate pressure in strain, you found a 6%. 6-8% strain variation is the same as in all cuprate family that I've shown you in the first. So we are in a region where we control by strain, we control the critical temperature. Remind that the TC strain don't exist. In the BCS theory, strain don't exist. So if you take H3S and deuterium, you get the real isotope effect goes from 1.1 up to 0.3, and then go back up to 0.4. This behavior of an isotope effect is not a 0.3. 0.3 is an average here. It's predicted by the two-gap superconductivity, but it's not predicted by BCS. In the BCS, you have just a constant. These are not theory, just data analysis of experimental data. The other point of BCS is that you have a very continuum density of states. On the contrary, you have seen lanthanum H10 and H3S show a peak in the density of states, very narrow peak in the density of states, indicating a flat band. On the contrary, the Fermi energy here, the 20 electron volts Fermi energy, is in the large Fermi surface. You have a large Fermi surface with the 20 electron volts Fermi energy, but you have a Fermi energy here in this narrow band that is order of 300 millieV, is exactly the same as the phonon energy. So if you take a strain, the density of states shift, and as it shifts, you cross the Lipschitz transition. So these are the Fermi surface of H3S. You have a multi-band superconductivity. But you have to go back to understand what is the origin of this narrow peak in the density of states. The narrow peak in the density of states originates from hydrogen. If you take the crystal of H3S, this morning you have seen also lanthanum H10 is very similar. You see this red, this is a crystal structure rotated. At some point you see wires of hydrogen. This green are wires of hydrogen. The distance between hydrogen distance in the wires is very short. It's like for metallic hydrogen. On the contrary, the distance between hydrogen wires and other wires is quite bigger. If you can eliminate in the crystal structure all the other atoms and to leave only the wires of hydrogen. The wires, metallic wire of hydrogen create a superlattice of metallic hydrogen, and in the 101 lattice plane, they produce a superlattice of hydrogen wire. This superlattice of hydrogen wires, you have a transition at the maximum density of states. You have a transition from the one-dimensional to two-dimensional phase. Looking to the Lipschitz transition at this point, we see that the density of states is a power law divergence with the exponent 6 and 5 in the two sides. This demonstrates that you are in the case of a supermetal that has been attracting a lot of interest. And you have a superconductivity in a supermetal in one portion of the material, in hydrogen wires, while on the others, you have a very large Fermi surface. We made a model calculations with a very simple superlattice of quantum wires of hydrogen. And you have the Van 't Hoff singularity is asymmetric with a dispersion of order 274 millieV, like in H3S. As you change the pressure, you see a variation of the peak, and you cross the Lipschitz transition. What is the key point to attack multi-gap superconductivity? The key point is the Van 't Hoff resonance, and the Van 't Hoff resonance is due to quantum mechanics. It's to quantum mechanics is overlap wave functions. In order to calculate this term, you have to get the real wave functions. You have to solve the Schrödinger equation, and Maria Vittoria Mazzotti will show also the Dirac equations that is much more complex, because in the Schrödinger equation you have not spin, but for this case we use the Schrödinger equation, and you have to calculate the exchange term. The exchange term is between band 1 and band 2. You have a lot of energy dependent and K dependent exchange term. And this can be solved also by quantum mechanics, not by type banding approximation. So the results show that you have a maximum TC when the two gaps have a large anisotropy. You have a gap in the hot spot, divided the gap in the BCS-like band, and you see that the maximum TC is reached when the ratio between the gap in the hot spot is much bigger than the gap in the larger Fermi surface, about a factor 3, 2.8, or different case, 3.8. So you have now a possibility to show TC at different positions of the density. You start to tune density. If you start tuning density, you change the chemical potential of your materials, and then you have this kind of domes. So you see here you have the energy, so it means the density modulation, but you can also change the coupling in the hot band. If you take a phonon of order of 200 or 250 milli-electron volt, and we consider that when you increase the electron phonon coupling, you have a softening of the phonon. In this case, you can change TC by changing electron phonon coupling in the hot spot. It's clear when you reach 0.5, you have a softening, and then TC drops, and you have a maximum TC at about electron phonon coupling around 0.3. So you have this kind of phase diagram, changing electron phonon coupling and changing chemical potential at fixed electron phonon coupling. So you get a dome. So a dome where you have here the density or chemical potential, and here you have electron phonon coupling. You can see you have a case where you have a 0, TC go down to 0 to 1 Kelvin, very low. Then you have increasing at the appearing of the Fermi surface, the shape resonance is give you 0 TC anti-resonance. Then if you increase coupling, the maximum you get about at the Lipschitz transition for charge density, for 2D, 1D transition, and coupling at 0.4. But then you can cross these domes in different ways. It's like in cuprates, you have a strain and doping. Strain will be the electron phonon coupling, and the Lipschitz parameter will be doping. Then you can make, you can cross these domes in different ways when you do experiments. If you apply external pressure, you can use, you can go through one pathways or another pathways. So the problem is, which is the pathways? This is another case with different parameter. You can see this temperature, critical temperature, you can reach nearly 300 Kelvin, with very reasonable parameters. So if you take a cut as function of density, for example, like this one, you get like in cuprates, this will be like standard. But now in the theory, you can go to 10 to minus 30 to the minus 3 Kelvin, and you see you have anti-resonance. You have Fano anti-resonance and Fano resonance. You have a huge superconducting dome. In the case of H3S, we considered many different pathways. And we propose the fact that you have a transition between hydrogen wires, 1D-like, and they interacting to the hydrogen wires. So in this 2D material, into the dimensionality, you have the peak in the density of states where you have a lattice instability and very strong coupling, give you the maximum TC. But also if you go here, you have a 0 TC. So we propose that in H3S, you go to, in 1D, you have a Lattinger liquid. So in H3S, you should follow this line. If you follow this line, it means you have to cross along these lines. And then you get TC as function of pressure. So because when you do you change the pressure, you change this kind of pathways. So this is a proposed calculation of the phase diagram. And clearly, when you apply pressure, you reach the maximum TC, and then you stop because you have a lattice instability and the crystal breakaway. So this makes a clear understanding of the superconducting dome in cuprates, in the all doped cuprates. We are clearly, I can develop the same ideas for the superlattice of layers and the superlattice of depending on interactions. But I think this is the key way, the key view to understand the dome in the cuprates and the dome in high pressure materials. So I thank you very much for your attention, and thank you for coming here.
Thank you very much, Antonio. So there is time for questions.
Okay. See. So we can discuss.
No, just a question. So you emphasized in your talk the role of strain of lattice. That was a starting point for a lot of discussion, also for superstripes.
Yes.
Starting point of all of our discussions. In your model, is it a simple way or a simple physical picture that strain enters? Is it always the same, or there are multiple ways of how strain really acts on superconductivity on the metallic system?
Okay, thank you for this question, because Baird was author of a fundamental paper in cuprates, showing, I think it was nearly the same time as us, showing that you have a critical tilting. If you consider the cuprates, you have two modes. You have tilting modes and stretching modes. And I focused on the stretching modes because Exap's technique was, and Baird focused on the tilting. And they have shown that increasing tilting you get a disappearing of TC. I remember very well. But we agree completely. So because the strain control both tilting and stretching. And what I told you, because the stretching it mix the high energy modes, and tilting it mix the low energy modes. So in the talk I gave today was a very simplified scheme where the strain is considered to be proportional to electron phonon coupling. So increasing strain, you have an anomaly in phase separation or anomaly in tilting modes, exactly what we discovered, I think, in '96. Will be a strong coupling. So strain means a strong coupling for me. So in order to be simplified, clearly, each case is different. But we are learning in this meeting, for example, that in magnesium diboride, you have a phonon softening for the high frequency mode. In the hydrogen-based superconductor, in the high pressure material seem to be mixing between stretching mode, quantum stretching mode of hydrogen, and the tilting mode. So I think, but this complexity of the perovskites. So the great idea of Alex was that complexity is based on the fact that the perovskites are very flexible materials. So the electron phonon coupling induces strong variation in the lattice parameters in the lattice structure. Thank you, man.
I think it's time to go to the next. This is going to be a bit of a different kind of talk. It's kind of what I spent my 2 years during COVID doing. And it's really questioning whether the hydrides are actually superconductors or not. So some of us are not completely convinced, and I'm going to show you why and sort of the path we took to get there. And if I have time, I'm going to talk about, this doesn't work very well, I'm going to talk about some theory as well. And it addresses a point that Arita raised about the Coulomb repulsion and the retardation effect, but I'm not sure I'm going to have time. Okay, so this is all done, I should emphasize, with Jorge Hirsch. So there he is. Everything here is in collaboration with him. So there's a brief outline. Like I said, I might not get to the, no, they're all 1, 1, 1. Might not get to the third one, but we'll see how we go. So all of you have seen all of this. Superconductivity is characterized by two things: zero resistance, but also the Meissner effect. Okay, and it's the Meissner effect that is a bit at issue here. And I'll just remind you that there's two effects here. There's exclusion, flux exclusion, and flux expulsion. Right? So flux expulsion is the Meissner effect, which means that when I show you this picture, I'm not showing you the Meissner effect, right? I have to show you a video. I have to show you a movie to show you the Meissner effect. You have to see this thing lift up, because that means flux expulsion as opposed to flux exclusion. So looking back again, you've seen this over the history. You're well aware of this. I just want to emphasize there are now many, many families of compounds, and I won't get into this aspect of things, but I, for one, and I'm very expert at Ellie-Ashberg theory, so the conventional theory of superconductivity. I'm beginning to question that, because we seem to have a zoo of families and a zoo of mechanisms that go along with it, and this seems to me a little bit, well, it's just not very good looking, which is why I added those question marks, if you notice, about the theory being well understood. And of course, in very recent times, way up there, we have the hydrides, and that's really what I want to talk about here. So, as I said, I'll just tell you how I got involved with this. It came with this announcement 2020, October 14th, in Nature, of room temperature superconductivity in this carbonaceous sulfur hydride. And as soon as we saw these resistance curves, they
they just didn't look right. They looked very sharp, and that drew our attention. And so we looked carefully at this paper. There are susceptibility measurements. I'm not going to talk about these. These are very problematic as well, but that's another story, and I'm not going to focus on that today. And over here, they applied a magnetic field and saw the TC lower. And this has been done for many of the hydrides. And this, in my opinion, is the strongest evidence that these are actually superconductors. Isotope effect is nice, but it's not the be-all and end-all. This is the strongest evidence. When you look closely at the resistance curves, for example, this is in the carbonaceous sulfur hydride, then you look down here at the figure caption, and this is in the extended data, so it's not in the main text of the paper. You'll notice that they had a quasi 4-point electric resistance measurement, and in fact, actually, one of the leads failed during this measurement, and that's how they explain, you know, the fact that the resistance isn't zero here. Well, we need to do better than that and actually make sure about this zero resistance. We're always measuring resistance. The ohms is a huge unit here. Resistivity is tougher to get at because the sample size is not generally well known. So we ended up writing a comment on this. It's actually submitted 6 days after the paper in Nature appeared, pointing these deficiencies out, pointing, you know, if you look at conventional superconductors, yeah, this is actually addressing the broadening of this transition, in particular as a magnetic field is applied. So we're just used to this idea that these curves tend to broaden the higher the field, and that wasn't present here at all. So there's another example, and so for example, if you plot that the width of the transition versus applied field for these various compounds and compare it to carbonaceous sulfur hydride, you see a stark contrast. So there seems to be something wrong here. And we're not the only ones who've noticed this. Dogan and Cohen also wrote a comment that ended up getting published in Physica C, and Mao and co-workers also commented on this in their paper. And I should add, I'm not, Eremets didn't mention it in his talk this morning, but that group has apparently spent 6 months trying to reproduce this result experimentally and have been unable to do so. So I would say this room temperature superconductor at least is under question. And then there's just a summary of some of the things I talked about. Now, I also want to examine the older hydrides starting in 2015. We heard about it all this morning, and it looked like a very solid story, but I want to show some things here that still are a little bit bothersome. The first thing is the Meissner effect. Okay, and here are the curves you saw this morning, and in particular, I want to highlight this one that shows magnetization versus temperature. And again, I want to make sure everybody understands that it's the field-cooled curve that is the Meissner effect. Nothing, absolutely nothing happens at TC. Okay, and that's not terribly unusual, especially for very strongly type 2 materials because of flux pinning and flux trapping. So it's not the be-all and end-all, but I just want to highlight that's the Meissner effect. So there's no Meissner effect shown here. They've done zero field cooled, applied a field, so there's clearly flux exclusion, but there hasn't been flux expulsion demonstrated here. And so we wrote a number of papers, and this is one of them, saying that, okay, strongly type 2 superconductors sometimes can trap flux, but there's an experiment. If you look at the Coop rates, Bednorz and Mueller published this paper in 1986, possible superconductivity, and then within months, they had another paper which illustrated the persistent currents from trapped flux. Okay, so this is very important to demonstrate so that we have confidence that this is a superconductor. There was a more recent follow-up paper to improve these magnetization measurements This has now been published, actually, and the title has changed. So a referee, which was not either me or Hirsch, also noticed that they should not have Meissner effect in the title, so that's been removed. But it's now in, I forget, Nature Communications, I believe. And they showed some improved data. I think you saw this morning. And you also saw this morning, except it wasn't emphasized. This is again, so again, the red here is field cooled. So there's no Meissner effect, no flux expulsion. The blue is zero field cooled, so there's definitely flux exclusion. But the reference for this is the material in the coolant before they laser heat. They need to laser heat to produce this actual compound. This is junk. Okay, that's neither here nor there. Actually, it's not completely junk because if you lower the temperature down to 17 Kelvin, you discover sulfur superconducting. So the sulfur actually superconducts under high pressure at around 17 Kelvin, and they've done that experiment, and so has another group. But up at these temperatures, this is basically complete junk. Why is there this difference that coincidentally, happens at this magical 200-degree critical temperature? We've asked them that, and the first answer was there might be some superconductivity in there. The second answer we heard just last week was that this is actually up at 230, so it doesn't matter because it's not at 200. But there's some characteristic temperature here that has nothing to do with the superconductor and happens to be at a temperature that's very close to the critical temperature. So this is a problem. There's something there in the apparatus that's, this is basically an empty cell. It's not empty, it's got the ingredients, but this is not a superconducting material. So to me, this is a problem that remains. As far as evidence for trapped flux goes, when I prepared this talk, there was none, but there was a talk last week by Minkoff, a collaborator with Eremets, and you saw some of these results in his talk, but nothing's been published or even posted, so I will leave that as work in progress. And this experiment for trapped flux, by the way, the one we envisioned and the one we suggested in this paper is that you should apply a field and then cool it, and then presumably the flux is trapped, and then you'll get persistent currents. For some reason, the Eremets group decided primarily to do zero field cooled flux, trapped flux experiments. But again, it's not much point in me commenting because there's no preprint yet. Okay, there's another set of measurements I want to also comment on. This was very difficult for me because Carbot is my former PhD supervisor. Tom Timisk is a very good friend, and so is Elizabeth Nicol. But this paper appeared shortly, or 2017, claiming to have spectroscopic evidence of superconductivity, if you read the text, and of a new energy scale. And I just want to emphasize that we don't agree. And I also want to acknowledge Tom for sharing all the raw data with us, so we could look at this very carefully. This is the data they published, and this is the reflectance ratio. So the fact that it's higher below TC, well, both are below TC, but the fact that it's higher as you go lower in temperature, so from red to blue, is what they claim is a sign of superconductivity. And it is. But when you look at their raw data, which is shown here, this is a figure from the comment we've written. So if you look right here at this reflectance ratio, then there's the low temperature one, the blue. There's the high temperature one. It's precisely this region that gets expanded in in the figure that they show, and you see that they're reversed. Okay, there's the raw data, and now they're reversed. They're reversed because a correction has been applied because of ice formation on the sample. Well, that might be all well and good, but if all of a sudden, you know, you haven't just made a correction, you've qualitatively reversed from lower to higher, from blue to red, to higher to lower by this correction. So it's unfortunate that they had ice there, but I don't think this constitutes very strong evidence. And as far as the mechanism is concerned, I think I'm going to skip this because there isn't that much time. I want to talk quickly about the theory. And here I'm going to I'll skip the BCS because you all know about BCS theory and go right to Eli-Ashberg. We heard a little bit about this from Arita, and the point I want to emphasize here is the retardation effect. So many people don't realize that in reality, the interaction between two electrons is repulsive. Electrons repel one another. We all learned that in elementary school, and it's still true. What is also true and more subtle is that the repulsion is slightly less at lower frequencies. So the frequency is just the Fourier transform of time, and so this is related to this retardation effect that Arita mentioned. And we do this scaling that was suggested by these guys way back, and then it looks like this. It looks like there's an attractive potential down there, and so on. You don't have to do this scaling. You can solve the equations in their original form like this. And the physics of that is very clear. It's this retardation effect. One electron polarizes the ions, and this is just a cartoon. But it then takes off because it's traveling at the Fermi velocity, and now that second electron gets attracted because the ions are still displaced, and so there's a net positive region of charge, and these two electrons never have to be in the same place at the same time. So that retardation is key in Eli-Ashberg theory. And just, you know, you probably heard this at least, well, this morning we heard about it. There's basically this nonlinear equation for the order parameter. Arita showed the equations on the imaginary axis. You can do imaginary or real. And the input parameters are this alpha squared f that they calculate from first principles. And he went into great detail about that, about avoiding negative modes. The key, though, the elephant in the room is the Coulomb repulsion. Eli-Ashberg theory does a pathetic job of treating the Coulomb repulsion. And I don't mean this renormalization from mu to mu star. I mean just treating U in the first place, the Coulomb repulsion. There's no correlation effects. It's just the bare repulsion that is being examined in Eli-Ashberg theory. Okay, so this we've been trained over and over again to write this down, to see this. Is it true? That's the question I'm addressing in this short study. And this is just a cartoon from Phil Anderson about the cuprate superconductors. He was trying to make fun of the mouse, which is the spin fluctuation here, and the elephant's actually J. So the U is actually represented by a mammoth, not an elephant. And so I give you the same cartoon where now the mouse is the electron-phonon interaction. That's a small interaction that causes some stuff for sure. But the big thing going on here is the direct Coulomb repulsion. So we're going to address, is this actually true? Because the scaling relation that Anderson and Morel and Tolmakov before him came up with is just a kind of a back of the envelope calculation. People looked for this in the 1980s, including me, in Monte Carlo simulations and could never see it. Okay, so not that it wasn't there, it was inconclusive. So, so I wanted to readdress this with a kind of the toy model of electron-phonon interactions, which is the Holstein model, and we put the Coulomb repulsion as a Hubbard U here. So this is not the full long-range interaction, but it's some some idea of what can go on. And the question is, can we get binding between two electrons because U becomes unimportant, as suggested by these guys? And so again, I've said all this and just emphasize, even if U goes to infinity here, then there's a cancellation and mu star becomes this simple denominator here, 1 over the log. And as Antonio pointed out, you know, W is not necessarily much bigger than omega E. So this reduction isn't going to be very much anyways. And these are just some numbers of what mu star becomes as this ratio grows for mu infinity or U infinity. So to do this, I wanted to do an exact diagonalization study. What I'm going to show you is kind of a Mickey Mouse version of what was done even better by these guys, but I won't go into the details, except to say it's exact. And also, I wanted to say briefly something about polaron physics, because that has an impact here. Polaron is just an electron by itself moving around carrying this lattice polarization. And that tends to make the effective mass, for example, much bigger. So here's some calculations in 1, 2, and 3 dimensions. These are for a single electron now, and these are all numerically exact, and they're all for the thermodynamic limit. And what you can see is that in 2 and 3 dimensions, at some point, down here's the coupling strength lambda, at some point, the effective mass shoots through the roof. And this is not a transition, it's just a very sharp crossover. I call this the world's sharpest smooth curve. So here are just the studies. This is just for 2 sites now, so it's not as compelling, I think, as the Boncha-Trugman work, but it's consistent with that work, and so here it is. So this is the binding of 2 electrons versus U. And the point of this graph is for lambda 0.5, depending on this frequency ratio, so this adiabaticity, you will get binding in this. I mean, you get binding down here, but this region is sort of not allowed for various reasons. So you get binding up to U over T of 2.3 or something. Okay, I want to emphasize that, up to 2.3, not up to infinity, as the Morel-Anderson renormalization graph seems to suggest. If we make lambda equals 1, then I'm also plotting here the number of phonons, which is like a proxy for the effective mass. I can't do the effective mass with just 2 sites. But when the number of phonons is above 3 or 4, which is way down here, then you know, then you're in strongly polaron type physics, and that's not really, you don't expect a superconductivity out of there. So in this case, larger U's are tolerated up to about 6 in units of T for lambda equals 1. But again, I want to emphasize the same qualitative result, that this idea of having U as large as you like, and it gets renormalized down to a mu star, simply doesn't pass the test when you actually treat it exactly on this limited size study. So that's the main theoretical message I wanted to get across. And now I will stop with a summary. And I've mentioned the doubts we have about the experiments, but on the theory side, I want to emphasize that retardation, the role of retardation, this is precisely what Arita was addressing as well, it's about time that we address this in a more systematic and rigorous way than what we've accepted for decades now, because of Morel and Anderson and Tolmakov. And polaron physics is another issue that I did not really address in this talk, but that's also there. Okay, I think I better stop here. Thank you.
Hypothesis as to what causes the reduction and then the resistance in these materials?
No. So yeah, so I don't know if you all heard that. It's about, I mean, we're as Gabe is pointing out, we're really putting our necks out because, you know, these are resistance plunges, right? Even if they don't go to zero, and the question is, what's causing that? And I don't have a hypothesis. The trouble is, Gabe, it could well be tied to something in the apparatus, given that result I showed you where even when there wasn't any superconducting sample, something seemed to be happening around that temperature. Now, they don't see things just at that temperature. They see it at other temperatures too. So, no, I don't have a good answer. And deep down, you know, I'm an Ellie Ashburg guy, so I kind of hope this is superconducting because it's kind of a realization of Ashcroft's dream. But that doesn't mean we can't be critical about what they've done and point out deficiencies in some of the measurements. And you know, the fact that when we talk to people, they keep telling us that the Meissner effect has been shown, and there's never been a measurement of the Meissner effect to date. Even the tinfoil experiment, which is a novel way of measuring magnetization, was flux exclusion. It was not flux expulsion. Yeah, so that's a good, so the question is how many groups are actually doing this, and this is one of the difficulties. It was really dominated by Eremets, and there was a, he wrote he and co-authors wrote in one article about the various independent investigations. There's a group in Japan, and that wasn't really independent. Eremets is a co-author on some of that. There's Hemley constitutes an independent group, so I guess that's a second group. And very recently there has been a third group, and I have it on. I actually added the slide, but it was after I gave the talk here, so it's not here, which is by Sven Friedman in Bristol. So they've done some very careful measurements, and by careful I mean I listened to a talk by him, and you can see, you know, the resistance is not zero, so they look at the delta R and things like that. But they've reproduced the H3S. So they've actually, that constitutes a completely independent verification for the resistance. They haven't done magnetization at all. So that, you know, that's good, strong support. I'm not denying that. But we'd like to see the Meissner effect.
So, Frank, what do you think if the system is inhomogeneous? So that maybe you have a fraction of superconductor in the system, but it does not percolate. In that case, you would explain the drop in the system, maybe not 20 kilo. Superconductivity does not percolate, and maybe the other.
Yeah, so question is about the possibility of inhomogeneity, and maybe that explains why you might get a resistance drop, but no Meissner effect. There's without question, and if you talk to the experimental people as well, there's a lot of inhomogeneity in this. So that was something Friedman was very careful about as well, and showing very, like, they can actually see optically, like, the inhomogeneities. So that's there, and it's, but again, if it's sort of filamentary superconductivity of some sort, that's not much of superconductivity. Yeah, yeah. So that's probably there, but the hope is that eventually they can resolve that. Right now it's being used to explain why in Friedman's experiments the resistance doesn't go completely to zero because of this patchiness, and then there are going to be regions in series rather than in parallel. There are going to be pieces that are conducting with resistance. So they're almost using it in reverse. So it's an open question, but it's definitely there, which is surprising a bit to me because you're squeezing the living daylights out of this thing, and you'd think you would, if you're going to homogenize, you know, you think about how inhomogeneous your car is, but when they put it into the wrecking center and crush it, it looks pretty homogeneous after that. Well, I would repeat it anyways. Okay. Zero. So the comment is that they see zero resistance. So, but zero resistance compared to you have to, if you can roughly translate it into a resistivity, how does it compare to copper? Okay, so the response was they can't really translate into a resistivity because the sample is pretty small. Okay. Yeah. Okay, thank you.
So first, I'd like to start my talk. So first of all, I'd like to thank organizers, so Antonio Bianconi, for inviting me to this very interesting conference and conference. So the title of my talk is here. So exotic density wave states and superconductivity in carbon metals and other strongly correlated metals. I'm Hiroshi Kontani in Nagoya University. So my collaborators are Dr. Rina Tazai and Professor Yoichi Yamakawa and Professor Seichiro Onari in Nagoya University. So I'd like to discuss unconventional orders. So that is that the order parameter is non-local and the order parameter has non-S symmetry, so no A1Z symmetry. Such unconventional orders occurs in iron-based superconductors and carbon metals, so vanadium-based carbon metal. And recently, nematic order is observed by twisted bilayer graphenes. We discussed these materials. So, the candidate of unconventional order is a D-wave bond order. This is a non-local because of this is a hopping modulation given by the symmetry breaking the self-energy. So once this happens, so system becomes nematic.
So this is a bond order. So observed in Kagome method. So it shows a sub-David shape. And recently, so the odd parity, when the hopping modulation is symmetry is odd parity, then the Hermitian condition requires that it should be imaginary. So imaginary hopping modulation delta t gives a current order. So this is expected to be realized in Kagome methods, and I would like to discuss the origin of this exotic order. So the open issue, I'd like to discuss open issues, the origin of these unconventional orders and interplay between different orders. So first, I'd like to shortly discuss the limit of mean field approximation. What the mean field approximation tells us. So, for example, we discussed in the case of multi-orbital Hubbard models shown here. So U is the interorbital Coulomb repulsion, and U prime is the intraorbital Coulomb repulsion, and U prime is the interorbital Coulomb repulsion. And usually, so U is larger than U prime. So in this case, we apply the mean field approximations. We obtain the STW stakes. It is a local order parameters like shown here. So we cannot obtain the orbital order observed in punktite. And in the case of, we also discussed the U plus V. V is the offsite Coulomb interaction, Hubbard model. This is in momentum space. The V offsite Coulomb interaction has this momentum dependence, and they can decompose the product of D-wave bond orders. So this is called a Fock term. So we can, if we apply the mean field theory, so we obtain the bond order. So however, the bond order, the required value of V is very large. So this is a difficulty. So we have to go beyond the mean field theory. So to understand these unconventional orders, we developed two theories. One theory is that to study the symmetry breaking in the normal state self-energy. So I start from the ground potential given by Leitner word, this function, and we input that symmetry breaking part in the self-energy. So sigma 0 is a A1 symmetry self-energy, and we input this symmetry breaking part. We call this is a form factor. And this is a stationary condition, thermal equivalent conditions of F. So this functional derivative gives that density wave equations here. So once we solve that these equations, we obtain the optimum, automatically obtain the optimum solutions that minimize the ground potential. So we studied this equations for the cuplets. So and by this is a irreducible 4-point vertex within the one loop approximation. And we have shown that this Azram-Flakin terms give rise to the orbitals in iron-based superconductors, and also bond order in Kagome metals. And we also find that the charge current order is given by this Markey-Thompson terms. And of course, it's a particle hole after the particle by inverting the green function, that direction this gives the gap equations. So this diagram gives the D-wave superconductivity. So the second theoretical method is that to optimization of find the unconventional orders by optimizing the general susceptibility. So and we use the functional Riemann group theory. So this is a susceptibility for the form factor F. F is a general form factor. So to find the realized form factor, we have to optimize this susceptibility. So that is So then the highest TC is so the form factor occurs at the highest TC. So this is a method of functionality. So for higher energies, we calculate the higher energy scattering part by constant RPM method because it is numerically accurate. So and back correction is not important for higher energy part. So and we solve the remuneration group theories by solving this functional RG equations, and we calculate the susceptibility with for the form factor F. F is shown by this green circle. And we can optimize the form factor by using variational method, using the more than 100 orthogonal bases. So the method is shown in this paper. So we studied this using this method for several simple Harvard models, and you obtain that essentially the same result as the functional density wave equation method. So this method we could confirm the Adams-Larkin type interference mechanism. So in the present talk, I study the analysis of this equation, density wave equation. In the present talk. So this is summarize the schematic picture of interference mechanism. So two paramagnon interferes here, and this interference gives rise to the unconventional charge density wave in the charge channel, and the momentum is Q equals Q prime. So recently I writing the debut paper in advanced physics, and maybe we post soon. So, and this is a mean field approximation phase diagram, and we considering this interference mechanism, so we obtain the new phase diagram. So some nematic or symmetric orders are intertwined, and these fluctuations give rise to exotic superconductivity. So this is our strategy. So now we move to discuss three topics. So nematicity iron selenide and treated by graphene, and we discussed the Kagome method. We discussed a bond order and superconductivity, and charge current order and nematicity. So we shortly discussed iron selenide. So this is a Fermi surface of iron selenide. So very small electron hole pockets exist. Under the when the nematic order sets in, so the Fermi surface is deformed to be C2 order. So the gamma point hole pocket is elongated along the ky axis, and the electron pocket around X point is elongated along the ky axis. So this is essentially obtained by interference mechanism on X and Y orbitals studied in this paper. So this is essentially the orbital polarization. However, so very recently, so this precise RPS measurement reveals that this pocket disappears below the structure transition temperature. So we revisited this problem by including the XI orbit, effect of XI orbital, because in this paper, so we neglect the correlation effect on XI orbital. So we consider that, so we revisit this problem, and we obtained successful result. So this is the result. So this is a previously, this is consistent with the previously obtained orbital polarization, XZ YZ orbital polarization. And so this is experimental sign change in the momentum space. So you can reproduce. And this is a new result. So we obtained the XI orbital exquisite bond order, D wave bond order, and this region makes the disappearance of electron pockets. So we found that all the T2G orbitals are important to stabilize the nematicity. And in our calculation, no fit parameters except for the value of U. And success of, I think that this is a success of other flashing type interference mechanism shown this here in iron-based superconductor. So we next move to the magic angle twisted by a graphene. So this is a more real space picture of more super lattice, and you see some more patterns. So so around the AB point, around the BA point, we have a one-year function, very long, large one-year wave function. So we can construct the tight binding models. So this is an experimental phase diagram. Now we talk about this nematic state here. So this is important because the superconducting phase appears next to the nematic state. So and it is of the nematic state is first reported by STM measurement, and recently so implane of the resistivity has been observed in the around this state. This is nearly the harmful singularity feeling. So the nematicity is treated by a graphene is an important unsolved problem. So we apply that theory, interference theory, to this problem. So so this is a theoretical model. So in the one-year orbitals on AB point is composed of 2 degrees of wave functions, and so there is various degrees of freedom. So in total, also this is a BA point. So in total, our Hamiltonian is 4 sublets, contains 4 sublets in the unit cell. So the Coulomb interaction is written by this very compact form. So made of a spin and pseudo spin. So pseudo spin is a various degrees of freedom. So and we can introduce this spin ballet operators, and our susceptibility. So there are many kinds of channels of susceptibility developed here in this model. So because of the approximately SU4 symmetries. So and this SU4 fluctuations interfere with each other and give rise to the XI nematic orders at Q equals 0. So and so it has a easy symmetries bond orders. So and we succeed in explaining the nematic orders at Q equals 0, and so based on by considering this interference mechanism. So this is the main part of my talk. So I discuss a Kagome superconductor. This is a schematic phase diagram, TP phase diagram. So in this material, so we observe the bond orders. So and as I explained, and we also the nematicity has been measured by below 35 Kelvin in this experiment. This is a so nematic susceptibility measurement. So nematic susceptibility increases below when the CDW sets in, and it stops when the nematic order occurs. And it is also the violation of chiral symmetry is reported by electric magnet chiral anisotropy measurements. In this study, so the structure transition temperature is around 35 Kelvin. So there are a lot of unsolved problems with the origin of bond order and the origin of nematicity. And so because of violation of chiral symmetry, a natural candidate of violation of chiral symmetry is the loop current. So, and also we want to understand the interplay between these phases. So, and also the mean field approximation is very difficult to understand the experiments. So this is a horizontal axis is the instability of these unconventional orders. So current a bond order, to represent the bond order, we need a large V over U, and the charge current order instability is always very small, and the absence of nematic phase and absence of superconductivity. So we have to go beyond the near field approximation, I think. So first, we'd like to understand the bond order. Based on this simple Hubbard model, simple means that only the on-site coulomb interaction is included in our study. So this is a structure of Kagame lattice, and this is a band structure, and this is the Fermi surface. So this is here the harmful singularity point is around this M point. So there are three harmful singularity points. So, and the importance of harmful singularity on the electric state has been pointed out by many experiments. So this is our obtained the density wave equation, eigenvalue for density wave equation, and we obtained a large eigenvalue, so large instability at Q equals Q1 or Q2 or Q3. So this is an experimental wave vector of CTW or bond orders. So, and we checked the form factor, and it is found that this instability is actually the bond order experimentally observed. So this is a schematical picture, so and this is a form factor in real space. So we obtained the modulation of hopping. This is a large delta t, and here is a small negative delta t. And the mechanisms are here. So interference among site A spin fluctuations and site B fluctuations. So in the near field approximation, the spin fluctuation developed inside the sublattice. So inter-sublattice component is spin fluctuation is very small. But this interference mechanism so gives rise to the interaction among B sublattice and A sublattice, and naturally gives the bond order along A and B, so like this one. So, and yes. So, and we next we discuss a triplet and superconducting phase because it is natural to expect the bond fluctuation should be important. So we obtained the anisotropic S wave gap here, and we obtained the P wave gap here. So there are two possibilities. And the recent experiment of Shibauchi group reveals that the impurity effect on TC like that. So it decreases fast in the first stage, and finally it saturates. So it is consistent with our S wave, anisotropic S wave superconducting case. So the gap becomes nearly isotropic, and the saturation of TC decreases. So this is our result. And very shortly, I discussed the current order and the nematic C in Kagame methods. So there are many experimental and on the time difference integrating and the nematic orders. So still controversial. So to understand that, so I think the theory is necessary. So we focus on the common bond order phase and the common bond order fluctuations. So this is still unpublished. I will post the archive soon. So this is obtained a current order and so given by the imaginary delta t. So and we find that the bond order fluctuations naturally give this charge current order. So this is I skipped the mechanism. So this is so odd parity particle condensations, and this radar diagram actually gives gives this particle condensations with odd parity. And we propose that the bond order fluctuation mediate the loop current like here and the experimental horizontal axis here. And we also discuss a possible bond order coexisting phase between bond order and current loop current order. So there are four possibilities. One of four is a has C6 symmetry. So here, so in this case, the film stuff is C6 symmetry. However, in this case, the film stuff deforms to be C2 symmetry. And this is in the DL argument tells that this is a stabilized. And we propose that here the nematic order, nematic coexist BO plus C order appears. So in our in this present predicted. So this is a summary. So we study the conventional phase transitions due to the beyond the mean phase approximation effect. So yeah, so there are two proposals for the Kagome method. So thank you very much. Pairing symmetry. I want to understand your question. Pairing symmetry.
The question was that in the bond-ordered case, what is the pairing symmetry? The superconducting state.
So we predicted two possibilities. One is an anisotropic S wave state, and another is P wave. So and yeah, so and the point is a bond fluctuation to be strong. So point so yeah, in the case of P wave, so time not if when the chiral P wave appears, so time should be broken. So yeah, so in the bond order fluctuation mechanism, so there are two possibilities, and of course, so there are also spin fluctuations, other fluctuations. So if we consider only the bond fluctuation, so we obtain the S wave state. But in the presence of finite spin fluctuation, P wave may win. And recent input effect studies on by Shibauchi group tells us that when the system is dirty, so it tends to be S wave. So and TC is saturated, and the gap becomes isotropic. So, but it's a difficult problem to find the symmetry, but the symmetry in very clean samples, we don't know. So there are, so our theory can explain several. Yeah. Yes. Yes. Yes.
Repeat the question, please.
So he asked about the isoselenide. So the bond order. So this is so this is the same as the so Eremets study. So and many people, experimental people also discuss that the bond order in the single orbitals, XY orbitals, only the XY orbitals. So because these bond orbital order and bond order have the same symmetry, so they can coexist, and it occurs at the same temperature. So, and our point is that we can naturally obtain the coexistence of bond order and orbital order based on that, without introducing fitting parameters. So, yes,
Repeat the question.
So the origin of the bond order, and yes, so and the bond order can couple the lattice, and but in our calculations we don't consider the phonon. So and it's pure electric origin. But as you said, so it's coupled to the phonon, lattice and phonons. Yeah. So we should consider the more realistic calculation.
Can I have one question?
Sure, where are you?
I'm online.
Yes, go ahead, please.
So you hear me. Okay, I have one question. There's some experiment showing that you can tune the gap structure by suppressing charge ordering. So there is experiment showing that in rubidium and KVS in the potassium compounds, you have a nodal pairing, but once you suppress CDW, you can have a nodeless pairing. Can you capture in your model the change in the symmetry by suppressing the charge density wave? So do you see that the CDW?
So excuse me, so which materials you are?
The 135, the Kagome superconductors. But
Kagome, okay.
Yeah. So do you really can capture whether CDW influences the superconducting gap structure or not?
So it is our next item. So we discussed yeah. So in this calculation, we don't consider the coexistence or existence of CDW.
Okay.
So,
okay.
Yeah. So we maybe discuss this area. So horizontal pressure. So but
experimental. Yeah, experimentally,
Yeah,
it seems that CDW can influence the gap structure.
Yes. So
you can make it nodal.
Yes, we have to consider. Yeah. So that is very important. A problem for us.
Thank you. Thank you.
Okay, I think we better stop the questions there. Thank you. The next speaker again.
Thank you. Thank you very much.
Okay, so the next speaker is Sergio Caprara, and the title is up there. And go ahead.
Thank you. I thank the organizers for inviting me. And my talk is devoted to charge density fluctuation and the strange metal behavior of cuprates. So this is a work in collaboration with theorists and experimentalists. My talk is devoted to the first of these two joint publications. And if you're eager to know more about that, you have to wait for Giovanni Mirarchi's talk later on this afternoon. So this is the zoo of superconductors that Frank has been talking about. And I'm talking about cuprates, which is this branch of the family tree of superconductors. Cuprates are anisotropic compounds, and transport is dominated by the copper-oxygen planes. A very, very schematic phase diagram for hole-doped and electron-doped cuprates is that the parent compound and the undoped parent compound is antiferromagnetic, and then as soon as you dope, either way, you destroy antiferromagnetism, and then you enter into this dome-shaped region where you have superconductivity. And optimum doping is here where the superconducting critical temperature is the highest. There is this pseudo-gap region. Maybe this is not a phase, it's just something, not a real phase. So the line that separates the pseudo-gap state from the normal metal, maybe it's only a crossover line. So, before I go into the matter, this is just the beginning of the story. This is a long story, an old story, and I like to quote William Shakespeare's Henry V, The Happy Few. Charge density waves were claimed to play a role in cuprates since quite long ago, and maybe the pioneering work by Antonio, and within our group, we were somehow pushing for the idea that charge density waves played a role in high TC cuprates. The evidence accumulated little by little, at the very beginning in the form of static stripes, but only in very specific compounds. This is lanthanum, strontium copper oxide, co-doped with neodymium. In that case, neodymium co-doping forces the formation of static stripes. Then in lanthanum and strontium copper oxide, there was evidence for less stripy order and some evidence of rotational symmetry breaking also in other families like YBCO. To make a long story short, more recent evidence for charge density wave in cuprates come from resonant X-ray scattering experiment, where you clearly now probe the charge susceptibility, and you clearly see this peak that develops at a given wave vector of the reciprocal space. And as you cool down, this peak gets narrower. So this is the charge density intensity, and once you enter into the superconducting phase, it is suppressed because apparently this charge density wave phase or whatever competes with superconductivity. Now we know that the landscape of cuprates is a very complex landscape. I want only to quote here Antonio's work on Nature Physics, where you have domains with charge density waves, or even a more complicated landscape where you have anti-correlation with oxygen distribution and charge density waves. Now, a breakthrough for us, for the theorists, came from this joint paper with the experimentalist in Milan, where besides the narrow peak that is usually attributed to incipient charge density wave, we could for the first time detect a second, much broader peak with a wave vector that is very close to the wave vector of charge density waves. We named the two peaks the narrow peak and the broad peak without much fantasy, and the corresponding excitation as charge density wave and charge density fluctuations. Again, this is just naming. Maybe they are the same object under maybe different conditions, so that in one case, the peak can become narrower, in the other case, it stays broad. The quasi-elastic peak, the integrated in frequency peak, is well described by a kind of Ornstein-Zernike form with a characteristic wave vector that is QC, and this QC is very similar for the two peaks. What changes from one peak to the other is the width of the peak, which is ruled by this parameter, which in field theory would be the mass of this excitation. So without much fantasy, we call it M. Now, if you go beyond the static and you go to the dynamics, these excitation live in a metallic background. So they are Landau damped. This is their dynamical propagator. So the static part is Ornstein-Zernike-like. And then you have dynamics. You have a Landau damping term. And then if you go at higher frequency, this is Matsubara frequency, but you get a very similar expression in real frequencies too. If you go to higher frequency, then you have an omega square, more propagating form of this kind of excitation above some characteristic energy scale, which we call omega bar. This mass is proportional to the inverse of the correlation length of the corresponding excitation. So the narrow peak has a rather longer characteristic spatial scale, and the broad peak has a much lower correlation scale. So the two names are given because charge density waves are, as long as we observe them above TC, not static, but dynamical objects. They are quite low energy, but they are dynamical. They are nearly critical in the sense that their mass, or whatever you call it, is proportional to the distance between the temperature and their ordering or would be ordering temperature, T, charge density wave, which is a function of doping. Charge density fluctuations stay broad all the time. their mass, or whatever you call it, is very weakly temperature and maybe also doping dependent. So this is the experimental phase diagram. We have dynamical charge density fluctuations that persist even at temperature much higher than the pseudo gap temperature T star. They are observed up to room temperature, and of course, if we would go beyond room temperature, we would observe them even above room temperature. Then the charge density wave appear in the form of dynamical object, rather two-dimensional, and we cannot access within our resonant X-ray scattering experiment, we cannot access the region below TC. That requires a strong magnetic field to suppress TC, which cannot apply in our setup. But if we extrapolate the coherence length, the correlation length of charge density wave, we find these 3 points where this correlation length would diverge, if we would access this region. And this nicely follows the static 3D charge density wave line that has been measured when suppressing TC under a strong magnetic field. So we believe that the charge density wave we measure up here are the same object that would become static 3D charge density wave at a temperature below the superconducting critical temperature. So the overall scenario as far as charge density waves are concerned is that they compete with superconductivity. Superconductivity wins, so the system prefers to become superconducting, but remnants of this static order are found above TC in the form of dynamical charge density wave. What is more interesting though is that besides this narrow peak related charge density wave, we find charge density fluctuations associated with the much broader peak all the time, even at high temperature. So this suggested a possible scenario for the strange metal puzzle in cuprates. What is this? So this is again a phase diagram where this is the antiferromagnet, this is the superconducting phase, this is the pseudo gap, whatever, state phase, whatever, this below T star. And then here you have the strange metal region. The strange metal region is a region where the resistivity, to say something, is a linear function of the temperature. Then, depending on whether you are underdoped, optimally doped, or overdoped, you have downwards or upwards deviation with respect to this linear behavior. And maybe the spot where this linear behavior is found down to nearly the superconducting critical temperature is around optimum doping. So what was maybe suggestive to us is that in the region where the strange metal phase, meaning the phase where you have a linear in temperature resistivity is found, charge density fluctuations are found. Charge density wave only occur here, maybe in the form of dynamical excitation below the pseudo gap temperature in a dome shape, below a dome-shaped curves that follows the dome-shaped curve for static charge density wave order that would occur here below TC. So the idea that we suggested is that the strange metal region of the phase diagram is the region where the charge density fluctuations are observed. Maybe this is not accidental, maybe. So another important property of charge density fluctuations is that they are sufficiently broad and have sufficiently small energy scales. So they are a good scatterer for the fermion quasi-particle, and they are rather isotropic along the Fermi surface, as I will show in a while, so that you don't incur into the hotspot problem that was pointed out by Lubina and Rice in this paper. When you have scattering dominated by a finite characteristic wave vector, of course you have spots at the Fermi surface where the scattering is strong,
This is the scattering rate along the Fermi surface mediated by charge density wave. So you see clearly the hot spots that are the places at the Fermi surface where the scattering is stronger. Now, the scattering, the Fermi liquid character of the quasi-particle is spoiled at the hot spots, but is maintained elsewhere at sufficiently low energy. So the argument goes like this. Fermi liquid quasi-particle would short-circuit the non-Fermi liquid quasi-particle at the hot spot, so that overall the transport in this scenario would be Fermi liquid-like. Now, as you see, contrary to charge density wave, the scattering of charge density fluctuations along the Fermi surface is pretty isotropic. There is no hot spots. They are broad excitation, so that the scattering rate along the Fermi surface is almost the same. If you look to the self-energy mediated by charge density fluctuation, this is pretty marginal Fermi liquid-like. You have a scale below which you become a Fermi liquid, and then you have this linear region where the imaginary part of the self-energy is a linear function of the frequency, and you have a very nice scaling property when you scale all the curves with kVt. So this is a possible realization of the marginal Fermi liquid scenario. If you want to calculate transport, we adopted the Boltzmann approach, but we got very similar results with the Kubo formula. We calculated the conductivity due to charge density fluctuation, or resulting from the charge density fluctuation mediated self-energy, giving a scattering rate that we call gamma sub sigma. And we add on top of that an elastic scattering rate, because in the experiments that we are going to fit, you clearly see that there is a tendency of the resistance to saturate at low temperature. So we estimate an elastic scattering rate of the order of 20 to 40 milli-electron-volt. We calculate by means of the Boltzmann formula the conductivity, where Kf, Vf, and of phi and gamma of phi are the Fermi wave vector, the Fermi velocity, and the scattering rate as function of the angle that marks the position along the Fermi surface. And this is the result. The line is result, and the yellow curve is the data in optimally doped neodymium barium copper oxide and slightly overdoped yttrium barium copper oxide. So we get this nice linear behavior, and below a certain scale that marks the crossover to a Fermi liquid regime, our curves deviates from linearity. In the underdoped, there is a downward deviation that is likely due to paraconductivity appearing in the system above Tc and giving this downward deviation of the resistance. In the overdoped, we can even nicely follow the initial upwards deviation of the resistivity, and then of course superconductivity occurs and the resistance drops, and you have a narrower paraconductivity regime in the overdoped sample. In the underdoped, or in the optimally doped sample, this paraconductive regime seems to be broader. So I come to my concluding remarks and perspective. I've shown that charge collecting modes in cuprates have a composite dynamical nature, and they are made of charge density fluctuations and charge density waves. Charge density fluctuation pervade the phase diagram of cuprates. They are found even at high temperature. Charge density fluctuations and charge density wave have very similar wave vectors directed along the copper-oxygen bond. They are very similar. The charge density fluctuation spectra are broader and maybe not T-dependent, but very weakly T-dependent, whereas the charge density wave spectra are much narrower and strongly temperature-dependent. Why is this so? We don't know. We may argue that maybe there are regions where charge density wave find a way to display their tendency to order, and other regions where the charge density wave cannot order because maybe of a locally higher disorder, and then they stay broad all the time. So charge density wave display a tendency to order and compete with superconductivity. Charge density fluctuations are responsible, and this is, of course, our proposal, for the strange metal behavior observed in cuprates, in the sense of linear resistivity. We have shown in a recent paper that we published with our experimental collaborators in Göteborg that strain in thin films may suppress charge density wave and extend the strange metal behavior. So it seems that suppressing charge density waves is a way to extend the strange metal behavior. Maybe I'm masking the charge density fluctuations. Charge density waves are not a scattering channel that gives a linear resistivity. So if you suppress charge density wave, you extend the linear resistivity. And I urge you to check this paper if you are interested in this result. There is the issue of the Planckian behavior and of the anomaly in the specific heat. So how can we possibly have a linear behavior that extends down to low temperature, maybe if you suppress superconductivity by a magnetic field? I had no time to tackle this issue here, but this is published in this paper and is going to be the subject of Giovanni Mirarchi's talk later on this afternoon. We are now developing a theory for charge density wave and transport in strained thin films, and this is underway in collaboration with Get Sabled, Marco Grilli, Giovanni Mirarchi. And with this, I am done, and I thank you very much for your attention.
Yeah.
Okay. Thanks a lot, Sergio, for your great talk.
Thank you, Andrea. Thank you.
So, in this very nice interplay between charge density wave and charge density fluctuation, how you can tune the two degrees of freedom in order to enhance the critical temperature, for instance, to have higher TC superconductivity?
So this is a very good question, Andrea, because this is not yet proven. So there are two issues here. First, here where you see that the peak is composite, you have at high temperature, you have only the broad peak. At lower temperature, you have two components. One is the broad component and the other is the narrow component. So they are both excitations in the charge channel. They have very similar wave vectors. So what are they? Are they related? Our educated guess is yes, they are related. There are two possibilities. I was more inclined to say that they both exist or coexist in real space and are maybe a narrower and a broader resonance in the charge response of the system. There is another possibility that they don't coexist in the same spatial region, so that the system is maybe phase separated on nanoscopic scale, and you have regions where maybe because locally disorder is higher, the charge density wave cannot get narrower and stays broad all the time. Now, our guess, and there are many evidences for this, is that the mediators of superconductivity are the charge density waves, not the charge density fluctuations. So there is this twofold role. Charge density fluctuations are responsible for the linear temperature dependence of the resistivity much above Tc, much above T star, much above whatever, whereas pairing is mediated by dynamical, not static are very bad for superconductivity, dynamical charge density fluctuations. So maybe they are good in a sense that if you have a landscape and then you have a good mediator, then in that case they would interplay. As mediators themselves, they are good as long as they stay dynamical, okay, as mediators. So how to disentangle, maybe if this is promoted by local disorder, I am not inclined to believe this, that this is only triggered by local disorder, but in that case, maybe cleaner system would reduce or suppress charge density fluctuations. This seems not to be the case because strange metallic behavior is also found in very clean sample. So I don't believe that this is enhanced by disorder. Yeah, so the question is, if I understand it correctly, Do they have the same selections rule in resonant X-ray scattering? Yes, that is what we see. We measure them in the same channel with the same setup. So we measure a single peak. This peak can be fitted by a single Laurentian at high temperature, but we need two Laurentians line shapes. No, so we have done 4 polarization. I don't know, yes, if you go to you can check the magnetic sector and you don't find, so this is in the charge sector. None of them is in the magnetic sector, sorry. Both are in the charge sector. Yes, this is in the charge sector. What is? The length, you mean the correlation length? So what is the length scale, the characteristic length scale, meaning the correlation length of this? So the broad peak is rather broad. So the correlation length is few lattice spacings, like 3-4 lattice spacings, which means in the order of, let's say, yeah, and this is much narrower, so you go to 10, 15 lattice spacing. If you take the half width, half maximum as a measure of this scale. So this is at what doping? Sorry, I didn't get it. Okay, so much lower doping. Yeah, so thank you. Actually, this is not in this talk, but we have, our idea is that if maybe with suppressing, after suppressing superconductivity by a strong magnetic field, or maybe even before you suppress superconductivity, you go with this shape. Your resistance goes down, reaches a minimum, and then goes up, and then maybe down again. This minimum is a proxy of charge density waves, not charge density fluctuation. A proxy because there is not really charge order at that temperature, but maybe since this is a state that has maybe slightly high, an energy slightly higher than the superconducting state, it appears in scattering phenomenon. So this is a proxy for charge density wave. Mm-hmm. Yeah, yeah.
Okay, let's thank the speaker again.
Thank you very much.
Okay, the next speaker is Andrea Perali, and the title is there.
Okay, so first of all, I would like to thank a lot the organizers, Antonio Bianconi and Claudio Marcelli, for giving me the opportunity to present the results of the investigation of a new type of BCS-BC crossover in multiband system, screening of superconducting fluctuation and pairing amplification as a route for enhancing superconductivity. So I have collaborated with many scientists in the field to develop the multi-component BCS-BC crossover physics. Of course, with Antonio Bianconi, I have collaborated since 1996 to work in multi-band, multi-component, and nanostructured superconductors. I would like also to promote our next event of the multi-super network, Super Fluctuation 2022 in Padua, and you can refer to the website for additional information. So in this talk, I will review the main concept of the BCS-BC crossover that then will be useful to understand analogies and differences with the multi-band BCS-BC crossover. with the reference to experimental systems as iron chalcogenide superconductors and magnesium diboride. Then I will present a minimal model for exploring the main physical properties of the two-band BCS-BC crossover, and I'm going to present a mean field result at 0 temperature and a model based on Ginzburg-Landau theory to study the effect of the screening of the superconductive fluctuation in a configuration of deep and shallow band in order to show suppression of pseudo gap and TC enhancement. I would like just to set up some milestone of the BCS-BC crossover physics, and of course, the first point is the setup of the two limits, BCS and BC, and it's nice to see that in one of the footnotes of the Bardeen-Cooper-Schiffer paper, in the footnote 18, they say that their theory, the BCS theory, is very different from a situation in which Shafrot, Butler, and Blatt demonstrated that if the size of the pseudomolecules is less than the average distance between them, then you have a Bose-Einstein condensation situation. So in the BCS paper, you have, of course, the setup of the BCS theory with extended Cooper pairs and a fermionic superfluid with a transition driven by the interaction, and instead, in the opposite limit, you have the Bose-Einstein condensation of preformed local molecule formed in real space with a large binding energy. But of course, I mean, we make progress by connecting different nodal ideas. The connection between the BCS theory and the Bose-Einstein condensation was done only later, and in the BCS-BC crossover eras, in the time axis, we can find the first two decades from 1969 to 1990, which there were a foundational work at 0 temperature by Leggett. The first proposal was by David Eagles, for low density superconductors. And then at the end of the 80s, Philippe Nozière, who unfortunately passed away recently, I heard this news, unfortunately, and Nozière, together with Smith-Rink, proposed the extension of the BCS-BC crossover at a finite temperature and the first diagrammatic approach to study the phase diagram of the crossover. Then, during the 90s, the BCS-BC crossover physics has been developed thanks to the understanding of all the work aimed at the understanding of the phase diagram of cuprate superconductors. And we started with Antonio to work on this topic in the framework of Superstripes, but also nuclear matter was another system of interest for the BCS-BC crossover. During the decade from 2000 to 2010, the field of BCS-BC crossover got an enormous progress thanks to the ultra-cold fermionic atoms, and then to the first detection of the pseudo gap in the finite temperature experiments realized by the Gene group. Very recently, in the last decade, between 2010 and 2020, we had again the BCS-BC crossover physics for superconductivity in a solid-state system and all the physics of multi-band and multi-component systems I'm going to describe today. So, the physical system that can host the BCS-BC crossover with the tunable properties and multi-component effects are, of course, ultra-cold atoms that can be realized with the fermionic degrees of freedom in several different spatial dimensions. So 3D, two-dimensional system, and one-dimensional system. Superlattice can be realized, and different shape of the traps. Then we have very recently the possibility to study the BCS-BC crossover in electron hole van der Waal heterostructures with or without magnetic field to realize the quantum Hall effect configuration, in which the BCS-BC crossover can be tuned by changing the densities of the carrier. Then our proposal of the superstripes, in which the BCS-BC crossover can be tuned by the geometry of the system. Again, cuprates is still a very interesting playground to study performed the Cooper pairing and also the physics of the Kosterlitz-Towles transition and the vortex-antivortex phase fluctuation. And nowadays, two very interesting systems for exploring in solid-state superconductors the BCS-BC crossover physics are the iron chalcogenide superconductors in different geometries and the layered nitrides, in which in these two-dimensional systems the charge carriers can be tuned in a very precise manner with the gate doping. I want to summarize the main properties of the BCS-BC crossover in a single component system, just showing very recent experimental results published in Science by the Iwasa group in lithium intercalated layered nitride. You see that by tuning the density of carriers, it's possible to explore the entire, almost the entire phase diagram of the BCS-BC crossover physics. So you have the superconducting phase in which the critical temperature display a maximum, which is typical of the BCS-BC crossover in lattice system. But then if you increase the temperature above the critical temperature, you have the persistence of the gap, but with a finite spectral weight. And so the name of the pseudo gap, for instance, in the tunneling, in the scanning STM experiment, in the tunneling experiments, in which the pseudo gap is clearly present up to a crossover temperature T star. And the ratio between T star and TC increases as you explore the entire BCS crossover physics. You see then that the ratio between twice the gap and TC increases from the BCS expectation toward the strong coupling, and also the energy scale of the gap increases, giving evidence of the strength of the pairing, which is increasing, approaching the BC limit. Then the central point of my talk is to answer the classical question on the multi-super BCS-BC crossover. Is the multi-band or multi-component BCS-BC crossover a new type of crossover with the new substantially different properties with respect to the single band counterpart? And this property can be useful for something. For instance, to try to enhance the critical temperature in the BCS-BC crossover, because you see here clearly that the pairing energy scale is very high. So this is the mean field pairing temperature scale. And if you see only the pairing energy scale, you can see, okay, also in layered cuprates, in layered nitrates, we can reach 40 Kelvin of superconductivity. But then the superconducting phase and amplitude fluctuation reduce by half the critical temperature for condensation in the superconducting state. So is it possible in some manner, in some way, to shrink the pseudo gap regime and to take benefit of the high energy scale of pairing while screening in some way the detrimental superconducting fluctuation? And in the case of a multi-band system, the answer, as we will see, is yes. So pseudo gap is a consequence of strong pairing and small Fermi energies. But in general, if we have a mechanism for increasing the critical temperature, what we have is that the detrimental fluctuation in general renormalize the critical temperature given by the mean field scale. The critical temperature is renormalized to very low values because of large or very strong superconducting fluctuation. And this superconducting fluctuation becomes even stronger when you reduce the dimensionalities of the system, or you reduce the densities, or you increase the coupling between the fermions constituting the pairing. So our proposal is that if you have at least a two-band system in which you have a deep cold and a shallow hot band, you can generate a screening of superconducting fluctuation, which allows to suppress a pseudo gap, so you have the pseudo gap shrinking, and to make possible for the system to stabilize Cooper pairing at a very high temperature, possibly closer to the T-star pairing temperature, which can be a very high temperature scale. So one interesting experimental signature that has been obtained in iron chalcogenide is that in the iron chalcogenide, the group of Matsuda observed, but also the group of Kanigal observed the presence of the Bardeen-Cooper-Schiffer Bose-Einstein condensation regime, a crossover in this system, but at the same time, the pseudo gap was not detected. So you have a system, a multi-band system, in which you can detect the BCS-BC crossover from the evolution of the excitation spectrum, but at the same time was not possible to detect the pseudo gap in the normal state, which usually is a fingerprint for the crossover physics in a single band system. So this was an interesting experimental news on the multi-band BCS-BC crossover. From the point of view of the physical system, we have at least two interesting prototypes of multi-band superconductivity in which the BCS-BC crossover can be tuned by tuning the densities or the geometry of the system. And one is surely the magnesium diborite, in which you can tune a Lipschitz transition from a two-dimensional to a three-dimensional Fermi surface configuration. And we have studied in 2010 resonant and crossover phenomena close to the band age in magnesium diborite superconductors. But also the case of iron chalcogenide bulk system or monolayer system or few layer is an interesting, very interesting physical system having multi-bands and the possibility by doping to have several different Lipschitz transition in which you have multi-component Fermi surface appearing, and then the appearing of a new Fermi surface spot is accompanied by an enhancement of the critical temperature and of the gap energy scale. So these are very nice with many incipient bands or a situation of consisting of holes and electron bands. So it's iron chalcogenide is really a nice playground for the multi-band BCS-BC crossover. Our theoretical model is based on two electron-like bands in which we have a deep band which is populated by a large fraction of electrons and a deep band in which the pairing is strong. Here in the deep band the pairing is weak, in the shallow band the pairing is strong. So we have cold band and hot band in this respect. The mean field analysis at =0 of the entire BCS-BC crossover has been explored in this paper together with Andrea Guidini. The only point I would like to highlight in the phase diagram at =0 is that the boundary lines between the BCS, the crossover, and the Bose-Einstein condensation line for the hot band are strongly modified with respect to the single band behavior only when you consider the crossover between the BCS-BC crossover and the BEC line. So in the presence of a reservoir of fermion, the boundary line between the crossover regime and the BEC regime for condensation of local pairs is expanded a lot. So the first important difference is that the Fermi pressure of the deep band acts in order to expand in a considerable manner the crossover regime in a two-band system. So you have a very large phase space to explore the crossover regime in a two-band superconductor. And here we have located, in terms of the detection parameter gap over EF, we have located the cases for iron-based superconductors in the crossover regime or even approaching the Bose-Einstein regime. Regarding the final temperature properties and the emergence of the new effect of the screening of pairing fluctuation in superconductors with the coupled shallow and deep bands as a route to higher temperature superconductivity has been the first complete paper with different theoretical approaches has been published together with Selaznic, Shanenko, Vagov, and Aguiar in 2019. The approach was based on a Ginzburg-Landau two-band free energy functional of the Ginzburg-Landau theory. And the main point was to write an effective free energy in which the critical mode was considered, and the parameters of the critical mode were written in terms of a combination of the parameters of the two subsystems taken separately and then coupled. So close to the critical temperature, we have a new free energy functional of the Ginzburg-Landau approach of the critical mode, in which the new effective parameter can give rise to a new Ginzburg number, which is a combination of the parameters of the single bands of the Ginzburg-Landau free energy of the single bands. The two are combined together, and for instance, in 2 dimensions, the Ginzburg parameter, GI, can control the renormalization of the critical temperature with respect to the pairing scale TC0. So TC0 is the pairing scale for the onset of pairing, so for the onset of preformed pairing, so the high temperature scale that we would like to reach, while TC is the renormalized critical temperature due to the fluctuation, to the detrimental superconducting fluctuation. And this kind of difference of renormalization is controlled in the Ginzburg-Landau theory by the Ginzburg parameter, and this expression depends from the dimensionality of the system. The results are the following. Weak screening, so we can tune the amount of screening, the effect of the screening in the two-band system by changing the pair exchange term between the two condensates, between the two partial condensates. So we have intra-band pairing scale, while the pair exchange lambda 1,2 term control the coupling between the two partial condensates in the two bands. So if the lambda 1,2 coupling is small, you see that you have a pseudo gap which is quite large in the phase diagram, and hence the critical temperature will be strongly renormalized with respect to the mean field pairing scale, while instead if we increase the lambda 1,2, we can shrink the pseudo gap, and the renormalized critical temperature can go closer to the pairing temperature scale. Then we can increase the effect of the deep band. So if we have GI deep, which is very small, means that the Ginzburg number for the deep band is very, very small, and so it's able to suppress a lot the fluctuation. And so if we consider the second band as very deep, this effect of shrinking of the pseudo gap regime is even more visible and more clear. So we have extended to many different band configuration our approach, and for instance, we have considered the coexistence of one-dimensional band giving peaks in the density of states, like this one, but of singularities, and a three-dimensional band, which instead gives a very flat density of states. Also, in this case, we can reach a situation in which increasing the coupling between the two condensates from 0.0025 to 0.05, we can, with the screening, completely suppress, wash out the detrimental fluctuation. So we have extended also our approach to ultra-cooled fermions with different components, and in this case, the superconducting fluctuation, the pair fluctuation, have been studied by means of a T-matrix diagrammatic approach. And for a window of parameters, we have found agreement between the diagrammatic approach based on T-matrix theory and the result of the Ginzburg-Landau approach. 5 minutes. Okay. Okay. So we can refer to these two papers, for instance, for analyzing the effect of pair fluctuation and BCS-BC crossover in multi-band systems. typical of ultra-cold atoms and with a different diagrammatic approach. So, to conclude, we have demonstrated that for a two-band, at least a two-band system having a two-gap superconductivity, we can generate a configuration in which superconductivity can be enhanced to very high TC, to very high temperature scale, and at the same time having one shallow band with strong pairing and one deep band, wide band with a weak pairing. We can have, together with at least a small Cooper pair exchange between the two condensates, we can have the coexistence between a BCS condensate and a BCS-BC crossover condensate in the same two-gap superconducting system as an ideal system to stabilize higher temperature superconductivity, even, we don't know, room temperature superconductivity. Thank you very much. Yeah, it's yes. So the question, if I understood well, is to give additional details on how the Gisborne-Landau equation has been obtained, separating slow and fast fluctuating contribution. So this is a typical method in the Gisborne-Landau approach, which first of all, in a two-band system, you have usually a critical mode and a subcritical one. And indeed, in the two-band configuration, you can have two length scale for phase coherence. One length scale is divergent at the critical temperature, and the other one remains finite as a function of temperature approaching the critical temperature. So the first distinction is between critical and non-critical modes, and here we study only the critical modes, psi, in which the phase coherence diverge at the critical temperature for the coupled system. Then the critical mode, you need to study the fluctuation of the critical mode to write down the Gisborne-Landau equation. And so the critical mode itself is then divided in two components, and you study then the components of the slow fluctuation, in which you average out the fast fluctuating contribution. And so the linear term is the one which is important for evaluating the renormalization of the critical temperature, because when the coefficient of the linear term goes to 0, you have the critical temperature. And once you renormalize the linear mode by averaging out the fast fluctuating contribution, you get the renormalization as the quartic, averaging out the quartic contribution in such a way to renormalize the linear and quadratic terms and to get the renormalization for the critical temperature. So that's the usual approach extended to a two-band system.
Okay, one more question.
I didn't hear very well the question. The question is on the pair exchange term, the amount of exchange. Yeah. So sorry. Yeah. So the question was on the to comment on the amount of pair exchange term that you need to explore the phase diagram and the different properties of the phase diagram. Yeah, this I mean, it's a result of our calculations, in the sense that the lambda 12 is very effective in switching on the screening properties, and lambda 12 is a term which is able also to increase the mean field critical temperature. Indeed, we see that increasing lambda 12, you have TC naught, which is increasing only because lambda 12. But then at the same time, lambda 12 is enough to switch on even a small amount of pair exchange to allow you, I mean, 2%, 0.02 with respect to a standard intrapair lambda, which is 0.3. So it's enough 10% of pair exchange term to generate a very substantial screening. That's the result of our calculation. But in general, it's true that a very small amount of pair exchange is enough to couple in efficient manner the system.
Okay, let's thank the speaker again.
Okay, thank you very much. Okay, so welcome again to the first afternoon session of Superstripes 2022. We're starting a bit late also because of the delay in the last session. So it's a pleasure to introduce Robin Guehne.
Guehne.
You?
Guehne.
You? Guehne.
Yeah,
you?
almost.
Okay.
It's difficult.
The talk will be on electronic properties of the bulk of three-dimensional topological insulators investigated with the So you have 25 minutes, including questions, and I will let you 5 minutes.
Excellent. Thank you very much. Thank you very much for the introduction, and thank you very much for the opportunity to be here and to give a talk. It's a great pleasure to me. As already said, my name is Robin Guehne. I'm coming from Leipzig. I'm from the laboratory of Professor Jürgen Haase, and together we are investigating three-dimensional topological insulators with NMR. And today I would like to give you a brief overview of our work on the last years and recent progress. So first of all, let me remind you on some basic properties of nuclear magnetic resonance. The spin system is governed by a Zeeman interaction once it's put into external magnetic field. And you know, the spin system is quantized, and the energy distance between these discrete energy states will then give the Larmor frequency. And the Larmor frequency is what we measure, or what we use to measure the NMR signal with. So from that idealized spin system in the magnetic field, you would expect a very narrow resonance line at the Larmor frequency. In reality, of course, we do not observe such a narrow line, and we do not observe that line actually at that frequency, because usually NMR signals are shifted with respect to the ordinary Larmor frequency. The reason is the NMR shift, the chemical shift, or as you probably know, the night shift, that reflects the influence of electrons surrounding the nucleus. So for example, the core electrons are polarized by the external magnetic field, and therefore the local magnetic field at the nucleus is slightly altered. But also the interaction with free electrons through the night shift would give rise to an NMR shift. So this already gives an idea that NMR can measure local electronic properties. Furthermore, the resonance lines are not delta functions, but rather they are broadened, and these broadenings can also contain very important information about the local environment and interactions governing the NMR signals. For example, usually a broadening of an NMR line comes from inhomogeneities, some defects, such that the local magnetic fields seen by the nuclei throughout a large sample are slightly different and distributed, giving rise to an inhomogeneous broadening of the resonance lines. But also, there can be additional couplings that give rise to such a broadening that I'm going to touch later on again. And these interactions are basic, for example, dipolar interactions. Simply, if you consider a spin sitting somewhere, this spin may see the magnetic field of its neighbor, and therefore the local magnetic field is slightly changed. Overall, the NMR, as you can see, provides a quantitative insight into chemical and electronic properties of the sample. To give you a brief example for that, please look at the right. There's the crystal structure of bismuth telluride. It's a layered compound. We have a quintuple layer, which is the basic building block connected via van der Waals interaction. And the quintuple layer consists of 2 outer tellurium sheets, 2 identical bismuth sheets, and 1 inner tellurium sheet. And because of the local environment of the different tellurium sites, we get 2 different signals representing simply the 2 different local symmetries. And because NMR is quantitative and we have twice as many outer sheets in comparison to inner sheets, our outer signal is twice as strong as the inner signal, and we can assign the NMR signals to the crystal structure. So we have a quantitative probe with a local resolution, which allows us to probe and investigate materials. Just to mention, again, the local resolution has been used to see or to try to see the special surface states of the topological interlapse bismuth telluride. You can find that in these publications. Today, I will talk only about the bulk, no surface states NMR. Okay. We have to mention one more interaction, which is quite interesting and quite important for us. If we consider spin systems with a nuclear spin larger than 1/2, as for example, bismuth 209, we have yet another interaction that could be present, a so-called quadrupole interaction or a electric hyperfine interaction. This is an electric interaction. It's the interaction of the nucleus with the local charge environment. And this interaction gives rise to a splitting into 2 times I equidistant resonance lines. In the case of bismuth, it's a spin 9/2 system. We have 10 energy states. This means we have 9 transitions, and they are split in the frequency space, giving such a typical spectrum of, for example, bismuth NMR in bismuth selenide. And the splitting itself is very important. It's directly related to this local charge environment. In addition, it's very sensitive, and these local charges may stem from partially filled orbitals. They may stem from the chemical bonds or even the neighboring ions. Now my talk outline, I will start with a brief introduction to our work on the measurements of the indirect Bloomberg-Rowland coupling. I will go over to some band inversion concepts, ideas, and the bismuth NMR again. And finally, I will inform you about what we call a magnetic field-reduced charge symmetry. Bloomberg-Rowland coupling. When my colleague Natalia Georgieva started, my former colleague, to investigate bismuth selenide using selenium NMR, they observed 2 resonance lines in a similar fashion as I've shown you before, the 2 tellurium signals from the bismuth telluride. So the same structure, they get 2 resonance lines for different orientations. They are just shifted towards each other, just representing the shift anisotropy and not going to the shift anisotropy. But what I also noticed is that the lines are quite broad. They are broad. And said, okay, well, that's perhaps not a surprising thing because we know that bismuth selenide and all the other systems are quite inhomogeneous. There are lots of native defects in there, like selenium vacancies, anthracite disorder. And usually you would then expect that the line broadening, as I mentioned before, may stem from inhomogeneities and representing the kind of dirty single crystal. It's single crystal NMR. However, what they've done after that, they changed the external magnetic field and they noted down the full width half maximum as a function of the field. This is what you can see in the lower plot. And obviously, the line width is pretty independent of the external magnetic field, which is extremely surprising. Because first of all, if it's inhomogeneities, you would expect the line width to be like a straight line proportional to the external magnetic field because it is representing just the distribution of shifts. And if the resonance frequency is depends or is proportional to the magnetic field, its distribution will be proportional to the magnetic field as well. But the observation is quite different. It's a rather field-independent line widths, and they are huge. And magnetic field-independent line widths usually stem from dipolar interactions, as I mentioned before, the direct dipole couplings. But we can pretty well estimate these couplings, and the resulting line width is given by this dashed line down here, and you find it's way too small. This means that a magnetic field independent line width, as extrapolated from the measurements towards zero magnetic fields, must be reflecting an additional coupling, which is usually mediated by electronic states. The idea is that electrons pick up the polarization of the nuclei and transfer that to distant nuclei, and therefore establishes a communication between nuclei over distances much larger, perhaps, or much stronger as the ordinary dipolar interactions. Together with Ian Garrett, or especially Ian Garrett, calculated this indirect coupling phenomena in bismuth selenide using a tight binding model, and he found that the Blomberg-Rowland contribution to such a broadening is much larger than the RKKY interaction. That is, that a coupling that involves virtual transitions across the band gap dominates over a coupling that takes into account the density of states, that scales with the density of states. So this was a really surprising result because, first of all, it gives a huge line width, and it may be an important, idea and concept in the field of magnetic topological insulators or magnetically doped topological insulators, because if nuclear moments can communicate over these exchange interaction, perhaps magnetic moments of localized electrons do the same. Meanwhile, we have extended the study to bismuth telluride and antimony telluride. It's a little bit a crowded plot, but what we observed is pretty much the same result. Now the outer signals are shown on the left and the inner signals shown on the right. The triangles belong to bismuth telluride samples, 3 different samples. And we can see that most of them show a huge magnetic field independent line width, even larger than that we observed in bismuth selenide. And the same holds for the inner signals. What is surprising is that the inner signals of antimony telluride are showing a similar large broadening. However, the outer signals, as shown with the linear graph here, they show not at all a broadening that is quite unexpected. They behave as if it's only inhomogeneities of the samples that give rise to the broadening. And this is quite surprising because we have no idea how the outer signals cannot take part in that interaction, whereas the inner ones do. So this is pretty recent work and just submitted to the Zeitschrift of Anorganische and other Chemistry Journal. Sorry for that. It's a German name. And this is something which is quite surprising, and we hope that it will give us the key to get a better understanding, because the theory so far does not really cover our results. So we still get much larger line widths than we expect. This is what I want to say about the Blomberg-Rowland coupling. I would like now to give a brief introduction to the bismuth NMR and how it is related to the band inversion. I started with the same plot as before, but now I do not show you just a single spectrum, but 4 of them. You get this is a spectrum that we got from 4 different single crystals, and the difference is that from the bottom to the top, the carrier concentration increases. So the defect density is larger from bottom to the top, and the carrier concentration increases, and you can see already that the spectra are shifted to higher frequencies. What is not as easily visible, but is actually the case, is that the splitting among these between these individual lines is reduced as we increase the carrier concentration. And this tells us that the quarter-pole interaction or the electric hyperfine interaction is indeed sensitive to additional charges. And this brought us to the idea that we may be able to put that into connection with the topological band inversion. If you look up here, the sketch, or actually it stems from calculations of the band edge in bismuth selenide, we know that the band inversion reverses the order of bonding and anti-bonding states across the band gap. So in bismuth selenide, actually a fraction of the lower tip of the conduction band associated with bismuth states is moved into the valence band, and parts of the valence band, usually associated with selenium, is moved into the conduction band. If you transfer this idea to real space, we must assume that those states related to the Fermi level must then be moved from bismuth location to selenium. And if the local charge environment changes, we actually observe a slight change in the quarter-pole splitting, or a change in the electric hyperfine interaction, because the bismuth NMR sees the local charges, the local charge symmetry in that system. Of course, we cannot just switch off the band inversion in the real sample, so we have to take into account. Oh, sorry, this is bismuth telluride. We have to take into account DFT model calculations. And our colleague Wojtek Lahn from Prague, he calculated this quarter-pole splitting. This is the strength of the electric hyperfine interaction as a function of the carrier concentration, here represented as extra charges per formula unit. And the open symbols, the open squares, belong to calculations using no spin-orbit interaction. Sorry, it's this one, and therefore no band inversion. And the solid symbols represent band inversion and spin-orbit coupling, whereas the triangles again represent our measurements, including even some literature values. As I've shown you before, in business terabyte, splitting is much larger, but nonetheless, it fits pretty well into our calculations. Currently, we are trying to analyze in more detail the calculations in order really to figure out what's the fingerprint of the band inversion, and it turns out that not necessarily the difference, the absolute difference between these two values of the splitting, so 150 kilohertz with respect to or compared to 500 kilohertz, but rather the slope as a function of additional carriers is indeed the fingerprint of the band inversion. There's some time left, right? I would continue with, I would like to continue with what we call, sorry? Left. Oh, 12 minutes left. Oh, I should slow down a little bit. So we have more time for questions, excuse me. Okay, so I would like to present our data, a little bit recent data of the, what we call magnetic field induced charge symmetry. What we now do is, I've shown you before the spectra that we obtain for the single crystal being aligned with its crystal C axis along the external magnetic field. And we get a nice splitting, we can fit it, we get the result. What we now do is we change the single crystal orientation inside the magnetic field, which is typical in order to observe the shift anisotropy usually, or in this case, the anisotropy of this electric hyperfine interaction. And the sample on the right and the lines that we observe is pretty much what we expect from the system, because the splitting should follow a 3 cosine square beta minus 1 relationship, and beta represents the angle between crystal C axis and external magnetic field. And this function goes, if you just put in different values, you will find that at the magic angle, which is 54.74 degrees, that the splitting perfectly disappears. It's not there. We wouldn't be able to notice that there's any quarter-pole interaction. The system should and does behave just as a spin 1/2 system, as if there's no electric hyperfine interaction. As we turn around the single crystal to 90 degrees, we observe half of the splitting. The idea behind this is that the actual splitting is given by this charge tensor. And as I said, the charge tensor must somehow reflect the local chemistry, the local environment of the nucleus. We usually tie the charge tensor to the crystal structure, to the crystal itself, and by rotating the crystal, we should then rotate the charge tensor and observe the actual change of the splitting. This is what we observe for this particular sample, and this is what is ordinarily expected from such a single crystal electric hyperfine interaction. However, if we look at different samples, again, bismuth selenide, we observe something very, very different. First of all, in the C parallel B orientation, we get pretty much the same as we observe for the other sample, although the splitting is perhaps slightly reduced. But if we go especially into the magic angle, we do not observe just a single very large and intense resonance line, but rather we get a broad spectrum, which is almost broader than the spectrum we observe in C parallel B. And we even have the impression to see these additional, individual satellites, individual transitions that tells us that to some extent it seems as if this local charge tensor seems not to be rotated together with the crystal structure. So it seems to be kind of disconnected from the crystal structure, which is extremely baffling because there has never been similar evidence before. We tried it back and forth and we tested everything and we looked at different samples, and it turns out that those samples with the higher carrier concentration, the sample on the left has a carrier concentration of about 2 times 10 to the power of 19 electrons per cubic centimeter, whereas those the sample on the right has a moderate or low carrier concentration of 3 times 10 to the power of 18 cubic centimeters. And we said perhaps it's related to the conduction electrons. So we checked other samples, and again we get the same result. For those samples with a rather high carrier concentration, we get a mismatch between measurement and expectation, whereas for those samples with sufficiently low carrier concentration, we get a result as we expected. So obviously, somehow the defect density, not the defect density, excuse me, the carrier concentration or these free carriers must play a role in our observation of this strange or unexpected orientation dependence of the electric hyperfine interaction. Which should put some ideas together. So we find something that is somehow related to the charge tensor being kind of disconnected or untied from the chemical structure. We think that it must be related to the charge carriers, and I haven't shown it to you, but in business terabyte we get a similar result, and we tested it down to 2 Tesla, and we find it being at the magnetic field independent for sufficient magnetic fields of at least 2 Tesla. We cannot go further down in magnetic field. As these observation seems to be related to the charge carriers, it might be noted that these charge carriers are subject to strong spin orbit coupling. They show effective G factors of 20 to 30, so they have a huge magnetic moment, a factor of 10 and larger in comparison to ordinary magnetic moments of electrons. This was tested by Köhler and Wollers using Shubnikov-de Haas measurement and even EPR, electron paramagnetic resonance. So they measure the NMR, the EPR signal of these conduction electrons. And it leads to the suspicion that perhaps due to the strong spin orbit coupling, the quenching of the angular orbital momentum, quenching of the orbital angular momentum of these electrons is not perfect. It's not quenched in the lattice, and some rotational part of this may remain, which is then be linked to the external magnetic field. So our idea is that the external magnetic field polarizes the electrons in the system, and they kind of tear their orbital angular momentum with them, such that the charge tensor that we observe with the bismuth NMR, I'm almost through, that the charge tensor as we observe that with bismuth NMR is rather tied to the external magnetic field than being tied to the crystal structure. This is just a hypothesis. We are working on the understanding, of course. Nevertheless, all this observation is, of course, questioning the NMR in strongly spin orbit coupled systems so far. And as we know, there are no proper theory about how to handle magnetic resonance in these systems. Furthermore, we do not we assume that if there are really some additional degrees of freedom related to the rotation part of L, there might be also other material properties affected, such as heat capacity or magnetic resistance. And we finally do not exactly know whether this is in any way related to the non-trivial band topology in bismuth selenide or bismuth telluride, even though it seems not necessarily to be the case. As a conclusion, as in the beginning, I've shown you that the NMR line broadening in bismuth selenide, bismuth telluride, and in bismuth antimony telluride is chiefly magnetic field independent. This is the observation as well as isotropic, and it seems to some extent to have a weak carrier concentration, carrier dependence, which implies it's rather of a Bloembergen-Roland type than of RKKY. We couldn't prove that so far for bismuth telluride and antimony telluride, and this observation may potentially be related to magnetically doped topological insulators or magnetic topological insulators at some point. The dependence of the bismuth electric hyperfine interaction on the carrier concentration allows us to sense the real space signature of the band inversion in quantitative agreement with DFT calculations. And we think that perhaps at some point this quadrupole NMR, or the NMR of the electric hyperfine interaction, may be used to study topological systems through their bulk properties. Finally, the unusual orientation independent or dependent quadrupole interaction in bismuth selenide and bismuth telluride should be taken into account when considering strongly spin orbit coupled systems investigated with NMR. And it applies indeed also so far perhaps unknown relaxation mechanism that is related to the lifetime of the corresponding electronic states. I didn't mention our observations on the shift phenomenology as well as relaxation, which is also quite unusual in that systems. This includes spin 1/2 nuclei. The same holds for these quadrupole nuclei. I have probably plenty of time to say thanks to my collaborators. Of course, Jürgen Hase, who helped me through these stuff and with the measurements. Natalia Georgieva, who carried out the first measurements in bismuth selenide. Jakob Nachtigall, a student who is currently working on these samples, as well as Andreas Pöppel, who is the EPR guy in Leipzig. Wojtek Klan for his calculations, as well as Claudia Felser and Chandra Shikhar from Dresden, and Grant Williams, Shen, and Uli Zülige from Wellington, and Katsu Kadowaki from Tsukuba for samples and discussions, and Ian Garrett for the calculations, as well as Oleg Sushkov for discussions. And finally, thank you very much for your attention.
Thank you very much. So, questions, please? Okay, with that.
Yeah, 17.6 Tesla. Oh, well, I'm sorry, I missed it. So we're using. Oh, it's also, like the magnet's a commercial Bruker magnet. It is a commercial Bruker magnet for 16. It's a 750. So the hydrogen resonance frequency is 750 megahertz. And all these measurements, I might have forgot to say, it's room temperature measurement. Okay. Okay, that would be great. Maybe I didn't understand all these details.
Next question.
To vary what? The thickness, yes, I did. So you're asking for the intensity. If I take my resonator and change, this is really a difficult issue actually, because one thing is, of course, it's a conducting system. So our RF field will not penetrate the whole system. So we do know that we have a penetration depth issue, which reduces the intensity of our signals. So what my colleague done before me, and what I did again with the bismuth NMR, we take a large single crystal and we cut it into slices, smaller and smaller, to observe the intensity and actually if something changes to the NMR spectrum. So I went from roughly 1 millimeter down to perhaps 10 to 20 micrometers. And the intensity issue is a problem because what you change, you do not only change the number of nuclei that contribute to your signal, you do not only change the penetration, or like at some point the penetration depth touches, but you're changing also the filling factor of the coil. And this again influences the intensity. And it's quite not a trivial question how to relate these different measurements with different thicknesses to each other, because the number of nuclei and the filling factor play an important role. And we were discussing a longer time how to use these measurements to see the penetration depth. So at some point we should be able to measure the penetration depth with such measurements. So it's actually not trivial, and we didn't really make it. It's really complicated because it requires the knowledge of the magnetic field of the coil and how it penetrates the sample. If you make it smaller and smaller, the penetration of the field is changing. I mean, the RF fields that we use to excite and to read the spin system. Sorry, the polarization. It's an alternating field. Yeah. This is the external field, and we need for the measurement himself. Well, it's much smaller in strength, of course, and it will have a much better penetration. No, it's related to the sorry. Oh, excuse me. Of course, the RF field that we use for measurements is always perpendicular to the external field, in any case. So if we rotate a single crystal in a way, we rotate it with this symmetry axis around the symmetry axis, which is of the coil, which is perpendicular to the external magnetic field. So we do not change the orientation of the RF field with respect to the external field. Okay, good.
Okay, we should move to the next figure. Thank you very much.
Thank you very much. Thank you very much.
For the questions. So now. So Sujoy Roy. Okay, so you have 23 minutes plus 2 for questions. We will let you 5 minutes before. So Sujoy Roy studied a dynamic relation of stripe domains in magnetic field.
Okay, good afternoon. My name is Sujoy Roy. I'm at the Advanced Light Source and at the MSD of the Lawrence Berkeley National Lab. Well, before I start, thanks to the organizer for giving me this opportunity, particular to Professor Bianconi, with whom I had the pleasure to work very recently. So I'm going to talk about static and dynamic correlations of stripes, which we have been hearing quite a bit in this meeting. But these stripes, the origin of these stripes are of course different. They are magnetic. They happen in magnetic film and not related to superconductivity. But my hope is at the end of my talk, you will be a bit convinced that you will at least hear some common language that we have been hearing at least today in the morning session. Those who are thinking that what the heck is this? This is actually a diffraction pattern out of a magnetic thin film, the domain pattern, but of course you see this modulation, and that's the modulation that happens because we are using resonant coherent X-ray beam. So basic resonant X-ray scattering will give a much more flat diffraction pattern, but because the beam is coherent, it gives to this speckle pattern, and this is the topic of the talk today. Before I start, let me just thank all my collaborators with whom I had the pleasure to work. James Lee was my postdoc, and then Sergio was a graduate student. They all have moved on to do bigger and better things. Karina was a postdoc with Karin Damen at Urbana. And then I worked with Arnab and Milan Sanyal at Saha Institute in India. And then some LTEM that I will show was done by Spencer Alexander and with Ben McMorran. And then all the team at LCLS. And I must thank US DOE for giving us continuous support and also through the magnetism program at LBI. I don't think this crowd needs to be convinced, but we all know that these thermally driven fluctuations are pretty important, and they appear in various different forms in condensed matter physics. And I've given a representation examples. They are by no means comprehensive, but today I'm going to talk a little bit about that how, in the context of skyrmion, which is a topological magnetic spin texture, these fluctuations come about. But we have been hearing a lot about superconductivity. A lot happens in complex oxide and all these different examples. So basically, I'm just trying to impress upon you the fact that understanding these fluctuations, studying these fluctuations are very, very important phenomenon. So the theme is really that I will use a coherent X-ray, and I will show you using this iron gadolinium thin film where the stripes and skyrmion phases appear, that how we can use coherent beam to study these two types, mainly these two types of fluctuation. One I call as spatial fluctuation, where I will show that avalanches and domains, cascades of domains in this film, and this is done as a synchrotron at the Advanced Light Source. And then I'll move on to this new method that we have been developing for the last few years at LCLS, and which is a way to study temporal fluctuations. So what are coherent beams? So let's say there's a sample and the beam comes in, beam goes out, comes at an angle alpha and angle beta. And now let's suppose that these two angles are varying. So this would be typically a intensity pattern. So there will be a critical angle below which the whatever beam comes in goes out, and then there will be reflectivity, and then the Bragg will starts appearing, right? And then you can fit this, and then you go get what you call the static structure factor S of Q. So what you see here is that there is no time, it's only the space. To get time information, you put this coherent beam. So whenever you put a coherent beam, what we can do now is that we can draw this type of a curve, which is not a data, of course, this is just a representation. And then these steps will start to appear, and each of these steps is a correlation event. So for example, let's say this is a magnetic system, so probably very fast time scales will be spin, and then there will be domain and things like that. So what the coherent beam enables is that it enables measures of correlations, mainly time correlation, but you can vary this independent parameter. So basically what we are after is S of Q or T or S of Q of H or something like that. So that's the goal of having that coherent beam. How do we see in real life? So let's say this is a labyrinth domain pattern and you come with a beam. Of course, it gives rise to a diffraction pattern, the so-called Debye-Scherrer cone. But then the moment we put coherent beam, then you can see that this whole structure remains same. So the total intensity, of course, has to remain same, obviously. But the intensity gets fractured into modulated into this highly structured thing, which is called the speckle pattern. And the reason this happens is because the beam is coherent, the outgoing beam re-interferes with itself. So this speckle pattern is the representation of the exact instant the beam interacted with the sample. And this is this very important thing that we will not get otherwise if we are not using coherent beam. That the signal from this coherent beam diffraction is basically, it's an exact representation of the way the beam sees the sample. So now imagine that if this thing was moving, then this thing will also move, right? And that's how we are measuring the correlations, because we are instantaneously getting the information. So here I just showed some other examples where, as I was showing in the title slide, so this is an iron gadolinium. I think it's a cobalt palladium thin film of domains, and this is the I think the orbital order of a manganite, and you can see that all these gives rise to this heterogeneity. So basically, what it means that whenever we see this speckle pattern, the sample has a heterogeneity. That's one of the main takeaway from this method, from the slide. Sorry. So let's go into the first example of jumps and domains. I'll just briefly mention, probably a lot of you already know what's a skyrmion. It's basically stable particle-like spin texture. So if you think of the parameter space in the spin space, then Sx, Xy, and Sz, if you have this soccer ball kind of a spin texture where the spins are going in the radial direction outwards, you project it on the real space, you will have this kind of a vortex kind of structure where the spins are going in and making a kink and coming out. So if you pull this kink, the kink can never go away. And that's why it's actually a topological structure. It's given by a winding number, how many times it wound on the great sphere. So this one wound 1 time on the great sphere. So it is a winding number of 1. There are predictions of winding number of 2 and others also. It's clearly different than a ferromagnet because ferromagnet has no winding number. Here the order parameter is the winding number. And it's different than chirality, of course, because chirality is a single Q feature. This is a triple Q feature, shows up as an hexagonal lattice. And this is from very early on, theory predicts that there are fluctuations in the skyrmion phase. This field is booming in the field of magnetism, and there are many schemes. People have done X-ray magnetic imaging. There are schemes of showing that how, this is a work by, I think, Albert Fert, that where he shows that, his group at least shows that how they are not getting pinned at the pinning center, and then there are other schemes of getting new types of devices. There are many reviews you can read, and they go from, I don't know, like nanometer all the way to micron size and different types of interaction. The most interesting one or the most popular one is the Zaloshinsky-Moreo interaction, which gives rise to this kind of spin texture. Basically, it's one of the way to think is that the exchange is keeping them aligned and the Zaloshinsky is causing them a tilt. So if you combine them, it gives rise to a skyrmion kind of spin texture. So let's come to the dipolar system. We were not very aware of the system till this paper came out by you from Tokura's group. And he studied this scandium doped barium hexaferrite, which is kind of an old material. And he showed that there are these stripe phases, and as you apply field, it then breaks into so-called this, what I will call as bubble structures. And it was kind of thought to be as like a bubble structure. And then he used Lorentz TM, which is kind of an acknowledged way of understanding this skyrmion texture. And he showed that there indeed, these are not really bubbles, but rather they are skyrmions. Although I must say that lately there is papers that claim that within the same group theory, skyrmions and bubbles can be treated in a similar manner. And then they form as a hexagonal lattice. So we saw this, and we were working on iron gadolinium thin film for a different reason, because iron gadolinium has a compensation point where the iron and gadolinium, they are ferrimagnets, so they suddenly compensate. And I was very interested in studying that. But fortunately or unfortunately, I don't know. What happened is that when we put a beam, we suddenly saw this 6-fold hexagonal pattern. And I'm come to the story in the next slide. But basically, let me just describe the sample is grown from the group of Eric Fullerton at UC San Diego. And it's a ferrimagnet, as I said, and it's basically a multi-layer structure. And we are doing soft X-ray resonance scattering in the transmission mode, meaning this is the sample. We will apply a B field. The beam will come. The beam is sigma polarized light. And then we are just going to measure the scattering pattern as a function of it. So this is what we see at B equals to 0, so at the coercive field. And you can see this beautiful diffraction pattern coming out of the magnet. This is purely magnetic scattering coming out. All it means that there is a structure, most likely like a magnetic structure, which is almost like a grating like. We are seeing almost like fourth order of diffraction pattern here. And then as we increase the field, it slightly distorts. It looks like to me that it's becoming like a two-fold symmetry, and then finally this beautiful hexagonal pattern that shows up. And by this time, we kind of thought that it may be like it's a skyrmion texture. If there is no way to know that this is skyrmion because it could be bubble too, as I said. And at that time, we were not very even sure that whether bubble and skyrmions are exactly same or exactly similar. And I think that controversy still persists. It's not very clear yet. So then we went to Guehne because we saw this, and James actually calculated out the structure factor of this, and he showed that these are indeed skyrmion-like strain texture. But to get a confirmation, I'm just going to play this movie, and it's an LTM movie of as a function of field. And you can see that how the stripes slowly morph. It goes through various different phases, and finally morphs into, this is the portion where you should pay attention, and becomes skyrmion. So if I take some snapshots, then you can see that we see various different things. We sometimes see bubbles, we sometimes see skyrmions, depending on the field history and the field condition. And sometimes we even see this kind of a pairs, which we call as skyrmion bound pairs. So what happens is that this is because this is a dipolar interaction, there is no global chirality in the material, of course. So locally, we can find out like this chirality is one when we can see immediately this one, which is going in the opposite direction. So obviously, there is no fixed chirality as we would see in a DM interaction basis. So, and then from there, we made the phase diagram, and then ultimately the phase diagram can be really made into schematic like this. So there's a disordered stripe, then there's some ordered stripe at high temperature, and then there's this skyrmion phase as a function of H and T. And then one of the questions that we were asking is that what is happening at this point, where three of the phases are coming together. And kind of I went back and looked at Parbach's paper back in, I mean, there are many such papers, but this is the one that we looked. And we found that this is a kind of a, well, I won't say it's similar, but it is reminiscent of this kind of work where there is a ferromagnet, paramagnet, and the modulated phase. So question is that what is really happening at this phase? Let's put coherent beam to this, and then you can see that immediately we start to see speckle patterns in this beam. So there's basically it just means that there's a heterogeneity in the sample. And then what we did is, this is one of our main results for this part of the talk, is that what we are doing now is that we are measuring this speckle pattern as a fine variation of field, and we are correlating data at field 1 with data at field 2, data at field 2 with data at field 3. And because it's correlation, if nothing has changed, then the correlation coefficient is 1. But the moment there is a change, the correlation coefficient dips. So if the domain suddenly go through big changes like avalanches or jumps, then the correlation coefficient is supposed to just dip. So this is exactly what you see as a function of one field scan. You have these huge jumps, which are completely arbitrary, has no specific length scale attached to it, and they are completely random. And we did this for both stripe phase, where we see a big changes. In skyrmion phase, we see very small changes. And then we took this data like 1,000 times each one, and then we made out the distribution curve. We can also plot the fluctuation as a function of temperature and field. And if it is a kind of a phase transition, then we assume or we hope that this fluctuation will peak. So you can see that at least this is the point where it is peaking up. It's not exactly this point, but very close to this point. And so this is kind of peaking up. And then in skyrmion phase, of course, we don't see any particular change, variation, because it's just a single phase, a topological phase that doesn't change. And then what we did is that we had a measurement below TC and above TC, and then we were able to, and then also below HC and above HC for both the stripe phase and the skyrmion phase. And we were able to put them together on one curve. So we did the curve collapse. This was actually mainly the work done by Karina Vila and Karina Damen from Urbana-Champaign. And they were able to make this curve collapse, and finally were able to get the critical values for this kind of system for both the skyrmions and for the stripes in iron gadolinium. And this was our first work, and we are just following up this work with iron germanium, which is actually a very interesting skyrmion material, and we are doing similar thing on that. So with that, I'm going to change a little bit gear and go to this pulse square mode. So that was the spatial variation correlation, and now in the temporal correlation. How much? 11 minutes, 10 minutes. Yeah, okay. So good. So this is so how do we measure temporal fluctuations directly? So in the morning we heard that how the CDW fluctuations were measured, and they were measured from a basically static measurement, basically S of Q. And whenever there's a fluctuation, the diffuse scattering part goes up. This is very well known. This is slightly different. Here we are trying to tackle the fluctuations directly. So let's say there's an ensemble or there's an enclosure where there are particles that are jiggling around. So their numbers are not changing. So the total number of particles is conserved. So if we measure a time average curve, this will remain same forever. But these particles are fluctuating. So if you now measure coherent diffraction from it or scattering, so they will give rise to speckle, as I said. And then these speckles, for example, these black lines are constant Q contour, and you can take a small Q contour and you can see these are also fluctuating because that is fluctuating. And then you can calculate the autocorrelation function. So we can take a time series, calculate an autocorrelation function, and that autocorrelation function is nothing but S of QT, which is the structure factor as a function of length scale and time. So by doing this measurement, we will be able to get the evolution of a sample as a function of length scale Q and a time T. So this is a traditional way of doing XPCS, but the synchrotron based XPCS is limited in time. And that's because of various different technical reasons, not rather scientific, but the technical, because we don't have that much coherent flux, we don't have that fast shutters. So we were thinking of how to do this in a much faster timescale, beating the synchrotron itself. And so then way before us, of course, this is an idea from Gerhard Grubel, where he said that, okay, let's go to LCLS, or for that matter, XFEL, and then you can divide the beam. You can split the beam into two and then get the time delayed pulses and get the speckle pattern. So we said that, okay, that's a pretty interesting idea. Then we can also do a similar thing. And then therefore we went to LCLS and we developed our own scheme. We are not putting a mirror, but we are doing this. So the beam is time delayed from the accelerator itself. So we are not really splitting the beam using a beam splitter, but rather the accelerator is giving us a pulse pair, and that delay can be varied. So what we are measuring at the end of the day is a speckle pattern due to these two pulses. So if nothing changes in time delay tau, then both the pulses will give rise to the same speckle pattern. And if things have changed in the time period tau, then the speckle pattern will move, and we will lose contrast, right? So by measuring the contrast as a function of this delay time, which is an idea given by Christian Booth and Stefan H. A few years back, we basically can map out the dynamics at a time scale given by the delayed time tau, which is coming out of the LCLS. So now so basically this then is really limited by the XFEL time delay. And that's how we are going to pretty fast time scales, as I will show you. And then we have started this experiment, doing this experiment, and we have done just 3 beam times so far, which is quite a bit in LCLS timescales. And we are now thinking of coupling with excitations, say laser and things like that, to study nonlinear effects too. So this is the same FEGD sample. So this is some of the earlier data, just to convince you that we are getting the data that we are supposed to get. So this is, for example, okay, so those who are thinking that what the heck is this? Because it's an important point. This is the Andor camera that we are using, but the Andor camera cannot run very fast. It can only run fast in a 90 by 90 pixels. So what we do is that we mask out everything and we just take this corner 90 by 90 pixels. A small technical detail, but very, very important one. So anyway, just to show that this is the stripe phase we got, and this is the data for a pretty much 1 second average at the LCLS, and then this is the skyrmion phase that we get, and this is again the skyrmion 190 by 90 second data. So some technical detail in the sense that this is how every shot looks like. So this is very, very sparse, of course. So first step is to convert this sparse data into a using this droplet method into photon data, because this is a CCD and they don't collect photons, they collect CCD charges. So we change it into photon. From there, we find out in the ADU terms the photon peaks, that how many photons per speckle, and from there we calculate the probability of photon per pixel and blah blah stuff. And ultimately, we go to this contrast 1 over root m, from which we decide the contrast. And this was our first result. And I would admit that there are very good for this sample that the points are very, very sparse, just 4 points, but that's what LCLS is. It's very hard to get time there. But anyways, I should not complain. So this is the kind of the skyrmion peak data that we got, and this is the stripe. And I think one thing that is for, and we can say with certainty, is that, with some certainty at least, is that near the stripe skyrmion phase, the dynamic, these fluctuations are much faster. We are not seeing any, like they are beating the nanosecond timescales, whereas in the skyrmion, they are about close to 4 or 5 nanosecond time delay. And this kind of mirrors or complementary to our earlier measurement that I did with Matt Langner and Bob Schenlein at LCRS, where we did a pump probe study on a similar skyrmion system, where we showed that the skyrmions somehow are slower in dynamics than stripe dynamics. And then we followed this up. Then because of this problem of the end station and everything, we actually have a new end station that we got with help from mostly from Yorgi. And then we have this new nice detector, I think from European XFL, the PNCCD. And now we can take all the data together, all the hexagonal pattern, as you can see here, beautiful patterns. And we basically remeasured all the curves with Matt, with Seberg now, Matt Seberg and Vincent Esposito. And we reconfirmed that, okay, this, whatever we said in our earlier PRL is right. And many, many other experiments are also planned. You may ask that where are we going with our fast XPCS? One of the reasons that I was very interested in doing fast XPCS is because of this connection to RIX. So XPCS is a sub QT and RIX, as we all know, is a sub Q omega. And one of the idea was that can we really match up? Can we come together from the two sides and come together? It seems pretty difficult even now. And I'm not sure if that's going to ever happen or not, but definitely we can come close to the picosecond time scale. Probably we will never be able to go, although the accelerator guys at LCLS tells us that they can time delay in several hundred femtoseconds. And we haven't gotten that time yet, but if we ever get that time, that will be very cool to do. So that's where really we are going, that can we do something which is complementary to RIX, but in the time domain directly, and because we can now think of doing something in femtosecond time scales. And then, of course, the other big idea is that can we go beyond G2? So this spontaneous fluctuations that we are measuring as of now is just temperature dependent. There is no excitation here, but we can think of putting an excitation, say, pump it with laser, and then measure correlation. So I'm done. This is a shameless advertisement of a new beamline that we have at the Advanced Light Source right now. And it's actually a coherent X-ray scattering measurement where we have a feed and we can go to low temperature. We have light and we are doing commissioning. So any one of you is interested, please let me know. We will be more than happy to collaborate with you. And with that, thank you. This is the view looking out of the San Francisco bridge. Sorry, you can't see the bridge, but believe me, there's a bridge. Those who have gone there, they know it's a bridge there, and this is our fantastic light source. So with that, thank you very much.
Thank you very much.
Yeah. No, it's actually no, as the idea is similar. The accelerators themselves, they do the undulator in a way that the two pulses come out. So it's not really splitting a peak, but even from the electron bunch, these two things come out. Yeah. They are separate coldly. When they're coming to the mono, these are two pills. Okay, I think one, so not two. So between pulse to pulse, so the two pairs, I should show you, maybe I have something to show you how they look. Let me see if I have a thing to show you at the, maybe not. I have actually used to have a slide where I show that how every pair looks like, and they are within one pair with two peaks. I see your point that whether the coherence is different. No, they are not. As I think, yeah. Let me understand correctly. You are saying that it's a very similar. I think I think the bigger question that probably you're asking, and which is something that we should be very concerned, is that the method doesn't work, we know, if the intensities of the two are varying big time. Yeah, so each one is, I think each one is, if the best I know, is quasi-independent for sure, because there are cases where each pulse is very, very different. Yeah, yeah. Oh, that I did not say, of course. This is like 90% data thrown out. Just the most balanced ones. Yeah, we have been struggling with that. Yeah, that's a very good point, actually.
Okay, another question?
Wait a minute, let me understand your question. You are saying that whether this thickness is important or not? Yes, it is. At least my experience is that this has to be very, very tricky. If this goes a little bit lower, well, low is very difficult, but if it goes higher, it doesn't appear. Just stripes, nothing else. And we have not been able to get, you know why they are so thin is because the compensation point was beyond 400 Kelvin, which we could not reach. So we started thinning down so that, and the compensation started coming down. It came to 320, and then suddenly the lower thickness showed this. So I actually don't know. We have never gone on to study the compensation point, but I do know that these things don't show compensation, and the compensation happens at higher thicknesses. Okay, that's a very good question. So we have other studies where, so this one we are applying along the field, but to get highly aligned, we need a small in-plane field. If you don't apply a small in-plane field, then you always see a ring of scattering. Basically, it's a labyrinth domain. To get a very aligned field, we have a small, very small in-plane field, along with a bigger perpendicular field. And that's what, and then after we do a kind of a voodoo field protocol, in the sense we go to plus saturation, minus saturation, and then quench it to the zero field. And then we suddenly see this. And this is a pretty repeatable thing for iron galvanum.
Okay. So,
thank you.
Let's thank again the speaker. Thank you very much. So, move to the next speaker. Fermin, first name is
Remco.
Remco.
Yes. Okay. Let me see. This
so
is the
23 minutes plus 2 questions.
Yeah, sure.
Okay. So let me introduce you Fermin. Superconducting people at deep currents in spin texture thermomagnetic.
Right. Yeah, thank you very much. I'm going to talk about, like I said, I'm going to talk about these rim currents, and those are spin polarized supercurrents that are running along the edges of our devices. And not they shouldn't be confused with any topological effect or edge currents, since they have nothing to do with topology or band structure whatsoever. And that's what makes them special. This work was carried out in the University of Leiden in the Jan Aerts lab, together with supervision of David Lahabi. So, as you know, in a superconductor, electrons pair up in Cooper pairs, normally of opposite spin. But in a ferromagnet, all spins tend to align. So how do we combine these two processes? The answer is triplet Cooper pairing, where the electrons pair up in spins of equal, in pairs of equal spin. And during this talk, I will try to convince you that we can generate these long-range triplets using the spin texture of microstructured devices. But first, what are these triplets? Well, let's first examine the standard Cooper pair, which is the singlet Cooper pair. Such an object has a spin quantum number of 0. And therefore, in direct notation, we can write down the Cooper pair wave function basically as follows. Then such a triplet Cooper pair has a spin quantum number of 1, and therefore it can be decomposed in 3 different flavors, basically, depending on the projection along the quantization axis. So first there is the M0 triplet. This is the type of triplet that doesn't have any projection along the quantization axis. Then there's 2 more variants. Those are the ones that are truly spin polarized. And these type of triplets, they can actually penetrate the ferromagnet over longer length scales. So those 2 are the ones we're looking for. So typically, these 2 are called the long-range triplets, since they can penetrate the ferromagnet over long length scales, whereas the short-range triplets, they cannot penetrate the ferromagnet over long length scales, and they scatter basically over long length scales in a ferromagnet. So how do we generate these long-range triplets? To answer that question, we have to take a look at the interface between a superconductor and a ferromagnet. Naturally, at the interface between a superconductor and any material, there is a decrease of the amplitude of the wave function, the superconducting wave function, that you can see here. But due to the process of spin mixing, which is basically spin-dependent scattering at the interface, there also naturally emerge these short-range triplets at the interface. If the ferromagnet is actually a strong ferromagnet, then not only the singlets decay in the ferromagnet, but also the short-range triplets decay in an oscillatory fashion. But in a strong ferromagnet, they roughly die out in 5 nanometers, so very quickly. Then if we combine spin mixing with spin rotation by having a non-collinearity of the ferromagnet at the interface, for example, shown here by adding a second ferromagnet that has this non-collinear magnetization with respect to the main one, then we use the process of spin rotation to transform these short-range triplets into long-range triplets. And basically, this is done by rotating the quantization axis, and therefore, naturally, these Cooper pairs have a spin projection along the quantization axis and are allowed to pass into the ferromagnet. And in a strong ferromagnet, this typically can happen over micrometers. That was the theory behind it, but this has also been shown experimentally over more than 10 years ago. For example, by one of the co-organizers of the workshop, Jason Robinson. He used stacked junctions that contain holmium, and holmium has as a natural property that it rotates its magnetization direction along the z-axis of the material, and therefore naturally it accounts for the spin rotation and it generates long-range triplets. It was also done using synthetic antiferromagnet stacked junctions, where the non-collinearity is basically there by design. In the 10 years after these 2 experiments, this was researched much more, and by now this is very well understood how these processes work, and it's very well understood how to generate long-range triplets. But there's also an alternative class of proposals on generating these long-range triplets, and those are based on the spin texture of a single ferromagnet. But experiments are rather scarce when it comes down to these type of proposals. So our approach to tackle this is using spin texture devices in the shape of disks that are made from bilayers, where the bottom layer is cobalt, a ferromagnet, and due to the shape of a disk, naturally a ferromagnetic vortex is present in the sample. And a ferromagnetic vortex is characterized by all the spins lying in plane in a whirlpool-like fashion, and except at the core, the ferromagnetic vortex core, there the spins stick out of the plane. And the top layer is niobium, and in the middle of the top layer, we remove locally the material, and that creates a Josephson junction between one electrode and another electrode, and thereby we force the supercurrent to pass through the ferromagnet to reach the other side. We fabricate these devices using focused gallium beams, and not only to structure the sides of the device, but we also use those beams to structure this trench, and this trench acts as the weak link, where we remove all the niobium, and therefore the current has to pass through the cobalt. Right, let's see if they actually are junctions. Let's see if they actually work. Well, the answer is yes. First, if you pay attention to the resistance versus temperature, here the blue curve represents a disk without such a junction. There we see a single transition corresponding to the superconducting transition of the contacts, basically. But if we fabricate a trench in such a device, then we see an initial transition here in the purple curve, but there's also a second transition, and that corresponds to the proximity effect of the weak link. So where we basically proximize the ferromagnet. And at low temperatures, there is a zero resistance state with a proper IC and everything attached to it. And to show that these are actually junctions, we also obtain the Shapiro response of our devices, where we apply microwaves to the samples, and we see these quantized steps that are telltale sign of the Josephson coupling. How do we know that that actually the spin texture, the vortex spin texture, is the thing that's generating the triplets? To answer that question, we also fabricated these bar devices, where due to the shape anisotropy, the sample is magnetized along the direction of the bar. And here we used the same parameters to fabricate the weak link in the middle. And we see that these type of samples only have an initial transition corresponding to the contacts, but at low temperatures, there's no second transition and they reach a finite resistance. And if you actually inspect the curve closely, you see that the resistance at low temperatures exactly corresponds to this point where these two curves part. So that tells us that the resistance that's left at low temperatures is the resistance that corresponds to the weak link. So we didn't proximize our weak link, and we only proximize our weak link when we have a ferromagnetic vortex present. So how is this supercurrent distributed? To answer that question, we used superconducting quantum interferometry, which is obtaining the critical current as function of the applied magnetic field that is perpendicular to the current direction. And this actually nicely shows the quantum mechanical nature of superconductivity in general, since it's a nice analogy to this single slit interference pattern in optics, where there is a Fourier relation between the shape of the slit and the intensity of light that is being projected behind the slit. And the superconducting analogy here is that we measure the critical current as function of field, and we use that Fourier relation to extract the critical current density as function of location along the junction. And thereby we can inspect whether the current is distributed uniformly or not. All right, well, we fabricated a single junction, so there's no reason to suspect that the current is not distributed uniformly. So what we expect for a single junction is this typical Fraunhofer interference pattern that is characterized by a wide middle lobe, twice as wide as the neighboring lobes, and a sharp decrease of amplitude in the interference pattern. When we actually carry out the experiment, we see something radically different. We see this interference pattern that's characterized by equal width lobes, and there's hardly any decay of the amplitude of the oscillations. And what's more, what we see is that the period of these oscillations, they scale with the diameter of the disk. The top data set is obtained on a device that is 1.6 micrometers wide. And if we go to a smaller diameter, we see that these oscillations, they grow in size. So we can use the technique I showed on the last slide to see where these current channels are actually located. And we find that this typical two-channel interference pattern corresponds to two current channels that are on the edges of the device. So by doing this analysis, we conclude that these long-range triplets only emerge at the sides of our device and are only transported through the sides. We also did a couple of control experiments to verify this. First of all, we made devices with shallow trench. So meaning that we didn't remove all the niobium from the trench. And this creates a so-called SSS junction, where basically the weak link is made from a normal metal niobium. And there we see a typical Fraunhofer interference pattern indicating a uniform current distribution. And the same is true when we fabricate the device using a normal metal weak link, in this case silver. And then we also see a uniform current distribution. And that leads to the conclusion that these rim currents only emerge when the long-range triplets are present, and that this is not related to any trivial effect related to the disk geometry or some band structure like stuff. We have in our lab a vector magnet cryostat at our disposal, meaning that it can apply a magnetic field in any direction that we want. So what we can do is not only scan the out-of-plane field direction, but also apply an in-plane field to manipulate the spin texture. So when we do this, well, first at 0 in-plane field, we have a magnetization texture, which is a vortex with the vortex core in the center of the device. And we see this typical squid-like interference pattern, this two-channel interference pattern. If we start applying a 10 millitesla in-plane field along the trench of the device, what we see is that we effectively start to move the vortex core towards the contacts or away from the trench. And as a result, what we see is still a squid-like interference pattern or a two-channel interference pattern, not regarding these glitches for now. But at 0 out-of-plane applied field, we see a strong suppression of the critical current. And this tells us that we're dealing with a 0 pi squid, which basically means that there's a reconfiguration with of the relative phase between the current channels. Applying an even higher in-plane field and moving the vortex core away from the trench even further, as you can see here, then we find this peculiar pattern that is characterized by a wide middle peak, but an increase of amplitude of the neighboring ones. And this is reminiscent of a single junction having many 0 pi segments. And I would say the takeaway message of this slide is that we have large control over the superconducting transport by changing the magnetization texture, and that this is a telltale sign that we're dealing with long-range triplets. Since regular singlet currents, they will not be responsive so much to changing the spin texture. Then the question is, how do we generate these long-range triplets? Since it's not the regular method of using spin mixing and spin rotation. Well, to answer this question, first we have to remember that it's a combination between this spin texture, since without spin texture we don't generate triplets, and the edges. The edges are very important in the story. And to answer this question, we teamed up with Mikhail Selayev, who is based in Finland, and he used the UZL equations, or the UZL framework, to analyze our system. UZL equations are charge and spin coupled diffusion equations for superconductors. And he realized that you can transform this typical ferromagnetic vortex spin texture into a uniform spin texture, and then within his equations, an effective spin orbit coupling term emerges. So again, this vortex spin texture can be removed by transforming to a system that is completely has no spin gradients, and that presents us with an effective spin orbit coupling term, but that in the UZL equations appears as from the spatial derivative of the anomalous Green's function. So that you see here is this effective spin orbit coupling term emerging after this transformation. And the anomalous Green's function here encodes not only the singlet superconducting correlations, but also the triplets. It's well known for nanowire systems that a Rashba type spin orbit coupling together with a Zeeman field can produce a spin current in nanowire systems. So, and that spin current runs towards the edges of the device, and that results in a local magnetization at the edges of nanowires. A similar effect is also taking place in our devices, namely that we have a spin texture that acts as an effective spin orbit coupling, And together with the natural exchange coupling in our ferromagnet, that generates a spin current that is carried by the short-range triplet condensate. Remember, these short-range triplets naturally emerge at the interface between a superconductor and a ferromagnet. So those are also present in our devices. And at the boundaries, this spin current doesn't result in a net magnetization. Rather, it is being transformed into long-range triplet correlations due to the boundary conditions of the UZL equations. I'll show this in a bit more graphical way, in the sense that, so we start out with these short-range triplets. Those are shown like these type of Cooper pairs that don't have any spin projection. And this is in the absence of any spin texture. So this is a uniform magnetization, and we don't have any spin currents. And if we start to curve the magnetization, having a magnetization gradient, then we see that there emerges this spin current that adiabatically follows the magnetization gradient. And this is carried by the short-range triplets. Then if this spin current hits the interface between the sample and the vacuum, we find that these short-range triplets are converted into long-range triplets, and those can then be transported to the other side of the junction. Michael also did numerical calculations, and here I'm showing the geometry of the disk, and in the color coding there is the long-range triplets that emerge in the sample. And first he calculated in the absence of any spin texture, and then we don't see any long-range triplets as we expect and also as we measure. Then if there is a vortex magnetization in the disk, then we actually see these edge contributions start to emerge, and those explain the two-channel interference patterns that we actually measured. Note that there's some little notches here. Those are needed to break the symmetry, since in a perfect circular geometry, the spin currents will adiabatically follow the magnetization gradient and will never hit the boundary of the sample. Of course, in a real sample, it's not a perfect circle, because the perfect circle does not exist in real life. And that means that the spin current will always hit some sort of boundary. As is shown also here, if you displace the vortex core slightly. And then about these little notches here, we included notches, since in our real devices, there's actually a geometrical dependence on the milling rate of the sample, and that results in the fact that these real samples also have these notches. But remember that these notches are not necessary in generating the triplets, since we don't have atomically smooth edges in our samples. So also without the notches, we would have generated the triplets. There's also some open questions. That is, for example, there is also a vacuum edge here at the trench between the sample and vacuum. And why doesn't this edge actually also why doesn't this edge generate long-range triplets? Because you would expect that this is a vacuum boundary, but here there's also a vacuum boundary between the superconductor and vacuum. The ferromagnet continues underneath, but there's still a vacuum boundary. And that doesn't generate triplets, and that's not captured by our model. And also when we apply in-plane fields and we start to manipulate the current channels and have a reconfiguration of the current channels, that's also not captured yet by this model. So those are still open questions. Then I reached the conclusions. We generated these triplet long-range spin polarized supercurrents that are generated using only a single ferromagnet that has this vortex magnetization pattern. And the triplet transport is confined in very narrow rim currents that run along the boundary of the sample. And we find that we have a large control of our superconducting transport due to this spin texture. And then before I finish, I just want to advertise a follow-up work that has recently been released on Archive. There we transform these disk devices into elliptical devices. And these have the nice property that you can have a bistability of spin textures. So either there is a state that is magnetized along the long axis of the device, or there are two vortices present. So using these devices, we succeeded in creating a non-volatile superconducting memory, since these states have different critical currents. But that's just a small advertisement, and with that, I would like to thank you for your attention.
Thank you very much. So we're time for a couple of questions.
Yeah, well, for example, these samples, they can form a superconducting memory. So at the moment with superconducting computing, it's such that there exist processors that that are designed using superconducting hardware, but superconducting memory is mostly lacking or is based on volatile ways of storing the information. So, for example, persistent currents in superconducting loops can be used to store information, but once you warm up the sample above the critical temperature, you lose your information. Whereas here we encode the information into the ferromagnet, and you only lose the information once you go above the Curie temperature, which is way, way higher. So you could store it at room temperature and cool it down later and still have your memory. And the other application I would say is possibly neuromorphic computing with superconductors, using these ferromagnetic vortices, since they can be coupled using RF waves. But this is maybe a future outlook.
Please.
Yes, that's correct. Yeah, that is correct. That is the, to repeat the question, sorry, like what? Neurons. Oh, but I think these are simply regular vortices, but they have either, basically a polarity sticking out of the plane or into the plane.
But in the center of the vortex, you have a component out. So this to me is looking a little bit like a neuron. So like someone should calculate to see if there's any chair number associated with it.
Do you mean that since there are also these lines going, these spin textured lines, or is it because? But there's a lot of works discussing ferromagnetic vortices, and especially the reversal of the vortex core that was proposed 20 years ago to use as a storage of information as well within spintronics. So these are well studied. But the nice thing of this proposal is that we do not change it doesn't matter the polarity, since we look at the difference between a magnetized state and a state that has vortices. So that this is relatively easy to switch between those, and it's hard to switch the vortex for polarity.
Thank you again.
Sì, l'avevo già detto, però allora dove sta? Qui sta dicendo lo zoom, non lo vedo zoom, dove sta?
Però ci abbiamo proprio attivato perché.
Andrea, can you hear me? I'm trying to share my screen. I'm trying to share my screen, but it seems like
I to share your screen. So now the last talk of the session by Igor Babaev. So let's see. Just a moment. No.
Right.
Okay, now you should share your screen, Igor. Sorry to be late with the session, so we are starting a little delay your talk. Okay, so we can see your slides. State with the spontaneously broken time reversal symmetry above the superconducting phase transition.
Great. Can you see my cursor of my mouse?
We can see your we can see your screen, but not your
cursor. Okay, let me then just something malfunctions. Then I will try it this way.
We can see your pointer now. Good. So you can go to full screen.
Yeah. So let me then try this.
Which side? No, or view. View. Perhaps on view you have the possibility to go on full screen.
Yeah, let me see. So is it? Yeah. So is it good? Let me see.
Try 300. Try 300. Okay, that is fine. We can.
Yeah.
No,
Okay. Good.
It's not this cutting the bottom part. It's better 200.
Oh, great.
Okay.
Yeah, so,
okay. You can go like that. Okay. Okay. So you have 23 minutes plus 2 for questions. Okay?
Oh, good. Oh, good. Yeah. Yeah. Thank you very much for inviting me to talk about this work. I'm really. I would really love to be in person, so I really very much enjoy my every visits to Italy, and I'm missing being in person at this conference series. So officially I couldn't come this time, so I will talk mostly about this work with large number of experimentalists and some theory collaborators. And fortunately, the lead experimentalist, he could not participate also this year, but I will be able to cover only a small part of the experimental data that Vadim Gridenko and collaborators obtained. So hopefully there will be some kind of other occasion where Vadim could present full setup of data. I will just only scratch it on the surface. Okay, so let me first start with an overview. So let's see. Oh, now it did not go to the next slide. Okay, let me then try to improvise. So, all right. So let me try to improvise slightly. So, okay, what do we know about ordinary phase transition in a superconductor? So, in a superconductor, so there is usually single critical point. So system goes from normal to superconducting state, and above the superconducting phase transition, there could be fluctuations, pairing fluctuations, but that doesn't constitute different state of matter. That's just some precursor pairing fluctuations. And all kind of super properties that were explored in the last century, they contained, they were all one or another type of fermion pairings, spin singlet or spin triplet. And if one takes the usual BCS theory, then within strictly that theory, there is no easy way to get fermion quadrupling. For example, electron quadrupling, it is neither energetically nor entropically competitive with fermion pairing. So this experiment, the main claim of the experiment is that we observe fermion quadrupling condensate, some condensate where the order parameter is fourth order in fermions. So let me first start with some the very simplest early works that consider the very simplest examples of how one can overcome the limits of the standard BCS theory and make realistic for fermion condensate. And basically, this simplest examples is just to get the essence of the argument. This involved so-called U1 cross U1 two-component theory. So there were two ingredients needed. One ingredient is that system should break more than one symmetry. That's very common, and there's nothing unusual about it in superconductors. And the second ingredient, second necessary ingredient, is that mean field theory should not be valid. So basically, the way it works is can be outlined as follows. So if we have a superfluid, then if you look at the superfluid phase transition, that is proliferation of superfluid vortices. Then we have basically in the neutral system, we have kinetic energy just gradient of the phase, and then one has a vortex, and we all know that the vortex has logarithmically divergent energy per unit length. In the superconductor, as was essentially first shown in before 1950 by London, is that if we have later by Brigosov, if we have a phase winding, so a fluxon in case of case of London, or vortex in case of Brigosov, then if one encloses one flux quantum, then one can get vector potential compensating the asymptotically the gradient of the phase, and then vortex has finite energy per unit length. So like if you have type 2 superconductors and beyond mean field, the phase transition is the proliferation of vortex loops, and the interaction is short range. Now, if we have like multi-component system, and let me think about the simplest possible. That was basically first that was considered in the case of fermion quadrupling condensate. Then we have, let's say, two complex fields, psi1, psi2, and they are coupled by vector potential. And let us for a moment neglect all other possible interactions, like no intercomponent Josephson coupling, just the simplest possible. And then if we like ask what is the phase transition, what is the fluctuations, we need to understand what is the elementary vortex excitation. But before that, it is useful to rearrange variables in a slightly different way to basically extract the gradient of the phase difference and gradients of the phase sum. And then from this, we immediately can see that if there is a phase winding only in one phase, only say in theta 2, then this kinetic term, it resembles kinetic term of a superfluid. So vortex, elementary vortex, the simplest vortex we can construct, the vortex with only one phase winding, it has logarithmically divergent energy because of this term is similar to kinetic term in a superfluid. But if you have phase winding to pi in phase 1 and phase 2, then this term cancels out. And the phase sum can be asymptotically gauged away by vector potential, so that so bound states of vortices, bound states of elementary vortices, now the composite vortex, it has finite energy per unit length. So as soon as you get to multi-component condensates, then we get, in case of superconductor, very interesting situation that a bound state of vortices have lower energies than elementary vortices. And then, like about 20 years ago, it was first observed as a consequence of this type of energy scale. It actually it requires quite a bit of work to show that. So it's not just this simple energy argument, as you can guess, because one should take into account entropy, and this is complicated. But in principle, like this is some early papers that consider it in connection with liquid metallic hydrogen situation, that there could be a state. Let me just focus on one state where bound states of forces proliferated. So let's say you have 2 dimensions and bound states of composite vortex and composite anti-vortex proliferated, but not individual ones. And in that case, you have a situation where the average of the individual order parameters is 0, but the average of the products of the order parameters is non-zero. And the product of the usual order parameters, so each of them is second order fermionic fields. So, and in that case, this is a quartic condensate. So this was the early example of how to overcome the limitations of BCS theory and to get a quartic condensate. And then, so in this example, for the arrows, they show angles. The angles corresponding to arrows are phases. And then in this case, individual phases are disordered, but the phase differences ordered. And to characterize the state, the simplest order parameter is requires to be constructed out of 4 fermionic fields. So this is some kind of 4 fermionic condensate. So let us get now to superconductors. To these superconductors, iron-based superconductors, they have at least 3 bands. So and then one needs to, in contrast to some systems like nuclear superfluids or metallic hydrogen, projected states in metallic hydrogen, one needs to take into account interbundulus uncoupling. So these are these terms. So bilinear in fields. And then, so these are just interbundulus uncoupling. And then if, for example, the they are proportional to cosine of the phase difference between bands. Phi ij is phase difference between gaps living in different bands. And we have 3 components, and these terms want to log phase differences between each 2 bands by 2 pi. And one cannot log 3 phases to pi phase differences, but the compromise solution is some kind of like this type of configuration. We have 3 phases, and then so these are two possible configurations that minimize the frustrated Joule-Thom terms, and they are related to each other by complex conjugation. So this type of superconducting state it has additional 2-fold degeneracy, and this 2-fold degeneracy is so these 2 states are related to each other by complex conjugations of the fields, and that is like time reversal symmetry, and this is so-called S plus IS state. So in this compound, the S plus IS state was expected for a long time, and mean field phase diagrams were calculated by many people, and this is just one example of how mean field phase diagram looks for this type of compound. This again phases. And on one side, one may have so-called S plus minus, so phase difference is pi, and then here are like 2 components only survive. And here it is S plus plus phase difference in this example between red and blue is 0. And then in between, as you go from one to another, it's rather generically there forms this S plus IS state that spontaneously breaks time reversal symmetry. There's 2-fold degeneracy in the phase locking. And if you stay at the level of standard mean field BCS theory, this additional Z2 transition, associated with broken time reversal symmetry, it is always below the superconducting phase transition. So if one works hard and super fine-tunes parameter, at most one can reach degeneracy in the phase transition where time reversal symmetry is broken and where superconductivity sets in. So basically, Andrea, how many minutes do I have? May I double check? Oh, okay, I can hear. Anyway, yeah, I will continue. Just alert me, Andrew, if I will be running over time. So, but if you get beyond mean field approximation, then so that was like about 9 years ago. There were Monte Carlo studies of the same model beyond mean field approximation. So then one can discretize it in the and include fluctuations in the 3-band London model. So this is like fairly simple model, 3-band London model, and then the phase diagram looks very different from the mean field theory. There is so here, if one has coupling constant, which is just inverse of the electric charge squared, and this are the units where electric charge is just the coupling to gauge field, is just parameterizes basically the magnetic field penetration length. So essentially, when the magnetic field penetration length is short here, so there appears a phase. So there at high temperatures, there is no odor of any kind. And then as the lower temperature one first goes into the state where the odor is only in the product of the gaps, of the superconducting gaps in the original field, but individual phases of the individual gaps are disordered. And this is this Monte Carlo demonstration of the possibility of for Fermion condensate. And now the experimental data on this compound that Vadim and collaborators obtained. So the upper line is the superconducting phase transition, which is defined through the magnetic susceptibility measurements and zero resistance transition. And these other symbols, these are symbols associated with detection of spontaneous magnetic fields in muon spin relaxation experiments, signaling the spontaneous symmetry breaking. And what is most interesting is the following. So if one is outside of this domain of spontaneously broken symmetries, one has a quite usual situation where the specific heat jump shown in these circles, like it's washed out specific heat feature. It well correlates with diamagnetic susceptibility. So, like in a compound which is not. Was there a question? I could not. Was there a question? Okay. So, and then most interesting case happens for just in the middle of this dome. You see specific heat shifts by basically 2 kelvins from the transition where any kind of diamagnetic susceptibility sets in. So that means there is some kind of bound state formation, but there's absolutely no sign of any kind of diamagnetic susceptibility. And that is first observation. Then, so basically, if you look at this data, so this is like spontaneous magnetic fields in the muons, we see that they are, spontaneous magnetic fields appears well above the superconducting phase transition, and it's approximately the same where a specific heat feature, this washed out specific heat feature sets in. And this shifted by a couple of kelvins to diamagnetic susceptibility set. And also the resistive transition is also only at this point. And so this was the first set of results. And then Vadim and collaborators made search for additional evidence for spontaneously broken time reversal symmetry. And they measured spontaneous Nernst effect and got measured Nernst effect and got spontaneous Nernst effect, so shown on this picture, which it also sets in well above superconducting transition, and it correlates well with the onset of muon signal indicating spontaneous magnetic fields. And so there is a lot more data that, and Andrea, how many minutes do I have? I guess I don't have that many. Is there a...
You have another 6 or 7 minutes.
Oh, do I have still 6 or 7 minutes? Oh.
So it's 23 minutes plus questions.
Oh, okay, good. Yeah, then okay, then if I have 6 minutes, then I could I could cover the experiments much more. That's thank you. Mm-hmm. Right. So basically, so what happens is that around this doping, first signature of the specific heat, and that were measured on like several instruments and also samples of different sizes. So you see there is like one really small sample measured and larger samples. So we have this shift, and this like at the onset of this pretty much for the sample around doping around 0.8, we see the onset of spontaneous magnetic fields and onset of spontaneous Nernst signal. So then also other thing that we see that was reported in the first paper is that in ultrasound probes there are two singularities at this also at this temperatures that signal for two kind of two phase transitions. What was actually less present in the original specific heat data. So here one cannot really distinguish any hints for two singularities in the specific heat. We actually later could see two sharp kinks in the specific heat in external magnetic field, but not in zero magnetic field. But now it's slightly different doping. Our experimental colleagues were able to find better crystals. So now, like at around 0.75 doping, we see the even in zero field, two specific heat signatures, and also so the first specific heat signature, it correlates with the onset of spontaneous Nernst signals, and so indicating the spontaneous breaking of time reversal symmetry, but there is no at this point there is no zero resistivity transition and no magnetic. So this is not the resistance. The black curve, the blue is the diamagnetic susceptibility. So and then it's also like instead of diamagnetic susceptibility, it closer to the zero resistance transition that coincides with the second feature in the specific heat. So and like another important aspect, so I'm moving now to my conclusion, is that both of these temperatures, the temperature, the onset of the spontaneous Nernst signal and the superconducting phase transitions. So they are both suppressed by applying external magnetic field. And so just from ordinary Nernst effect, etc., we see that there's large region of hinting for large region of superconducting fluctuations. Then just a couple of kelvins above the superconducting phase transition, we see evidence of spontaneously broken time reversal symmetry, and that means, like from what I outlined, the spontaneously broken time reversal symmetry means onset of non-trivial phase locking between the bands. And so to plot angles as to plot arrows where angles are given by the phase, you can visualize this type of vortic metal is as a state where individual phases are disordered, but there is a phase, non-trivial phase locking, and this phase locking is the 2 degenerate. So then the only way to assign another parameter to that state is to construct it out of 4 fermions, and that is the other parameter, which is like psi or delta, if you wish. So it's essentially other parameter for non-superconducting state that breaks time reversal symmetry and has spontaneous magnetic fields, but no diamagnetism. Is the other parameter is delta in one band multiplied by delta conjugate in the other band, and you can construct it out of 3 or more bands. This is for fermionic encoder parameter. So hence our conclusion is that this is the evidence for the 4 fermionic condensate, which is not superconductor because of here it is delta times delta star. So this is not a superconducting order parameter. So its order only in phase difference is not coupled the same way to vector potential as in superconductor. It's coupled in a different way. And actually one can write analog of Ginzburg-Landau model for this state, and it will have the form of actually Skirmy model. So it is non-trivially coupled to magnetic field, but a different way than superconductor without diamagnetism. And that's it, I guess. Am I badly over time, Andrea?
Okay. So, okay, thank you very much, Igor, for your talk. And okay, so thank you, speaker. So if you like to have a question, it's better to come here. Otherwise, Igor will not hear you. Sorry for that. After that, we have the coffee break, so we can let me go. Yeah. Okay. So Luis Balicas will have a question for you, Igor.
Thank you.
By the way, he can also see you.
Okay. Yeah, I don't know if I want him to see me, but that's okay. So the question for you is, what makes barium, potassium, iron arsenide so special? Why don't we see this in other compounds? And because everything seems that are strange in iron selenide. So the 1 to 2s have electron hole Fermi surfaces. In iron selenide, it has just electron Fermi surfaces. Can you comment on that? Why we have not seen this in other superconductors? What is so special about the iron 1 to 2s?
Right. So it could be. I don't think there is anything like super special about that. So it could well be that there are more compounds with this type of states. So essentially 2 ingredients are needed, just more than one broken symmetry. And recently there's a lot of superconductors discovered with broken time reversal symmetry. So that condition will be met by many materials. And the second thing is that, okay, there are caveats. So let me give you a two-tiered answer. So, and the second aspect is that fluctuations should be strong. Now, so what I just said is very true for actually low-dimensional materials. So I guess in low-dimensional materials, that phase is relatively easy to get. It is a little bit harder in 3 dimensions, and it seems that there might be like third requirement needed. There should be what helps is some kind of mixed gradient terms between the order parameter. So it is a little bit harder to split this phase transition. It might be that for this compound there is like additional ingredient at play, but I don't have like good kind of generic prescription. I don't have essentially very good answer except saying like it is much more generic in low dimensions.
Okay, so, thank you.
I wouldn't want to oversell.
Thank you very much. Other questions? Just time for another one. Can I add one if no one else? And so I'm curious, I don't know if it's a relevant question. What about the consequence on the single particle excitation spectrum of the switching on of the fourth order parameter, I mean the quartic parameter? Is there any consequence on the excitation spectrum?
Right. Yeah. So there are some discussions now. So there are like now many type of just if I try to put it in a slightly more generic form, there are like now many type of for fermion ordering being discussed. So charge for E superconductor is another type of for fermion ordering that forms via a similar mechanism. Then many other type of for fermion you can construct more for fermion ordering. And then this one of the discussion is whether or not the system is gapped or gapless. So that question was not really well investigated, I would say.
Okay.
So it seems the prevalent opinion is that these are gapless. So for fermion order is gapless. I think the prevalent opinion. There was like one article recently making stronger statements that charge for E superconductors gapless. So that's like some stuff.
Okay, thank you very much, Igor. Other points, other questions? If not, we can thank again the speaker for his online talk. Very nice. Everything was very clear, Igor. Thank you very much.
Thank you.
And now
thank you for inviting.
Thank you. Now we have the coffee break. Thank you. Bye-bye, Igor. Keep in touch.
Thank you.
Bye-bye.
Bye.
Good morning. So, okay. So we see you and hear you very well. So please share your screen. Steve Carlson will be the chairman of your session.
Okay, you're doing 22 and 3?
20?
You're doing 22 and 3.
22 minutes. 22, yeah, 22 minutes for the talk and 3 minutes for discussion.
Okay. Okay, should we start?
Okay, please.
Okay. Sorry. Hi. Okay, so we're ready to go? Okay, so the first talk is by Erika Carlson, and I don't see the title, and we're doing, there we go, critical pneumatic correlations throughout the superconducting doping range in bismuth 2201. And we are doing 22 minutes of the talk and 3 minutes questions. And since this is the last session of the day, it'd be very useful if everybody stuck on time. So go ahead and start.
Excellent. Thanks. Can you guys hear me okay and see the slides?
Yes, we're good.
Okay. Very good. Thanks. It's great to be invited again. I really enjoy this conference every year, so thank you very much for the invitation, and I look forward to being back in person. I will be happy to tell you today about critical nematic correlations throughout the superconducting dope range in BISCO 2201. My theory collaborators include Karin Dahman at University of Illinois, as well as some of my PhD students, Ben Philibom, Forrest Simmons, and Shuo Liu. Our experimental collaborators include Jennifer Hoffman, as well as Conley Song, Liz Main, and Eric Hudson. And we are grateful for several funding agencies supporting this work across the theory side and across the experimental side. We have a few tricks up our sleeve for classifying phases, right? We know of many, many phases of matter and many, many phases of electronic matter in particular. In fact, there's an infinite number predicted once you get to quantum Hall phases. So we need ways to classify these phases of matter. And the two main ways that we classify these phases of matter are by symmetry or by topology. And either one of those is a statement about the long distance properties and really the long time properties of the material. So for example, if you're using the symmetry classification and you're wanting to distinguish between liquid and crystal, then if you look at the liquid, I've drawn here a liquid of long floppy molecules. If you take a snapshot of the liquid and look at short distances, it doesn't look smooth. But on long distances, and when you time average it, it becomes smooth again. And so this definition that the liquid phase retains all of the symmetries of the Hamiltonian or retains all of the symmetries of free space typically, that's a long distance and long time criterion. Topology is similar. It depends on long distance properties of the system. However, these definitions of phases of matter ignore mesoscale structure, and we see mesoscale structure coming up in a lot of different materials, particularly quantum materials, particularly materials that have strong interactions in them. So I'm showing you just a few. So you have here in the upper left an example of a metal insulator transition system. This is vanadium dioxide. Right below it is neodymium nickelate, which also has a metal insulator transition. And the data on the left is taken by Dmitry Bazov's group using scanning near-field optical microscopy. And they imaged the metal and insulator domains, and they were able to see that the metal insulator doesn't transition immediately. It transitions in a patterned way, right? There's significant pattern formation in there. And the two in the upper right are cuprate high-temperature superconductors, measured via scanning tunneling microscopy. The middle one is Seamus Davis's group. The one on the right is Jennifer Hoffman's group at Harvard, and I'll be digging into that data set in particular more in this talk. But they're basically imaging stripe orientations, and the patterns of the stripe orientations seem to have a certain randomness to them, but also a lot of structure. We'll dig into that one a little bit more. And at the bottom, I have a couple of other examples, including, for example, in the lower right, strontium iridate imaged by scanning tunneling microscopy by the group of Milan Allen at Leiden. Now, this pattern formation, on the face of it, at first seems to challenge our definition of phases of matter, and we certainly need new theoretical tools for understanding all of that pattern formation. These in particular may still fit into that classification as long as we're willing to look at the spatial structure of things. So I just want to remind you what it is that happens at a critical point, at a second order phase transition. And what I've got here on the left is a test tube of two different liquids inside at high temperature. So the two different liquids mix at high temperature. It doesn't matter what they are, but for those of you who are curious, it's cyclohexane and methanol. And it starts off at high temperature around 50 Celsius, and then let's see what happens when we lower the temperature. We're going to lower the temperature on this thing, and you'll start to see some interesting things happen as the phase separation takes place. So the temperature is lowering, the temperature is lowering, and what I want to show you is a visual of critical behavior and what it looks like. We all know that as you approach the critical point, there's a correlation link that blows up, and you can see it with your eyes here. You see all that white stuff, those white tendrils are critical fluctuations, and all throughout the white region is the critical behavior of the system. Here, the correlation length at this moment in time just goes to Well, the size of the test tube, presumably it would go to infinity if we had an infinite size test tube, but it got cut off by the size of the test tube. That moment is critical opalescence, and everything goes power law there, right? Including the density fluctuations. And because there are density fluctuations on all length scales, all the way from the molecular level out to the size of the test tube, it scatters light of all visible wavelengths and it turns white for us. So this is, anyway, it's a nice visual representation of critical behavior, and we're used to thinking of that critical behavior in terms of a power law. Now, what I like about this demonstration is we can actually see the correlation length. I just backed it up a little bit because I want to take you a little higher temperature. Let's reverse this a little bit. And I want you to notice this right here. Okay, so I've frozen it in a moment of time where you can see the correlation length. The definition of the correlation length is when you look on length scales smaller than that correlation length, there's power law behavior. If you look larger than that, it goes back to exponential. And so you can see here a finite correlation length in the test tube, but all where it's white, you're seeing critical behavior. So when you look at something on length scale smaller than its correlation length, it'll look critical. Now, it also means there's fractal behavior in there, right? If the density itself has self-similar behavior, then I can zoom in on the density and zoom in on the density, and it will look the same at all those scales. So that self-similarity translates into fractals when you're talking about spatially dependent measurements. And so I want to keep that in mind in looking at the significant pattern formation that's being observed in a lot of different quantum materials. And we'll focus in this talk on stripe orientations in BISCO. This is BISCO 2201. You're looking here at a 50 nanometer by 50 nanometer field of view. And what Hoffman's group has done is they've taken a local Fourier transform to discern the stripe orientation in each region. I should also tell you this is an underdoped sample that superconducts at 32 Kelvin, but the data is taken at 6 Kelvin, so it's a low temperature measurement. And so by taking local Fourier transforms, in each region they see something that looks like either the red plot or the blue plot. So if they see strong peaks in one direction, that corresponds, we've circled those in red, that corresponds to the red regions. In the red regions, the stripes are going diagonally to the left. In the blue regions, the stripes are going diagonally to the right. And there's a lot of structure in this image. It is clearly not homogeneous, but there are tiny clusters and there are large clusters. So if we look, there's a system spanning cluster. Spanning means it connects from one side to the other. So I can take nearest neighbor steps on all the red ones and go all the way across from one side to the other. There are a few medium clusters, and there are several tiny clusters, which is a hint at a power law. And I'll show you later there are power laws in here. So we're seeing structure on multiple length scales. You can see with eye that there may be fractal boundaries in there. This boundary is not compact. It's very, very, very wiggly on many length scales. And even the interior has holes upon holes upon holes. And so my claim is that if this pattern formation is driven by proximity to a critical point, maybe it's the critical point associated with long range order of these stripes. If it's associated with a critical point, then the critical exponents, which are universal, should be something we can get out of the pattern formation. So let me give you a model now so that we can think about what fixed points, what critical points might be possible. Once you know the critical points that are possible, then you know the exponents that can come up in your power laws. So we saw that there were stripes of two different orientations, either diagonally to the right or diagonally to the left. I'll call diagonal to the right sigma equals +1, diagonal to the left sigma equals -1. That's an Ising variable. The nice thing for theorists is that there's not that much that an Ising variable can do. So we make the reasonable ansatz that neighboring stripe patches want to be aligned. That translates into a ferromagnetic coupling among the Ising variables. That's here in the first term of the Hamiltonian and in the second term. The first term is in layer coupling. BISCO is a highly layered material, so presumably the coupling is stronger within planes than between planes. And then there's a coupling between planes that we can vary. So we can take this model from the two-dimensional limit, maybe you're just seeing two-dimensional physics on the top surface, to the three-dimensional limit, maybe you're seeing bulk physics. And material disorder, you can think of that in the following way. In any given region of space, there's a disorder pattern of the dopants, and it breaks rotational symmetry. And so it tends to drag the stripes either one way, or maybe over here, the pattern is different of disorder dopant atoms, and it drags the stripes in a different direction. So we model that as a random field at each point in space. The random field is chosen from a Gaussian distribution, and the width of that Gaussian tells you the disorder strength. So if I make the Gaussian infinitely sharp, there's no disorder. As I broaden that Gaussian, that introduces more and more disorder. So that what I'm calling here random field strength is the width of that Gaussian. So the phase diagram is simple. You either have long range order or you don't. So there's an ordered phase and there's a disordered phase. This is temperature versus random field strength. The front two axes are in the two-dimensional limit. The back two axes are in the three-dimensional limit, and the interlayer coupling takes you from one to the other. But it's always a second order phase transition. Notice that you have a more stable ordered phase in 3 dimensions. That's typical. So what is the critical behavior that can come up in this model? So the critical behavior that can come up in the model is that I could have a purely 2-dimensional system. That's the first 2 axes. So I could have the clean 2-dimensional critical point. I could have the random field Ising model criticality coming in, and that's here at the limit of that is that the critical disorder strength in the random field model in 2 dimensions is 0, so it's way down here is that random field critical point. I could have a clean 3-dimensional model, and that would be the clean 3-dimensional Ising fixed point. I could have a 3-dimensional disordered model, which tends towards the 3D random field critical point, or I might have just a non-interacting model. Maybe all that pattern formation is just driven by surface physics and there weren't actual interactions between the stripes. So the question is, so these are all places in the phase diagram where you can get that significant pattern formation because things go power law, all the textures go power law at those points. And the arrows on the phase diagram tell you the renormalization group flows. So anywhere along this line, for example, if you have 3 dimensions and you have any finite random field disorder strength, then the normalization group flows towards the 3-dimensional critical point. So if the patterns are critical, so what you're looking at right now is that view of scanning tunneling microscopy on underdoped visco with a 32 Kelvin transition temperature. And you're looking at the 50 nanometer by 50 nanometer field of view, and we've colored for you the orientations of the stripes. And we want to know, can we get critical exponents out of this pattern? Now, normally when you try to get critical exponents, you need to sweep the field or sweep the temperature, but that's in the context of macroscopic experiments that average over the entire sample. Here we have spatial information, and so rather than needing to sweep the temperature or needing to sweep the field, it's like you can sweep the position and get the same information. And so so looking at these power laws, you can derive critical exponents. And something similar was done by Bianconi's group in 2010 for the oxygen interstitials and them being scale-free. So let's look at all the critical exponents we could think of to get out of here. If you think of a new one to get out of here, contact me. But we've thought of 5 so far. So there's the correlation function exponents. There are the volume fractal dimension exponents. And then you can take a histogram of cluster sizes. So I'll show you what those plots look like. So let's look at the whole fractal dimension. This would be what is the fractal dimension of that edge. And so here you count the linear size of a cluster measured by your favorite measure. We did the radius of gyration, and then you compare that to how many sites sit along the edge. If that forms a power law, then you have a fractal dimension. And so here you can see that all of our clusters are falling on this nice straight line on a log-log plot of radius versus perimeter. And it's over at least 2 decades of scaling, so that gives us confidence that there is a power law there. And so we can extract that critical exponent. I'll show you what the number is in a little bit. We can do something similar for the volume fractal dimension. This is where you compare the radius of gyration of the cluster with the number of sites that are in the cluster. I apologize for this typo. This P should be V for volume. So you want the number of sites that are in the cluster. And once again, that's on a log-log plot. That's a nice linear plot over more than 2 decades of scaling. So that gives us confidence that the hypothesis of criticality is plausible. You can take a histogram of cluster sizes. Here we did a finite window analysis because it was a small field of view. So to get the noise down, we did a finite window analysis. But the gist is that on this log-log plot, we're seeing moments of the cluster size distribution they're all falling onto these power laws. And then the correlation functions gave us a bit of a hassle, and in the following sense. The data plotted out, you would think that the correlation function you should study is the spin-spin correlation function, which here translates into orientation correlation function. And that's the triangles. They're not power law. But what is power law is the measure from percolation. Percolation has a different correlation function to look at, which would be these two aligned patches. Are they connected by nearest neighbor steps of aligned patches? And that's the circles. And there is evidence of a power law in there in the data set. But the exponent is not a percolation exponent. It's not a percolation value. And so, so it turns out, we did a lot of simulations that confirm this. Our simulations reveal that that measure from percolation physics is actually playing in an Ising model. So at all the Ising critical points that I mentioned, the pair connectivity function also goes power law, and it does so in a much more robust way. It's a lot easier to see the power law in the pair connectivity function than in the spin correlation function. And for time's sake, I'll skip a little bit of that. So long story short, we get those critical exponents out of the images and then compare them to the fixed points that I mentioned to you. We have the clean Ising fixed points, whether two-dimensional or three-dimensional. We have the percolation fixed point. I've listed just 2 dimensions because since it's non-interacting, dimension doesn't really matter except for your field of view. So it's non-interacting, so 2D or 3D would look the same in your 2-dimensional experiment. Then the random field Ising models, either in 2 dimensions or in 3 dimensions. So what you're seeing here is the circles are theoretical predictions, either from the literature or from our group. And the ones that are about the 3-dimensional models are the predictions from our group, because what we did is simulations of bulk systems, but then measured on a free surface, just like the experiment would measure. So that little s means there is that we measured it on a free surface like the experiments. So the circles are theoretical predictions. The line is what came out of the experimental analysis, and the width of the line is error bars. And so the exponents are not matching the 2-dimensional they're not matching the 2-dimensional models very well, either the clean case or the percolation case or the random field case. There's some exponent that's pretty off. If you look then at what is plausible for matching that criticality, the 3-dimensional models stand out, okay? So either the clean 3-dimensional model or the random field 3-dimensional model. And so here's an interesting question then that's already answered by the analysis, which is that, how do you know if that pattern formation that's in the SCM, how do you know if that's a bulk phenomenon or a surface phenomenon? It could be the case where it just grew on the surface and it's not really happening in the bulk. Much like frost growing on a window would be a 2-dimensional effect. But sometimes when you look out a window and see a fractal, it's a tree. It's something that fills space. And you can tell the difference by eye because of the geometries and because of the fractal numbers. So likewise, what we're saying here is that this pattern observed by STM is not like the case of frost growing on the window. It's not 2-dimensional. It's a 3-dimensional effect that you're seeing intersect the surface. So that's nice. We do know that this is a bulk effect. Otherwise, you wouldn't get those critical exponents and you wouldn't get those fractal numbers. They're 3-dimensional textures. Now, here's another mystery, okay? And if you want to see the deeper analysis on this, it's on the archive. The next mystery that came up in the data sets is that we got the same results for all the dopings that Hoffman's group and Eric Hudson's group measured. So 2 underdoped samples, 1 optimal sample, 1 optimally doped samples, and 2 overdoped samples. All gave the same critical exponents. Now you expect the critical exponents to be the same because they're universal, right? That's what universality is about. But I expected to see that the correlation function would have a doping dependence because as you approach a critical point, so I expected an ordered phase and then a critical point and then a disordered phase, and that as you approach this critical point, the correlation link to blow up like it did in that video that I showed you. However, what the data showed is that the correlation length exceeds their field of view over the entire doping range. So that's a bit strange, but it does actually help you distinguish between the last 2 models. Was this clean Ising or was this random field physics? And so when you have broad critical region. That's actually characteristic of the random field Ising model. You can get 2 decades of scaling in that model, even 50% away from the critical point. And that's something that I think we're not used to in thinking about quantum materials. We're used to thinking about quantum critical points, right? So in a quantum critical point, the diagram up here on the right, you have your ordered phase and a disordered phase, and you're tuning into the disordered phase through quantum fluctuations. And there are 2 regions of criticality here. There's the classical critical region, which hugs the this piece here, the ordered to disordered phase. And then there's the quantum critical region, which is a nice wedge. But notice that quantum critical region is confined to a narrow range of doping. Now, quantum critical points are not the only type of zero temperature critical points. The random field fixed point is also a zero temperature fixed point. And look what it does to its critical range. So the random field fixed point is a classical, it's not a quantum critical point. It is a zero temperature fixed point. You're just tuning by disorder strength. And it's got a huge critical range. This is what I really want to emphasize. So you can see this 2 decades of scaling even within a factor of 2 of the critical points. You can be at 50% of the critical disorder strength and still see 2 decades of scaling. It's very broad. So if I look at then the phase diagram of BISCO and look at temperature versus doping, these red dots indicate where they had samples to measure. 2 underdoped samples, 1 optimally doped, and 2 overdoped. This whole region down here was critical, which doesn't match quantum criticality, okay? It's a very broad critical region that's inconsistent with quantum criticality. So this pattern formation, I want to argue, is classical criticality and not quantum in this case. Because of the doping dependence, right? Or I should say the doping independence. It's not showing a doping dependence. Now, what are the implications then for this material and also other quantum materials that are showing this kind of pattern formation in this universality class? One of the implications is that the random field Ising model is known for broad criticality, but also for lots of hysteresis because it's worse than critical slowing down. We're used to critical slowing down, but this has extreme critical slowing down. The barriers to equilibration, the time scale to equilibrate blows up exponentially with proximity to the critical point. That's this function here. And so it's really easy to see hysteresis. It also means you should expect glassiness. It also means if you didn't control for all the hysteretic effects, you might get in a region of non-repeatability. And I will end there. Thanks for your attention, and I look forward to your questions.
I have a question. Erika, this is Adriana. How are you doing? Let me just put my face. Yeah, so the question that I have is, if you were able to clean your sample more and more, do you think that, or if you were able to dope, to introduce doping without introducing disorder, do you think that this region of criticality would be reduced and eventually you would see the quantum critical point effect or not?
Oh, that's great. So I don't want to say that, first of all, can the people in the room hear Adriana's question?
Yes, yeah.
Oh, okay, great. Okay. So Adriana, that's a brilliant question. And I'd love to know the answer. So I don't think that this critical point precludes quantum critical behavior. I think you could get both, okay? You know, you could have some quantum critical going on as well, but they're going to affect different regions of the phase diagram. So I think that's a great idea to look at, you know, can you dope these things without actual dopant atoms? So like maybe put it in a field effect transistor configuration and dope it that way, for example. Yeah, that'd be great to see because this criticality depends on disorder. Now I will warn you that, you know, disorder, people work really hard to make really clean samples, and thermodynamics is against us on that. So you can make the cleanest sample, it will still have a little bit of disorder, and if you set it on a shelf at room temperature for any length of time, it will gain disorder over time, right? So you need a really clean sample measured really fast, right? But I think that's a great idea. Yeah.
Thank you.
Okay, any more questions? We have 1 minute, if anyone has a short one, or we can thank Erika once again and move on to the next speaker. Okay. Thanks very much. Okay, the next speaker will be Adriana Moreo, and you're on. Oops. Wait.
I need to be my co-host, I guess, to be able to put my talk.
Sorry, yeah, can you share your screen?
Let me see. I am.
Can you hear us?
Yeah, I wonder if so let me see if I can. Just a second. So I need to open my talk. Okay, I think I can share screen. Okay, yeah. Can you see my talk?
Yes, we're good.
Okay, so let me, when I compact the thing a little bit. Okay. Okay, so can I start? Can you hear me? Okay, so I hope that you can hear me. I cannot hear anything right now. I just want to thank the organizers for giving me the opportunity of presenting my results here. Okay, thank you. I see you can hear me. For giving me the opportunity to present my results here. Particularly, I want to thank Antonio, and I hope that the next year I will be able to be there in person. So today I want to tell you about the multitude of topological phases that we have found by numerically studying systems of interacting electrons in dice and Lieb lattices with Rashba coupling. So this is work that I did in collaboration with Raul Soni, Nitin Kaushal, Amit Sanyal, Satoshi Okamoto, and Elvio D'Agoto. So let me start with the motivation. Okay, so we know that topological insulators are systems that are insulating in the bulk, but can have currents on their surface. And these currents are topologically protected, which makes these materials promising candidates for applications. Because small perturbations are not going to disturb the currents, okay? So models for topological insulators have been found in non-interacting models that display quasi-two-dimensional flat bands with a non-zero Chern number in the presence of external magnetic fields, okay? So that was one traditional way of trying to find these topologically non-trivial systems. And the Chern number equals the number C of chiral modes at the edges if open boundary conditions are used. So for example, this is a system that has a Chern number equal to 1. So examples of these models are the tie-binding model on a honeycomb lattice with a staggered flux proposed by Haldane, and then tie-binding models in a dice lattice, as we see here, when a spin-orbit interaction is added, or a tie-binding model in a Lieb lattice, as we see here, with a spin-orbit interaction. And the question that we want to address today is what happens when Coulomb interaction is introduced in these two models. The question is whether the surface states will survive and whether novel topological phases will appear. So in order to do this, let me tell you a bit about how we calculate numerically the Chern numbers in a lattice, okay? So the Chern number is a number that is gauge invariant and characterizes a topological protected surface states. For example, this is a state with Chern number equal 1, this has Chern number equal 2. and it is calculated in terms of the so-called Berry curvature, which is in turn is a gauge invariant property, which is in turn defined in terms of the so-called Berry connection. The Berry connection is obtained as an overlap between a block function at a given momentum, the overlap with the derivative of that block function with respect to one of the components of the momentum. And this derivative can be written as a difference if we have a discrete system. And using this expression for A and using the discretization I wrote here, we end up with the Berry curvature written in terms of overlaps of block functions at different sites in momentum space. In order to actually calculate F12, we need to go around a plaquette calculating overlaps of block functions. And because of this, that resembles a magnetic flux, this is also called the Berry flux. Okay, so we can calculate this Berry flux in terms of these variables. If we define these variables U, that are not other things than the overlaps divided by their absolute value, we obtain that the U's are basically phases, okay, of the form e to the I phi. And looking at this, comparing or replacing in this expression U and trying to obtain F, we see that F can be obtained as the logarithm of the product of the variables U going around the plaquette, with the caveat, the admissibility condition, which is that it has to be in this interval. And that means that the chair number can be obtained in a discrete way. So rather than doing the integral over the torus, we just evaluate F12 over all the plaquettes inside the first Brillouin zone. And this result, when we divide this sum by 2 pi I, gives us an integer number that can be positive, negative, or 0, when n relates to the band in the system, okay? So for a topologically trivial system, Cn is equal to 0 for all the bands, okay? And this was believed that most of the systems had that property. But when Cn is finite, in fact, this tells us that there is a possibility of having surface currents, and also that there is a possibility of observing the anomalous quantum Hall effect, because the Hall conductivity is related to the sum of the chair numbers over all the field bands in the insulator, okay? So if the chair numbers are different from 0 and they do not cancel, we will be able to observe a quantum Hall effect without introducing a magnetic field. Okay, so now let's see what are the results for the non-interacting systems in the lattices of interest. So this is the dice lattice. It has a unit a cell that contains 3 sites, one labeled here 1, 2, 3. It's a system that can be kind of created experimentally via transition metal oxide heterostructures going along the 1, 1, 1, 1 direction. It can also be created via optical lattices or in photonic crystals. And the non-interacting Hamiltonian in real space contains a hopping between different color sites, okay? An off-site energy for the red sites, and the Rashba spin-orbit coupling. Because of the lack of interaction, we can go to momentum space, and we can write a 6 by 6 Hamiltonian matrix because of the three sides and the spin degrees of freedom. And this matrix can be diagonalized for each value of k. Doing that, we obtain the band dispersion. So in the most trivial case when there is no spin-orbit coupling. This is the band dispersion. There are 3 bands with spin degeneration. There is the bands touch here, okay? When we introduce the spin order coupling, the bands separate, but they are still spin degenerate, and the system is still topologically trivial. And if we add a Zeeman field along the 1-1-1 direction that breaks time reversal symmetry, we finally split the spin degeneracy, and you see that non-trivial Chern numbers appear. And in particular, if we go to half filling, this system will have a Cn equal to 2 and will admit the anomalous quantum Hall effect. So what happens in the Lieb lattice? In the Lieb lattice, again, is a system that can be realized in materials with a geometry similar to the copper-oxygen planes, not in the cuprates, of course, in optical lattices or in photonic crystals. So again, we have a Hamiltonian that has a hopping between the sides of different colors, okay? And we have an offsite energy for the red sides, and we have the Rashba spin orbit coupling. Notice again that there are 3 sides per unit cell. So again, because there are no interactions, we can write a 6x6 matrix in momentum space. And if we diagonalize this matrix, we find the band structure. This is in the case with only hopping. So all the bands touch at the pi point, and the system is topologically trivial, as you can see here. If we introduce the Rashba term, you see that now there is a non-trivial Chern number for the doubly generate state. This can be calculated in this case, but we are not going to observe the anomalous quantum Hall effect because these levels are degenerate. But if we break the degeneracy, again putting a Zeeman magnetic field, we see that there are non-trivial Chern numbers. At half filling, there is a very tiny gap, so the system can be half filled, and the sum of the Chern numbers is different from 0, so the anomalous quantum Hall effect can happen. So let's see what happens if we consider the Coulomb interaction, okay? So technically, we have to put the Hubbard term and the Hund coupling because there are several orbitals, and this is a difficult problem to solve. It requires many body tools. So as an initial approach, we decided to use a Hartree-Fock approximation. And because people would expect that the ground state in these systems would be ferromagnetic, we decided to use mean field states that are invariable or translational invariant unit cell by unit cell, okay? This means that we can work in momentum space even with the interaction, and in momentum space, this is the 6x6 quantum Hamiltonian matrix, and this is the classical part. Okay, and in order to solve the problem, we had to diagonalize the Hamiltonian matrix, but finding these average values self-consistently. Okay, so let's go to the results. Okay, so these are the results for the dice lattice. So we were able to work in a 60x60 lattice. That means that each of the 60 sites contain 3 points in the dice lattice. Okay, so this is effectively like a 180 by a 180 system. The first thing that we did was to look at the ground state, the magnetic properties of the ground state. What we observe is that the spins, for example, in the site 1, are developed magnetic order, and this magnetic order is ferromagnetic. This happens as we turn on U. You see, we have a lambda that is finite. We turn on U, and there is a jump in the value of the spins in the blue side because that corresponds to the split of the flat band, okay? While the spin on the red side is smaller and increases smoothly. Okay. However, when we look at S1.S2, so the correlations between these two spins, we notice that it is negative. So this indicates that the ground state, rather than ferromagnetic, is ferrimagnetic. So this was a big surprise. It was unexpected. This state breaks times reversal, but is not a ferromagnetic state. And in order to be sure that this is not a mean field artifact, we also perform a Langsos calculation on a much smaller system, 2 by 2, which is actually includes 12 sites, okay? And we see that the ferrimagnetic, the ground state is ferrimagnetic. Okay. The other thing is that after this jump, there are no any features in the magnetism. So by looking at this order parameter, we wouldn't expect to see any variety of phases characterized by symmetry in this model. However, when we look at the topology, that means when we calculated the Chern numbers as a function of U and lambda, we got a big surprise. This is what we obtained. So we found a remarkably large number of phases characterized by a variety of Chern numbers. These are the Chern numbers for each of the 6 energy levels. So you see that at U equals 0, well, very small U, we didn't start at 0, but we have basically the trivial phase with all the Chern numbers equal to 0. But as we start increasing U, we go to phases with a variety of Chern numbers as large as 3. One interesting thing about the results in the dice lattice is that if you look at the sum of the Chern numbers in the 3 lower bands, is always 0. This would actually indicate that at half filling the system will be a Chern insulator rather than a system that will have the the anomalous quantum Hall effect. Okay, but still we can get that away from half filling. So let's see what happens with the energy levels as we move across the phase diagram. Okay, so here if we go, if we increase U, keeping fixed lambda, this is what happens with the energy levels. Okay, so you see how, for example, here in going from phase 3 to phase 4, what happens is that we had these two Chern numbers are 0 and 2, and here they become -1 and 3. So this one gets down by 1, this one gets up by 1, and the increase happens because these two levels at some point cross with each other, okay? And this is the mechanism by which we change we go through the phases by crossing of levels. Here we see another example, keeping lambda fixed to a larger value, 0.8, we go from the trivial phase to a non-trivial phase in which these are the numbers that change. So is due to a cross in these two levels. Notice that here the jump is by 2 rather than 1. Okay, this increases by 2, this decreases by -2. The way in which we find this energy, these boundaries, these topological boundaries, is by monitoring the gaps between the 6 bands and seeing in all the Brillouin zone, okay, for all the values of the momenta, when these gaps, or when some of the gaps go to 0, okay? And so here you see that the 3 transitions related with going to from phase 3 to 4 to 5 to 6, this means going along these lines from the green, okay, all these transitions, corresponds to the closing of gaps between the bands. Okay. And here you can see exactly when these crossings happen. For example, this is at the boundary between the phase 3 and 4. Okay, so it would be here. So you see that these two are the bands that cross, that they had originally chart number 0 and 2, and after the crossing, they will go to -1, 3. Okay, so here, in order to get the 4 to 5 transition, still these two bands are the ones crossing, so these are the two numbers that change. And when we go from 5 to 6, we see that the bands, the numbers that change now are these two, -2, 0, go to -3, 1. This decreases by 1, this increases by 1, and these are the two bands that are crossing. Okay, so this is the way in which we get this phase diagram. So let's see what happens with the leaf lattice. In the leaf lattice, we are able to study 64 by 64 clusters. Again, remember that they contain, for each side of the momentum space, there are 3 orbitals, let's say. And again, we measure the magnetization, and again, we find the same result as for the dice lattice. So there is a ferrimagnetic ground state as opposed to a ferromagnetic one, as some people had predicted. Interestingly, in this model, this magnitude 2s1 plus s2 has a little kink here, but is not associated to any kind of topological transition, and we still don't know where it's coming from. Another interesting feature of the leaf lattice is that we need to perform a gauge transformation if we want to calculate the Chern number in the first brilliance zone, because as written, the wave functions are periodic in 2 brilliance zones, and that creates problems if we want to calculate the Chern number in the way I told you. So if we extend the brilliance zone, we can calculate it by performing this gauge transformation. We downward the first brilliance. This transformation effectively moves these orbitals onto the same.
2 minutes.
So what happens when we calculate the topological phase diagram? Again, we find a large number of topological phases as we did before. An interesting thing is that if you look at the phases that appear at weak coupling 1 and 2, you see that the sum of the lowest 3 Chern numbers is different from 0. Okay, so this technically gives the possibility of observing the anomalous quantum Hall effect in this system. Okay, then as we increase U, you see that we go to this regime in which the sum is 0, and this would correspond to a Chern insulator, similar to the case of the dice lattice that have filling. Okay, so let's see again how this arises. So in the leaf lattice, for example, this is the phase number 1, okay, that is observed for these values of U and lambda. And what you see is that it looks as if the Chern numbers are non-trivial, and it looks as if there are band crossings, but actually there are very small and tiny gaps. And the same is true in the phase 2. Okay, so these are not band crossings, but are very tiny gaps. On the other hand, if we start increasing U at larger values, for example, at lambda over t equal 0.3, you see that the gaps become larger, and the separation between the lower and upper bands becomes larger and larger as expected as U increases. Okay, so let me wrap it up. My time is almost up. So as a summary, let me tell you that introducing both Hubbard correlations and spin orbit coupling in electronic in electronic models is currently one of the most important challenges in condensed matter theory, because interactions, electronic interactions are always there. So we need to know how the topological insulators react to that. Our study unveils ferrimagnetic order, which was unexpected. Remember that it breaks time reversal, which is why it may allow the anomalous quantum Hall effect. And there is a plethora of hidden topological phases in both the Lib and dice lattices. The topological phases are characterized by different Chern numbers and appear unrelated to other physical observables. Our results confirm the growing perception that topology is everywhere. That means that a large percentage of well-known systems may have non-trivial topological properties. We need to understand how they impact the physics of the materials, of course. So the half-filled dice lattice is a Chern insulator because the sum of the Chern numbers of the three bottom bands, the occupied ones, is always 0, while in the Lib lattice there is a possibility of observing anomalous quantum Hall effect at very low values of U. Finally, the anomalous quantum Hall effect could occur in both lattices by changing the chemical potential, because a bunch of the Chern numbers are non-zero. And the next challenge is to perform the Mirarchi studies on ribbons of these lattices in order to confirm the mean field results that I presented here. Thank you for your attention.
Right. Well, thanks very much for the talk. Let's see, we're running on negative time, so if we have one quick question. It's getting late in the day and we're getting pretty tired. Okay. Well, that was good. Why don't we just move on then? Adriana, thanks very much again.
Thank you.
Right. And then the final speaker of the day, no, sorry, not the final long talk of the day, is also going to be virtual. So I can get this right, Cenke Xu, right? And you're ready to go?
Yes, yes.
Okay.
Can you hear me?
Right. Yes, yeah, we can hear you.
Oh, okay, great. Yeah, so first I want to thank the organizers for putting together this great conference. And I apologize for not being there in person. So today we'll talk about a theory for an exotic interaction-driven continuous metal insulator transition. Actually, this was motivated by a recent experiment on a metal insulator transition in TMD Moreo heterostructure. So let me first acknowledge my collaborators, so Yichen and Xiaochuan, they are students in my group, and Mengxing and Zhu Xi, they are postdocs at KITB, UCSB, and Chao Mingjian, who is a faculty member at Cornell University. So basically, I will first give a quick review about two-dimensional conductivity and resistivity, and how they are actually universal quantities. I mean, they can be universal quantities in many scenarios. And then I will review the recent experiment on metal insulator transition in TMD Moreo heterostructure. I will focus on the fact they found and also some pretty surprising puzzles. And then I will propose a candidate theory for this exotic interaction-driven MIT. So first of all, I want to point out that actually, while it's a well-known fact that in purely two-dimensional system, the electric conductivity and the resistivity, they are actually a dimensionless quantity, which means that they can take a very universal value. Here by universal value, I mean that they can be independent of the UV details or microscopic details. So the most well-known example of such is the quantum Hall effect, for example. So in quantum Hall effect, we know that the Hall conductivity actually is just the order of E squared over H times a universal constant. And actually this constant is quantized. And here the universality is guaranteed by topology. So it turns out that in many 2+1 dimensional critical point quantum phase transition, the electric conductivity and the resistivity, they are also universal quantities. So here actually both the DC limit and also AC limit, actually the conductivity can take different values, but they are both universal quantities. By DC limit, I mean the limit where omega over temperature goes to 0, and AC limit means that the frequency over temperature goes to infinity. So, for example, this diagram, this plot here is actually a typical example of what was observed in a superconductor to insulator transition in a thin film superconductor material sample, and you can see that actually as the critical point, actually the conductivity is actually kind of insensitive to temperature, and actually you can see it's as the order of 4e squared over h. The reason is 4e squared over h instead of e squared over h is because actually Cooper pair carries charge 2e instead of e. Yeah, and also a third example of this kind of universal behavior of two-dimensional transport is the criterion for bad metal. So this was started by a lot of authors. So this actually is one of the typical paper, I mean, one of the early papers which actually pointed this out. So suppose we use the standard, a very rudimentary formalism to study the conductivity of a metal. So the dual theory, basically, the conductivity will be n e squared tau over m, and tau is the mean free time. We can just choose tau equals to the mean free path over velocity. So, so basically the dual theory actually applies when there's a semi-classical picture of the metal. So for this picture to work, we need the mean free path to be greater than 1 over kf. Kf is the Fermi momentum. So this means actually there's a lower bound for conductivity or upper bound for resistivity. And then this upper bound for resistivity for two-dimensional metal, where we can use the semi-classical picture to describe the metal. So this limit or upper bound is called MIR limit. And this limit is also h over e squared. So actually in two dimensions, a lot of scenarios, actually the transport properties, they are universal. Okay, so now let me talk about a metal insular transition. So metal insular transition can be driven by disorder, of course, can also be driven by interaction. So here I will focus on interaction-driven continuous metal insular transition on, for example, the triangular lattice. So let's imagine we have an extended extended Hubbard model on the triangular lattice, and then by turning on the interaction, then supposedly at a certain critical interaction, actually there will be a metal insular transition. At filling 1 means that 1 particle or 1 electron per unit cell. So this theory was proposed by this series of authors. So the basic picture for this theory, the metal insular transition, is that there's a parton construction. So basically, they actually can formally write the electron operator as a B times F. So B is a scalar parton, bosonic parton, which carries charge only, and F is a fermionic parton, which carries spin 1/2. So the advantage of writing an electron in terms of B times F, so the advantage is that now the metal insular transition becomes almost just a transition within the B sector, within the charge sector. So basically the bosonic charge B will go through a superfluid to a boson mod insular phase transition. Then the fermionic parton will not have much change at all across the transition. So this superfluid to insulator transition of the B parton actually can be interpreted as a metal and the insular transition of the electron. Okay, and then they say, how do we evaluate the resistivity of the entire system? So it turns out there's a locking rule which actually says that the total resistivity of the system will become the sum of the bosonic part plus the fermionic part. So rho of the entire system will be rho B plus rho F. Okay, so you can see that suppose rho F is just a standard metallic behavior, then actually the resistivity is pretty much controlled by rho B. It's pretty much controlled by rho B. Okay, so actually as the critical point of rho B, as a critical point of the bosonic parton, because rho B is at order h over e squared, and because rho F is a standard metallic behavior, and a standard metallic behavior rho F will be smaller than h over e squared, then we should expect that in this picture, the critical resistivity should also be at h over e squared, like many other quantum critical point as the in 2+1 dimension. So indeed, this is a theoretical sketch of how the resistivity should behave. And actually, you can see that as the critical point, as a function of temperature, the critical resistivity should just be an order of h over e squared times the constant, of course. Okay, so this is a prediction from the previous theory. So let's actually briefly review the very recent experiment. So TMD, Moreo heterostructure, is a perfect example. I mean, the perfect system to simulate interacting electrons in 2 dimensions. So basically, the physics in the Moreo structure, in the Moreo system here, actually can be captured by an extended Hubbard model on a triangular lattice with a spin-line half fermion. So here I put a quote, so spin-line half is because here there's a spin-orbit coupling. Actually, there's a spin valley locking effect here. So it means that spin up is tied with one valley, and spin down is tied with another valley. So it means that here there's no, I mean, in principle, there's no SU2 spin rotation symmetry. Yeah, right. So actually, the here spin, more precisely speaking, is going to be a pseudo spin. And in this system, because actually there are 2 different TMD samples, they are stacked to each other. So without any twisting, actually the lattice mismatch will already introduce a Moreo potential. So without any twisting, this system will already have a Moreo structure. The Moreo lattice constant is going to be 5 nanometers. So actually, it's a this will be a extended Hubbard model on a triangular lattice whose lattice constant is about 5 nanometers. So basically, by turning on an external displacement field along the z direction, they can tune the bandwidth of the system, which means that they can tune the ratio between the interaction and also the bandwidth. So actually, they can actually plot the charge gap. You can see that the charge gap, pretty much actually close continuously at a certain critical point. So this is the metal insert transition critical point. And the claim from the experiment is that actually this actually is an interaction-driven continuous metal insert transition, and actually disorder in the system plays a perturbative role according to the experimental report. Okay. Yeah, so what's exotic about the system is that actually suppose we decide the critical point, the metal insert transition critical point, using the extrapolation of the charge gap. Actually, we can see that as the critical point, the critical resistivity is actually very, very big. Okay, it's very different from all the other samples we have seen, all the other examples we have seen. So for example, here, the h over e squared is here as the dashed line, here. But then you can see that this critical point, the critical resistivity, is actually way bigger. It's actually much, much bigger than h over e squared. Okay, it's exceptionally large compared with the prediction of the previous theory. So this actually causes a puzzle. So why is there a continuous interaction-driven metal insert transition where the critical resistivity is so large? So let me also compare the system with another system with the metal insert transition. This is a 2-dimensional electron gas. Okay, 2-dimensional electron gas. Of course, actually, this the picture for the transition will be different from the TMD sample because actually, well, I mean, we don't think this system actually is actually described by the Hubbard model, but still, nevertheless, we can see that in the 2-dimensional electron gas, as the critical point of the metal insert transition, the resistivity or conductivity, the conductivity will still be as the order of E squared over H, which means that actually the resistivity as the critical point is still going to be as the order of H over E squared. So that means that here, indeed, in the transition metal, in the TMD Moreo heterostructure, we are at a pretty surprising scenario where the critical resistivity is actually very, very big compared with all the other MIT sample. So we should try to come up with the theory or picture to understand this continuous MIT with a exceptionally large critical resistivity. Okay, so let me try to propose a candidate theory for this system. So let me start with a simple alternative parton construction. So in the previous theory, we have a parton construction, which is we split the electron operator in terms of a one bosonic parton which carries charge times another fermionic parton which carries spin 1/2. So here, let me just modify this parton construction a little bit. So we introduce one bosonic parton for each spin and valley flavor. So that means that C up equals to B up times F up, and C down equals to B down times F down. So this actually is an extremely simple or almost trivial modification of the parton construction, but actually we are going to see that it will lead to very different predictions. So for example, in this system, because the total filling factor is nu equals to 1, so nu equals to 1 means that we have 1 electron per Moreo unit cell. Okay, because the total filling factor is nu equals 1, it means that each boson B will have a half filling. Okay, so for example, for B1 or B up, the total filling will be a half of the boson number per Moreo unit cell. So because the boson is half filled, then according to the Lipschutz-Maddy theorem, we know that the boson model insulator cannot be featureless. It means that the model insulator of the boson has to be non-trivial. Non-trivial means that it has to break either translation symmetry, which means that it forms certain charge density wave, or it has some topological order, okay, or it has some topological order. So the simplest scenario actually may not be the most natural scenario. The simplest scenario is that the model insulator phase of the bosonic parton will have a Zn topological order. So this topological order will be compatible with the Lipschutz-Maddy theorem. Okay, so what is the consequence? So what is the consequence of the non-trivial nature of the model insulator in the system? Suppose the system has a non-trivial model insulating phase, then for example, a Zn topological order, then actually one direct consequence is that the charge will fractionalize. Okay, the charge will fractionalize at the Zn topological order. So instead of so basically the charge carrier, instead of carrying charge E, it will carry fractional charge, which is the E over N. This actually is a very typical property of the Zn topological order. So now we can immediately see that if a charge carrier is carrying E star equals to E square, E star equals to E over N, then as the critical point, then the critical resistivity should be as the order of H over E star square instead of H over E square. And because E star is actually smaller, then the critical resistivity should be, for example, here is going to be N squared times H over E square. So it means actually the critical resistivity can be naturally much, much larger than the previously proposed theory, which is H over E square. So the picture for this scenario is that actually this metal insulator transition is still going to be a phase transition between a superfluid of the bosonic parton B and certain model insulator of the bosonic parton B. But because of the non-trivial nature of the bosonic parton, then this bosonic parton insulator will have a Zn topological order, and because of that, the charge will fractionalize, and as the critical point, the critical resistivity will actually be much larger than the previously proposed theory because of the charge fractionalization. Okay, so this Zn topological order is the simplest scenario, but as I said, may not be the most natural scenario. So what is the most natural scenario? So the more natural scenario is that actually, as I said before, because the bosons have half filling, then a half filling boson, it can form a topological order kind of a model insulator, or form a charge density wave, or some kind of density wave model insulator. So suppose the fractional filling, suppose the fractionally filled boson have a certain density wave, then this actually can be captured using a theory which actually was proposed by my colleague Liang Balance many years back. It can be captured using the vortex condensation. So basically, we can start with a dual picture of this of the transition and consider the vortex of the boson B or boson B alpha. So the condensate of the vortex becomes the insulating phase of the boson, and then the metal phase actually becomes the insulator phase of the vortex. And then the density wave of the system is actually manifested in the fact that the vortex band structure will have multiple minima in the brane zone. So indeed, suppose we actually try to solve the vortex band structure with the half-filled boson in the background, then actually we can see that there has to be multiple minima in the vortex band. So it means that actually the vortex will have a multiple component vortex. Okay, so when there are n minima, in the vortex band structure, and these n minima are protected by the symmetry of the system. So when there are n minima in the vortex band structure, then the charge carrier will again fractionalize and become the E star over E over N. Will become E star over E star equals to E over N. So this is very similar to the Zn topological order. And again, because the charge actually fractionalized, actually the critical resistivity will be bigger than a previously proposed theory. So how big can the N be? Okay, how big can the N be? So indeed, actually, we have played with this vortex band structure a little bit. We can see that N can take the value 4, 6, 12, 24, or even infinity, which means that when N goes to infinity, it means that actually there's a ring degenerate minima in the brane zone of the vortex. So it means that there's a very rich phase diagram. And also, but however, unlike the case with the Zn topological order, the resistivity here will actually gain a factor of n rather than n squared. So for example, the AC limit resistivity will be 4n over pi times h over e squared. So it's still a big enhancement. It's still a big enhancement compared with the previously proposed theory, but this enhancement will be as order n instead of order n squared. Okay. This is the AC resistivity. We can also compute the DC resistivity, which actually is much more difficult, but actually we can do it with a Boltzmann equation. So indeed, for the DC resistivity, actually it will also acquire enhancement with a factor of n. Okay, it goes like this. Okay, so here is a catch. So actually, so normally we would see. Normally we would expect the DC conductivity will actually always go to infinity when there's no disorder, because actually the momentum relaxation rate, the momentum actually will have a momentum is conserved. And as long as there's a non-zero overlap between the current density and the momentum density, and as long as the momentum is conserved, then the conductivity will always be infinity. But it's not the case here. It's not the case here. The reason is that the bosonic parton, the bosonic parton of the theory actually has a emergent particle Hall symmetry, and this particle Hall symmetry will guarantee that there's a zero overlap between the current density and also the momentum density. So the momentum density conservation actually does not lead to a divergence in the conductivity of the bosonic part. Okay, so the bosonic part can still contribute a finite non-zero answer to the resistivity, and also the fermionic parton contribution to the resistivity mainly comes from the scattering rate disorder, and it's supposed to be much weaker, because actually, as we learned from the experiment, the disorder plays a perturbative role in the system. Yeah, so this is a phase diagram of what's going on in the system, of what we think is going on in the system. So the metal phase actually is a superfluid phase of the bosonic parton, and then actually the mod insulated phase actually is the mod insulated phase of the boson, and also it's a spin liquid phase of the spins. And then the boson, the vortex of the boson will have a multiple or even infinite number of minima in the band structure, which actually will cause the charge to fractionalize as the critical point. Actually, this is the reason why the critical resistivity is so much bigger than what was proposed and predicted previously. Okay, so this is the phase diagram. So what kind of predictions can we make? What kind of predictions can we make based on our theory? So one obvious thing to predict is that actually there are two gaps in the system. One gap is the transport gap in the insulating phase. So in the insulating phase, we can try to fit the conductivity with the activation gap and try to extrapolate, and try to extract a activation gap. And because the charge is fractionalized in the system, the activation gap will be controlled by the fractional charge gap in the system. But however, suppose we
2 minutes.
Yeah, understand. But suppose we measure the tunneling gap. Suppose we try to tunnel an electron into the system, then actually the gap will still be given by the electron gap. And the electron is n copies. It's actually roughly n copies of the fractional charge. So this means that there's a contrast or difference by a factor of n between the tunneling gap and also the activation gap, which we can extract from the transport experiment. So suppose we observe this clear contrast between the two gaps. Actually, this could be evidence of the charge fractionalization going on in the system. Another prediction one can make is that, for example, there's a quasi-particle weight. I mean, we know that in non-Fermi liquid or as the metal insulator transition, the quasi-particle weight usually vanish. And actually here, because the charge fractionalized, we can also predict that the quasi-particle weight will scale with the tuning parameter in certain way. And the scaling, this beta n scaling actually will also increase with n. This is another prediction that one can make. Okay. So this is the end of the pretty much the end of the talk. So actually, in the summary, we reviewed an interaction-driven continuous MIT observed in the TMD Moreo heterostructure, and I point out that the one thing which I find very exciting and actually surprising is that the critical resistivity actually far exceeds the previous prediction. And then we propose the exotic theory to explain this exotic fact. That is, there's a charge fractionalization going on as the mod transition. Also, so let me acknowledge the funding agency, the Simons Foundation, and also National Science Foundation, and also there are some other related works previously and also recently. Okay, yeah, thank you. That's the end of my talk. Thank you for your attention.
All right, thanks very much. All right, let's see, time for a brief question. Right, everyone, end of the day, pretty tired. Okay, me too. All right. Okay, well, without any questions, again, thanks for a very nice talk.
Okay, thank you.
Giovanni Mirarchi, will be talking. 15 minutes? Okay, so 13 and 2. Okay. Thank you. Okay. Okay, first of all, thank you all for being here, and thanks to the organizers for this opportunity. I am a PhD student from La Sapienza, University of Rome. I work with Professor Sergio Caprara, who was an invited speaker from this morning's session. And in some sense, some of the things I will talk about today can be considered as a sort of integration of his talk. So today I will speak about some of abnormal properties observed in cuprates outside their superconducting phase. We remind that cuprates are materials made of layers of copper oxide alternating with layers of oxide of other metals. And the reason why they are so important and so interesting in the field of condensed matter physics is due to their wide phenomenology that is still not well understood yet. In this picture, we see a typical phase diagram of a cuprate superconductor. On the y-axis, we have the temperature, and on the x-axis, we have the hole doping level. And we see the presence of several kinds of order, like charge order or spin order. And we see the presence of several phases which compete or coexist within this diagram. For instance, at low doping, we have an antiferromagnetic phase at which cuprates become Mott insulators. At higher doping level, we have the superconducting phase, which is the green dome we see on the picture. And usually the temperature, the critical temperature at which the maximum critical temperature as a function of doping is referred to as optimal doping. So at the optimal doping level, the critical superconductivity temperature is maximum.
Well, outside the superconducting dome and the antiferromagnetic phase, the phase diagram is divided mainly into three parts: the pseudogap phase, the strange metal phase, and the standard Fermi liquid phase. Today, I will focus only on the abnormal properties of the strange metal phase. So why strange metal? The reason is the fact that within this phase, the standard Fermi liquid theory that explain the behavior of standard metals seems to fail in the description of some aspects of cuprates within this phase. And the most important example is the temperature as a function, the resistivity as a function of temperature. Since experimentally have been observed a linear behavior of the resistivity as a function of temperature, which is very robust in the sense that starts from very low temperature up to the highest measured temperatures, with no sign, with no change of slope, no sign of saturations at high temperature, and no sign of the standard quadratic behavior at low temperatures. Another interesting aspect regards the thermodynamics. In particular, if we plot the ratio between the specific heat and the temperature as a function of the doping level, there seems to be strong enhancement, possibly a divergence, at a level of doping which is very close to the optimal doping level. We know that close to that doping level, there is a Van Hove singularity, but it is possible to prove that this Van Hove singularity is not enough to explain this behavior. So there must be something else, but it's still an open issue. Another interesting aspect of the strange metal phase of cuprates is the presence of charge order. From a theoretical point of view, we can predict the existence of inhomogeneity of the charge density profile because of a compromise between a Coulomb repulsion with a strong short-range Hubbard-like channel and a phonon attraction strong enough to create an inhomogeneity. From the experimental point of view, we know that these charge density modulations actually do exist. We know it thanks to resonant inelastic X-ray scattering experiment spectra. We know their distribution in momentum space, which is dome-shaped with a Lorentzian profile. And we also know that they are dynamical objects. So I will refer to them as collective modes since we are talking about collective modes. And another very interesting aspect that has been experimentally observed is that in some phases of the phase diagram, there is the presence of two different kinds of collective modes signaled by two Lorentzian peaks, which have essentially the same characteristic wave vector, which is a finite wave vector incommensurate with the lattice, but one is narrower and the other one is broader. The narrow peak is commonly attributed to the well-known charge density waves, while the broad peak, which is a quite new discovery, is attributed to a new kind of collective mode, which we call charge density fluctuations in order to distinguish it to the previous one. They may have a common origin. They may be also the same object in under different conditions, but we will treat them as two different degrees of freedom in some sense. Well, while charge density waves, so the narrow peak, are observed only in a small part of the phase diagram, which essentially coincides with the superconducting dome, the charge density fluctuations are much more robust. They are present essentially in the whole strange metal phase. And moreover, differently from charge density waves, which are very narrow, charge density fluctuations, being so broad, are able to mediate an isotropic scattering between electronic quasiparticles along the whole Fermi surface, which makes this object suitable to explain the linear resistivity, at least in the high temperature regime. So this would suggest that charge density fluctuations may have an important role in this phase. The problem of this kind of collective modes is that in the limit of low temperature, we would recover the standard T-square behavior of the resistivity provided by standard Fermi liquid theory. So if we want to describe the strange metal phase of cuprates in terms of this collective modes, there must be a missing ingredient. And we identified this missing ingredient in a possible increase of the Landau damping of this oscillations, of this collective modes, which can be quantitatively described by the dimensionless gamma term that appears in the denominator of the collective modes propagator. Why is this can be the key ingredient? From the experimental point of view, we know that the correlation length of charge density fluctuations is always finite, in the sense that they never generate long-range correlation, and quite short. We are talking about 2 or 3 lattice spacing, no more. And the correlation length from our model does not depend on the Landau damping term. The characteristic energy scale at which charge density fluctuations modes activates is inversely proportional to the damping term. So if for some reason this damping term is large, we would lower the characteristic energy scale of collective modes, so we would extend the non-Fermi liquid behavior down to lower and lower temperatures, but leaving the correlation length unaffected, which is a constraint given by experiments. So this is the reason why this seems to be the right ingredient. We, at least for the moment, we don't have a microscopic model which could explain this, which would explain the fact that gamma can become large. So what I will show henceforth is essentially a phenomenological description. I'm just saying that if for some reason gamma is large enough, I can explain the linear behavior of the resistivity. So in order to reproduce the linear resistivity, we need that this parameter is large at least when the doping is close to the optimal doping and the temperature is low enough. But since the physical effect of an increasing gamma is to shift the spectral waves of collective modes down to lower and lower energies, we expect to see something also in the thermodynamic properties of these collective modes, and in particular, we expect an increasing in the specific heat. It is possible to prove that the relation between the specific heat given by collective modes and this parameter is almost linear. And so in order to fit both resistivity data and specific heat data, we choose this following phenomenological form of gamma, which seems complicated, but it's quite simple. It's essentially a parallel sum of two values that separately goes to 0 or to infinity when the temperature goes to 0 or the doping goes to P star. So we started from resistivity data, and we deduced the order of magnitude that gamma should have in order to fit the data. And of course, this value can be compound dependent, but sadly, we realized that these values are a little bit too large to correctly fit also the specific heat. So we get an overestimation of the specific heat. So by using the previous phenomenological form for the Landau damping term, we can reproduce the shape of the specific heat curves, but there is an uniform amplification which does not depend on temperature or on any other parameter. Well, resistivity data are fitted both qualitatively and quantitatively, while specific resistivity and specific heat data are reproduced only qualitatively, but there is this amplification. So just to sum up, we showed that our model is able to take into account, at least qualitatively, of 2 highly anomalous behaviors of cuprates. And it is possible to do so by touching only one parameter which appears within our theory, which is the Landau damping term. And this would suggest that charge density fluctuations actually could play an important role in the phenomenology of this space. And another interesting aspect of our description is that it shifts the role of the divergence of the correlation length to the divergence of the damping parameter of fluctuations which remain short range, which is in some sense, a new way to conceive critical phenomena, and it can be an interesting way to explore. The open issues are, first of all, the fact that we still miss a microscopic description for the dependence of gamma on the doping and temperature, and the fact that it's still unclear why the specific heat is overestimated. So it's still it's interesting, but it's still a work in progress. Just want to conclude by thank the people who helped me the most during these years. Of course, my two PhD supervisors, which are Sergio Caprara and Marco Grilli from La Sapienza, and also Gus Sebold from Cottbus and Carlo Di Castro from La Sapienza. And thank you for your attention.
Very nice. Questions?
I think I can hear you. Okay. Okay. So thanks for the question. The first question is the fact that the slope of the resistivity seems to depend on the doping level. So how do I describe it? Okay. So I'm not very sure to give an answer to this question, since I studied the behavior of the resistivity only close to the optimal doping, when the slope, so the slope does not depend so much, since I'm not moving so much from the doping. What we observe is that if we go far from the optimal doping, we don't get the linear resistivity, but at some point we recover the standard T-square. So I started from the resistivity data, and I simply watched in some way when I see the crossover. So if I am at the right level of doping, I never see the crossover. And if I move a little bit, I start to see a quadratic behavior, but I'm not going too far from doping level to see also the change of slope. So that's the first question. The second question regards the fact that how did I subtract that the Van Nove singularity. Okay. The fact is that when I did the numerical computation of the specific heat data, I considered both the contribution given by electrons, which is computed essentially by a quite standard Sommerfeld expansion, and then I use a technique to evaluate only the effect of the collective modes alone. So I simply computed separately these two contributions. Of course, the electronic contribution is renormalized by the effect of this collective modes, but this renormalization does not help to make the singularity stronger. Otherwise, it seems to suppress the singularity. So I made this computation, I subtracted it from the data, and what remained, I tried to fit only with the bosonic contribution. So that's the method I used. I don't know if.
Regarding the connection with the microscopic theory, I'm really trying the connection was done with the Albert Einstein model plus long range rule of the partial, then information of place, direction, Now we try the ideas nowadays. We use the fundamental microscopic model you are considering to make the vacuum parameters close to the fundamental.
Okay, as you said, I consider I started from a microscopic model which takes into account the phononic attraction, long-range Coulomb attraction, and a strong Hubbard-like local repulsion. We treated this Hubbard-like local repulsion within a slave boson approach, and this gave us a renormalization of the parameters of the Hoping parameters, and gave us an effective potential. Well, now if we compute the correlation, the electron-electron correlation function renormalized by a random phase approximation, taking into account this effective potential that comes from the slave boson approach, we know that it is possible to reach a singularity in the sense that the denominator of the random phase approximations goes to 0. And if we do, this happens at a finite wave vector, which presumably is the wave vector at which we see the peak. And if we do an expansion around Q equals to QC and omega goes to 0, we should reproduce the parameters of the propagator. So, yes, are the same. The fact is that we still, it's not clear why the linear term, which is the damping term, should have a particular dependence on the doping, and that's what is still missing. So that's it.
Second speaker again.